Hello and welcome to Chapter 13, Web Services. So what we've been doing so far is we've been using the request response cycle. We've learned about sockets, we've learned about URL lib, and we've actually learned how to pull HTML and even flat text off the internet. But what we're going to talk about now is using that same request response cycle to retrieve information that is specifically designed for programmatic consumption, so that we had to have this beautiful soup which sort of did a hack job or solve the hard problem of parsing HTML. But why not produce data in a format that makes good sense to a program, because programs want to talk to each other. If you recall, the whole idea of a socket is to have one application process sending data to another application process. And so if we think about this for a moment and we realize that we have all these programs, they could be written in different programming languages and they're all connected. And so they might want to send data back and forth through the network. PHP programs, JavaScript programs, Java programs. And so we have to decide on a protocol that is independent of any programming language. And we call that the wire protocol, because if you were to sort of take some connection and watch the exact characters that go back and forth, that's what you would see if you were monitoring the wire. So that's why we call that the wire protocol. And so the idea is that we have to agree on a format that is going to represent the data, and we can't make it a Python specific format or a Java format. And when we take the data from the internal representation, maybe a Python dictionary, to send it to the wire, we call that act serialization, and that is going from sort of the internal representation to the serial representation or the wire representation. And then here is an example of a person with a name and phone number with using less thans and greater thans. This is an XML example. And then in the far end, in a different programming language, it receives this and then deserializes it and then turns it into some useful structure inside that programming language. And so this is an example of a wire protocol that's using XML, and that's one of the formats we're going to talk about. Another format that we're going to talk about is a format called JSON, JavaScript Object Notation, and it is simpler and easier, but it's not as precise and descriptive as XML is. And so while you'll find that most of the things you run into, especially if you're talking to APIs of one form or another, you'll find that JSON is very common. XML still holds sway in places like documents. So if you look at docx at the end of a Microsoft Word document, docx means that it's an XML version of the representation of a word processing document. So the first thing we'll talk about is XML. So one of the two ways that we mark up data is XML, the other JSON. First we'll talk about XML. We'll talk about XML more for a longer time than we talk about JSON. XML stands for Extensible Markup Language. There was a number of markup languages in the 90s that were out there, ways to send data between computers. And none of them was like amazingly better than the other, but in the early 1990s, as HTML came out, the idea that we could use less thans and greater thans, or angle brackets, some people call them. Once HTML made angle brackets popular as a representation format, it was pretty natural that we would find a data representation format that would take a similar approach. And so inside XML, we're going to talk about tags, we're going to talk about attributes, we're going to talk about data, and we've already talked about serialization and deserialization. Serialization is the act of taking data inside of a computer in one programming language, setting it up for transport, transporting it across, and then taking it back apart and turning it back into the data in whatever internal data it needs to be in the destination system. So here is some basic XML, so we can take a look at the various things that make up the XML. So it's very much like HTML in that we have tags, less than, greater than. The difference is we get to name the tags anything we want rather than the A tag or the P tag or the H1 tag. And there's a beginning tag and an ending tag, and they're bracketed together. And there's syntax errors in XML. Syntax errors in XML are more severe than syntax errors in HTML. It's supposed to be right, and if you send bad XML, it's likely that the far end will not understand it. So we have a beginning tag and ending tag, and so like name and slash name are a beginning and ending pair. Then there is the actual textual content, and that is the material between it. And then here's a phone and slash phone, and we have this thing called the attribute. Key equals value. The key doesn't have double quotes. The value always has double quotes, and this is like href equals on an anchor tag. And sometimes you have what's called a self-closing tag, where you don't actually have a closing tag. You have all the data that you need in the attributes, and so you don't even bother putting an empty text area in a closing tag. So that is a start tag, an end tag, attribute, and then a self-closing tag. Those are some basics of XML. In general, XML doesn't care too much about white space. It does in the text areas, so in here it matters and here it matters, but things like we can indent this a little bit differently, and we tend to indent it in a way to make it look reasonable. Although once you have programs sending it back and forth, they tend to send it more compacted just for efficiency purposes. So one of the concepts is that there is a hierarchical structure within an XML document, and there are parent nodes and child nodes, and you can think of these as simple nodes that is a tag and some data, or a complex element that has a tag that includes other tags, some child tags. And there's a couple of different ways we can take a look at this. The simple and more natural way to think about this is a tree with parent-child relationships. So here we have this A tag on the outside, and that's the top level one. You can only have one outer tag, and you can't have another tag down here. So you have to have one tag that's sort of the root tag for everything in this XML document, and it has two children. So the C tag and the B tag are two children. So the B tag is a child of A, and then C has a D and an E tag that are children there, and then the textual data we model as a child of each of those tags, and you'll see in a bit why it's best to do that. So that is the way to think about this as a tree, to represent that XML as a tree. If we add attributes to it, and this is where you kind of see why it's nice to take the text area and make that be a child of the node, an attribute is a different. So the text is a special kind of child, and you can literally have more than one attribute. You could have x equals 2, zap equals whatever, and these could have a couple of different attributes. The w attribute is a value of 5, and that's the 5 down there, and so you could have multiple ones. You can only have one text node. Now, in the case of A, you have a whole bunch of text nodes, but these are because there are child nodes. Within one simple node, you can only have one text element. You can also think of XML as paths, and the easiest way is to sort of look down this tree version and look at from the path from the parent. So you go to A, then the child B, and then X. So at position AB, you find X. So AB is the path up to the root. So ACD, that's this one, is the path to Y, and ACE is the path to Z. And so you can think of these as paths. Part of what we're doing is we're coming up with ways to walk through and parse trees of XML data. So the next thing we'll talk about is how we determine if a particular XML document is legal or meets the contracts that two applications have set up. We're going to do a little bit of code. If you want to get your hands on the code, go to the materials website, materials.php, materials.php, and download the sample code. The code that we're going to work on today is the XML code, and we need to be able to talk XML to work with web services. And so here's one of the examples from the book. It's xml1.py. And so later we'll be pulling XML and JSON from the web, but for now we're just going to put it in a triple quoted string, so data, and we're going to use a built-in XML parser in Python called element tree. And when we say import XML eTree element tree as ET, this as ET gives us basically a shortcut handle for it. And so the idea, this is a string, it has less thans and greater thans, it looks like structured information, and it is. But really at this point it's only a string. Now we have to call this ET from string to read this and give us back a tree object. And what it does is this might blow up. This code might blow up right here if there was a mistake in it. Okay, and matter of fact, I can probably put a mistake in. Let's see if I can delete this and save it and run this code, and we'll see that it will blow up. Right? And so it blew up here in line 8. Element tree blew up, it blew up in line 12 of the code, which is right here. this failed because the line 8 of the XML string was wrong. So let's put that back in. So now it's properly formed XML. So this tree we get back, I name it tree just because I always name it tree, but you could name it X. So the key is tree.find goes and looks for a tag named find, and tree is no longer got less thans and greater thans in it. It is went and turned these into objects within objects within objects. So tree find name says I would like to find the tag name, and that's what this bit is right here. And then .text is going within that and grabbing that text, okay? And if we say tree find.email, then that's going to give us this. And then that's that object. And then .get asks for the contents of the hide attribute, which is the string yes. Okay? And so if we run this, now that it's fixed, Python 3 XML1.py, it will pull in and get the name and the attribute. So it pulled the Chuck out. And so you get this object and then you kind of dive into that object. And so that's XML1.py. If you've got a tag, you can either get the text out of the tag or you can get an attribute out of the tag. So now let's take a look at XML2.py. Again, we import element tree and we have a tag. And XML's always got to have a single outer tag. But this time we're going to have, in effect, a list. Now let's line this up a little better. There we go. That looks a little prettier. And so users, the fact that it's users doesn't mean anything, but we often come up with semantically meaningful names for these things. Users is going to have as its children a list of user tags. Okay, so the children under user, user under user, and then this has each of these as a tag. So we want to parse this, and this is a common thing we want to do. You know, and so again, the first thing we do is we read the string to just take this. It's a triple quoted string going from here to here. And then we're going to, instead of doing find, which gives us one tag, we're going to do find all the users tag, the user tag that is a child of users. And we get back a Python list of the tags, not of the text, but of the tags. So there's a one tag, and there is another tag. And so we can do len of that, so we can see that we got two. And then we can write a for loop, and this item is going to iterate through the tags that are the user tags that are children of users. So the first time item is going to be this tag, a tag, remember, and then the second time it's going to be this tag. And so we can do things like find and get, just like we did with in XML1. So running this is not too exciting. Python 3 XML2.py. You see that there are two users. That comes from this print right here. There are two users in there. And the first one, if we go into name and we go find the text within the name tag within user, then we get Chuck and we get the ID, which is 001. So we find the ID within that item, and then we get the text, and then we look and we grab the X attribute off of that. And so we see Chuck 001 and 2, and then in the next tag the for loop continues, and we print that out. Okay, and so that's just a basic run through of the XML from the chapter in the Python book. Okay, thanks. So now we're going to talk a little bit about XML Schema. XML Schema is a language that allows you to decide on whether or not a particular XML document meets a contract, an arrangement. So you have two pieces of software exchanging data using XML, and what if one of them, if they're all working, nobody really worries too much about it. But if all of a sudden one breaks, you change one side and the other one breaks, whose fault was it, right? Was it the side that got changed or the other side? And so you could argue. So what you like to do is, before you set up these arrangements between these applications, set up a contract. In a way, they're kind of like the RFCs are, except that their scope is between pairs of applications. And so it itself is XML, and it basically, what we do is we take an XML document and an XML schema contract, and then we either say that's good or that is bad, and that's called validation piece of software that validates XML when given a schema is called a validator. And so an XML document, here we have our little XML document, we're passing it to the validator, and then we have a schema contract, which is itself XML. It's kind of a particular kind of XML, that XS: complex type. That's just a tag. Colon is a legitimate character for the name of a tag. Name equals person, that's just an attribute. And so XML schema is a particular format of XML that renders an opinion about what XML is supposed to look like. So there's a number of different XML schema languages. The one we're going to look at is one that's kind of came a little bit later, that's very common, called XSD, which is the World Wide Web Consortium's schema specification. Often you'll find files that have suffixes of .xsd that actually contain the XML, just like we're going to show you. So if you recall, there are simple elements which have text children, and then there are complex elements where other nodes are children of other nodes. And so we can say this. And so here we have a little bit of XML, and the XML schema that makes sense with that. So what we're saying is the outer tag of this legitimate XML is supposed to be a complex tag with a name of person. And so there we go. That looks good. Good, good. Then there is a sequence, and then there is a simple element, a name of last name, looks good, and it's a string, that looks good. Another tag that's of a named age that's of type integer, that's good. And then a thing that's called date born, and then there it looks like a date. So we check all these things, and we can basically say, yup, that is a good XML document according to this schema. And you don't have to write this generally, but there is software that reads these two things and comes back with a true or a false, and might even have some detail as to what went wrong with this particular schema. Here's some more that you can do with a schema. We can do things like, have a complex type, we have a sequence. Here we have a string, full name, and a string child name. But we have this min occurs and max occurs. So min occurs is the minimum number of times it can occur, and maximum is the maximum. So min occurs equals 1, max occurs equals 1 means it's required. And so this is required, and we don't have two of them. Two of them would be an error. One of them is fine, so that's good. Here the child name is min occurs 0, max occurs 10. So we have 4 here, and so that's good too. And so that is another kind of XML schema constraint that you can have. Here's a few other data types that we can do. We've done the string, we've done the date. The date looks like this. Dates are 4-digit year, 2-digit month, 2-digit day with dashes. Now there's lots of different ways to represent dates, but the nice thing about this, and you have to put the zeros in, so 09 for September. It means that these are sortable as strings, so that if you do all your dates this way, they're sortable as strings. So you could argue what is prettier, but for computers we don't worry about that. We're arguing about what's the most functional. And then the date time is that same date format with zeros, followed by the letter T, and then followed by hours, minutes, seconds, 0 filled, right? So 9 o'clock is 09. And then the time zone, which we'll talk about a second in the next slide. You can have decimal numbers and you can have integer numbers as well. And so we are able to sort of render an opinion as to what is good and what is bad in the resulting XML. So dates are kind of interesting. There's, again, we have lots of different formats of dates, 9, 10, 9/10/2002, right? That's a format of a date, but that's one. There's another format of the date, which is 12 December 20, whatever. And so this is how people show dates. Computers don't want to have all those different dates and don't want to figure those out. They have libraries that produce dates and make them look pretty and for particular locales, but computers really want dates that work best for them. So we just say, okay, we're going to have this year, month, day, time, and then 0 fill, hours, minutes, seconds, HMS, and then time zone. Now, computers even prefer a time zone. I don't know if you've used something like your Google Calendar and you take a flight or take a train trip and you end up in a different time zone, everything switches. And that's because Google Calendar is not really storing the time zone that it's not storing the dates relative in your current time zone. It's storing them in what we call universal time, or Greenwich Mean Time. Zulu time is another word for that. And Z means this time that is the time in, London, England, Greenwich Mean Time. And so the thing is that means if this data moves between time zones or crosses the international date line or standard daylight savings time or anything like that, none of that changes. And so we have this internal date and time that's very common in situations where computers are exchanging data that then gets shown with a time zone, converted to the time zone or the local format. That's the right way to do that. And there's a standard for how dates and times are supposed to look. So here's another little example of some stuff. Let's see what we got. Now, if you see this little question mark XML, that's not a problem. That just is a way of sort of putting a header on the whole document that says it's an XML document, telling it that's a UTF-8 document. And that's not really a tag. That's sort of like a marker on the file, so that you can put that there, but it doesn't harm the XML. The outer tag is this tag right here, XS::schema. And then what else we got? We got an address. We've got a string. We've seen all those. Here we have country, and we're going to have a restriction that basically says this is a simple string, but we're going to make it so that you have to list one of these 4 as the country code. And so here we are down here, and that's UK, and that's UK, and so that is valid XML. Another couple of examples here. Let's see, string. Max occurs unbounded. That means infinite number. There's no limit on the number. You can do that. Min occurs of 0. Excess positive integer. We've seen integer, but you can also say it's got to be a positive integer. Decimal, we've seen that. And then use equals required is just another statement that you can make. I'm not trying to get you to the point where you can do XML schema. Just get you a sense of the kinds of statements that we can speak about when we're talking about what is and is not legitimate XML. So let's talk a little bit about how we might talk XML inside Python. And so, like most things that are in this extended part of Python, we have to import something. And so this is the name of a library, XML eTree element tree. And then as ET, this ends up being a shortcut. So we don't have to type these long things. And so ET is the same as typing that. It's almost like a macro. Now, normally this XML is going to come somewhere from the network, but I'm just going to put this in a string. I'm using a triple quoted string, and so that means that this triple quoted string starts here and ends here, and all these new lines that are here are actually part of the string. So this is kind of like I opened a file and read the whole thing in. But just to keep this totally self-contained, I'm putting it in a string. So the XML would come from some server on the other side of the network. We would get this XML. So that's how it would normally work, okay? So this is the XML right there, and we parse a string of data, and we call ET from string. So we're passing in the less thans, the new lines, the greater thans, all of this stuff we're passing in. And this could have syntax errors in it. So this might blow up if this had a syntax error, like we forgot the little slash or something, there was a syntax error. But this doesn't have a syntax error. So then what we do is we get back an object. I just happen to call it tree because it kind of is like that tree version of the XML. That is an object that we can then query to pull data out of it. So we say tree.find and look for a tag name name. So that finds the tag name name is this. It's everything. It's the tag and the text. If we want the text, we add .text, and then that .text, that actually refines it to only the word Chuck. And similarly, if we do tree.find email, that tree.find email, that finds the email tag, which is this tag. It has a child attribute, and you can get any of the attributes. You say .get. There's only one text child, but there are many attribute children, and so you have to tell it which one you want. And so this bit right here, all of that will resolve down to that string yes. That's what you're going to get there, yes. And so you kind of build up these little finds and call methods this is not clearly a full introduction to element tree, but you get the idea that you sort of dive down in with these methods that call methods that call methods to get little pieces out and parse all of that. Here is a different example. In this one, again, we're using triple quoted string. We always have a single tag on the outside, and then I have a complex type of users, and in it there are 2 user objects. So this is kind of like a list, right? So this is more than one of these things. So this user can occur more than one time. And again, we take this, we pass that into from string and get back an object that represents the name stuff. Does not necessarily have to be the same as this outer tag. Just a variable. This could just as be easily as X if I wanted. And so now what I'm going to say is, hey stuff, I want to find the tag, the path, users/user. I want to find all tags that match users/user. So that's going to give me a list of 2 tags, 1 tag, 2 tags in a list. Tag, tag. Oops. So 2 tags. Now I can print out how many I get. That'll be 2 in this case because I got 2 tags. And then I can actually iterate through the list. All right, so I can iterate through the list. So this item is going to iterate first to this tag, and that tag, now it's like in the previous example, we can look for the name tag within there and pull the text out. So we pull that text out, find the name tag, and then within that find the text. And we can find the ID tag and pull the text of that out. So that pulls out this 001, and I've scribbled too much. And then we can item, which is, this is item, is that whole tag, dot get X. So that gets the attribute, that gets the 2. That 2 comes down here. Okay, and then item goes to the next one because item is looping through, so item iterates down to that one and pulls out the name.text, the ID.text, and the attribute.x and pulls all those pieces out. So this is the basic pattern. You saw one where you're tearing into a single thing, and here you're tearing into something that is expected to occur more than one time. And so that's a quick summary of how you talk to XML in Python. Up next, we're going to talk about the other serialization format, JavaScript Object Notation. So now we're going to talk about the other serialization format, JavaScript Object Notation. Chances are good, as you go out there, you will very likely encounter more JSON than you will XML. Not that XML is bad. XML is better for rich and hierarchical documents, whereas JSON is best for just pulling data out of a system and moving it between 2 systems with the minimum of fuss. This is Douglas Crockford. I have a great interview from him. He's a funny guy, very, very smart. He claims he didn't invent JSON, he discovered it because it really is based on the literal notation for JavaScript. And it actually looks a lot like the Python literal notation for objects and for lists. Now, Douglas Crockford is quite a sense of humor. He wrote this book called JavaScript, The Good Parts. That's the little one right there. And then JavaScript, The Comprehensive Guide. And the sense of humor is all the stuff that's in JavaScript that's not too useful. And while this is sort of a tongue-in-cheek, it also is trying to say that JavaScript, what Crockford is really saying here is JavaScript is a great language as long as you avoid the tricky bits and sort of keep it very, very simple. And JavaScript is indeed a great language. But JSON comes from JavaScript. You can read about JSON at json.org. JSON is not an international standard. It's not like an RFC. It really is. Douglas Crockford decided to register json.org and typed in some pages, and people started reading it and people started using it. And partly that was because it was truly derived from the JavaScript JavaScript literal syntax. So we're all ready to code. Here is some Python that's going to process some JSON. Keep it straight. Python process JSON. So again, I'm using the triple quoted string here. Now you'll notice the syntax that we are using is not angle brackets, but instead curly braces. And so the curly brace, and then within the curly brace you have key value pairs, name, colon, Chuck. And the key colon value, and both sides have quotes. You can also have objects within objects, curly brace, key value pairs, key value, key value. Looks a lot like Python. And then you can do this. And so this is a structure that has one key value pair that's a string, another key value pair that's an object, another key value pair that's an object, and then these are key values within those contained objects. So this is a string that again probably was retrieved across the network from some other place. And we're going to pass that string into the JSON library load S. Load S stands for load from string. So it reads this, parses it, looks at all the white space. White space again doesn't matter too much here unless it's in between double quotes. The white space doesn't matter, and so it parses it and then returns us a dictionary. So the thing that's different about JSON is that its structure and representation are simpler than XML. So in Python, everything either comes back as a dictionary or a list, or a dictionary within a dictionary, or a list within a dictionary, but it's all dictionaries. It's not a separate structure that you have to do gets and finds and find-alls and lookups. So it's right there. So when we get this back, because this is a curly brace, info is a dictionary. And so we can just use the standard syntax of Python. Info subname. Well, that will bring, let's clear this. So info subname, we'll go find Chuck. So if you compare that with the XML, that's just a lot easier. Now, when we have info sub email, that's this thing. So info sub email is that thing. And then sub hide is this. So that's what comes out here. Okay, so it's really nested dictionaries and lists. We haven't seen a list yet, but this is a set of nested dictionaries that it parses. And it's equally simple in other programming languages. This is a little more complex version where the outer element is a square bracket, which means it's going to be a list. And so we have a list of 1, 2 things. So this is a list of 2 dictionaries. So there's 2 dictionaries inside that list. So again, we take this string and we load it into, use the JSON parser to read the string and give us back, in this case, info is a list. It's got 2 items. If we print out info, it'll give us 2. And we're going to iterate through. And so if we're going to iterate through, item is going to first be this, and then it's going to iterate to this. And it's going to print out item sub name, which is going to print out Chuck, item sub ID, which is going to print out 001. Now you'll notice that there is no attributes, and that's because JSON is simpler. But we can have the X, and it just is another item, so we say item sub X, and that's going to print the 2 out. And then it'll iterate to the next one, and it'll print out the same thing for those guys. And so JSON is simpler because you can't represent as complex a data structure, or you have to compromise and map it into a simpler data structure, but then it is lists and dictionaries, and so once you've got it parsed, it is easier to understand and to make use of. So that was quick. So that's partly why everyone likes JSON better, is once you have come up with a format that you're going to send it back and forth, it's easy to make it and it's easy to read it. Now what we're going to talk about is sort of moving up a level. If you've got all these data formats and URLs that you can hit to pull those data formats down, what approach do you do as you start to construct applications that increasingly go from a single application to a networked application? We're playing with the web services chapter right now, and if you want to get the materials for this course, you can go here and download the sample zip, samplecode.zip. I've got this all sitting already on my computer. I also have the whole thing in GitHub if you want to get it out of GitHub. So the thing we're talking about now is we're talking about the JSON1.py example from the book. And so JSON is kind of like XML except a lot simpler. And that's why a lot of people like it. It's not that JSON is always better, but JSON is better in a lot of situations that don't require the complexity of XML. So we start to import JSON. JSON is built into Python, but we have to ask to import it. Again, we're using a triple quoted string to put the JSON in there. And JSON looks a lot like Python dictionaries, key value pairs, key value pairs. In this case, this is a key, and the value itself is another dictionary, or in JSON terms, an object, but again, key value pairs within key value pairs within key value pairs. And all these little cursor guys have to, all these little curly brace guys have to line up properly. And so, like all the time, this is a string, which we normally would read and decode from the internet, but for now we're just going to have it in there. Load JSON.loads says go into the JSON library, pull out load string, and parse this, which turns this set of curly braces, spaces, commas, perhaps syntax errors into a structured object. And if we'd made a syntax error in here, then this would blow up. But if this doesn't make a syntax error, if this doesn't blow up, then we have a structured representation. Now the difference between XML and Python, JSON, is that this turns into a Python dictionary with key value pairs. Okay, and so once we have this, this is a dictionary. And we can say info subname, and that's the exact syntax that we would use to get the dictionary, and that's going to extract this value out of there. And if we want to go in deeper, we can say info sub email, and that's what info sub email is right there, and then sub hide. So that's a dictionary within a dictionary. And so if we run this, Python 3 JSON 1.py, it digs in really fast. And so this is why people tend to like JSON, is because you read the JSON, which is actually a syntax derived from JavaScript, but it looks just like the syntax for Python. So it's moving that's moving an object, a JSON object that turns in directly into a Python dictionary with nested dictionaries. Now we're going to look at JSON 2. And so JSON 2, we're going to see a list, or an array in JSON terms, but it turns into a list in Python terms. So this is a list of dictionaries. In JavaScript, that would be an array of objects, but in Python, it's a list of dictionaries. So we'll just pretend that it's a list of dictionaries. Again, we load the string, parsing, looking for syntax errors. So let's just make a syntax error here and run Python JSON2.py, and you'll see where it blows up. It blows up at line 15, which is right here. It's like this load s blows up. Now you could put a try except around it to save it, but we're not going to do that. And it even complains. It says, look, we're expecting something here in line 11, and that's line 11 of the JSON, which starts at line 4. And so I'll put my little square brace back in so it's not syntactically broken. So let's run it again and make sure that she runs, and yes, she does. So this parses it and converts from the JSON syntax into a Python, in this case, list, because it's got square braces instead of curly braces. The previous example had square braces. And we can then take a len of it, and it's an array, it's a list, and we see that there are two things in there. And then we're going to iterate through, and this item is going to iterate through these dictionaries, that dictionary followed by that dictionary. So the first time it's item sub name, which is this value right here, and then item sub ID, which is this value. So you can dig right into this, but you're not using get, and you're not using the weird extra find or find all or anything. You just are going at these structures directly. And so you can quickly extract this stuff out, and we read through ID is name is Chuck. Oops, name is Chuck. There are no attributes, by the way. X is 2, and so we had to make X. So if you look at the XML, we had this concept of attributes on the outer tag. These things are also not named. We just have to know what we're looking for. So JSON represents simple structures, but it's much simpler to use. So I hope this has been useful to you, and talk to you in a bit about some more JSON. So the service-oriented approach is a way we approach solving a complex application problem where all the data really isn't present in one computer system. It's somehow spread out over the internet, connected via the internet or internal network. And so the idea is that some applications just can't contain everything. The perfect example is a travel website that can book you a flight, book you a car, buy tickets, book you a hotel, and do all these things. Well, that travel website is neither a hotel nor a rental car company nor an airline. But what it really does is it talks to all these services somewhere else on the web on your behalf, and it makes reservations for you. And so you have this convenient user interface that says, oh, here's your whole vacation. I'm going to figure all this stuff out. Now you say go, and it goes book, 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 and books on all these other systems. Now it requires a lot of infrastructure, a lot of coordination, and a lot of effort to make sure that your application can talk, and these other services that are out there in the internet have good contracts, and you know exactly how to send data to them and get data back from them. And so initially, when you're building a service-oriented architecture, often you have one application and it's all internal. Often it's all one language, and then maybe you'll say, oh, wait a sec, we want to take part of what we do and put it in a second system, and then sort of come up with a set of rules between the systems, and then more and more and more. So now that we're solving our problem using a series of cooperating applications communicating across a network, we're going to talk a little bit more detail about the notion of what we call web services. And in this, we're going to take a different perspective. Instead of building our application and breaking it into pieces, we're going to have an application that's going to really consume an API from somebody else. So there is some other provider of this API that's not us. And so that if you're going to talk to somebody's data like Google or Amazon or Twitter, they're going to say you have to use our API. So what's that? So an API is a contract that says, look, if you do this and this and this and this, we're going to give you data this way. And they set the rules, they tell you what the URLs are, they'll tell you if it's XML or JSON, and this is called the application program interface, and it's something you read and you understand. And so you go look at the documentation. This is the documentation for the Google Maps API. So it turns out that Google knows a lot about maps. It knows a lot of data. It knows how to search maps. And it actually provides some of those features to you that your application can take advantage of. I took advantage of this at one point by asking all the students in one section of one of my online courses where they were from. And I just let them type in where it was. And then I said, well, I don't know how to code any of that. So I used this API doing what's called geocoding to look all those places up and get precise latitudes and longitudes for the ones Google could figure out. And that saved me a lot of work. Now, these are expensive resources, but I could be patient and make use of these resources, which as long as you use them not too much, they can be free. We'll talk a little bit more about rate limiting and what's free and what's not in a bit. But you start by reading documentation. It says, do this, hit this URL, hit that URL. So if you read that documentation, you will find that there is a URL that you can hit. And they tell you where to go. And then you go to this URL, you add a question mark, and then you say address equals, and then Ann Arbor plus, and there's all these rules. These are called URL encoding rules when you have key values on URLs. The plus means space and %2c means comma. So these are called URL encoded. But don't worry too much about that because we're going to have a magic library like we always do in Python that takes care of this. And so if you were to hit this URL, you type it in the exact right way in your browser, you will get back a JSON document. It's an object that has key value pairs. The first value is this status, then it has these results, and it's a list, and you dive down, and eventually you can kind of find the latitude and longitude of the thing that you are looking for. And so the idea is, can we write a program that can read this? And so here's our little program that reads this. And a lot of this is sort of comfortable. You've already seen some of this. You import URL lib. We have to parse them JSON. We grab the URL. And then we're going to write a little while loop that's going to ask for a location. And we can type that location in. And we've got to concatenate with this URL the location equals. And there is a bit of code, a library that called parse URL encode that takes the key and the value, so the address equals, and then whatever this text is that we read in from the user, that goes in here, and it does that URL encoding with the pluses and the %2c and all that stuff is taken care of, and that is our URL that we're going to pass to URL open. So we print out that we're going to retrieve it, prints this out, and if you look at this, it's too long, it has all that fancy stuff on it, and then we read it. I mean, we open it with URL open, and then we read it and decode it. So these two things, hit this URL, decode it, and then we retrieved 1669 characters, because it's just in this case, because we've decoded it, data is a string now. That's read is bytes and data is a string. So we read that many characters, 1669 characters, and then we're going to take this data and we're going to parse it with JSON, and we might get bad data here. It might blow up, but it might work. And so in this case it works. We have an error that basically says if we got a bad thing, we're going to blow up, but in this case it doesn't blow up. And so now we're going to sort of dig through. And if you go back, let me just go back. So the results, sub-zero, geometry. Let's show you how that works. So results is the first key. So this is a dictionary with a key of results, but then it has a list, and the 0 item, this list starts here and goes there, and I'm only going to show part of it, but there's many things here. So the 0 item is this. This is the sub-zero. And then geometry within that sub-zero item. So if we look at that, it is the outer dictionary, the first item in the list, sub-geometry. So that grabs one part. That grabs this part right here. And then we're going to go into location and lat. And those are just keys within keys, a dictionary within a dictionary. And so you see it says sublocation, sublat. And so that is literally going to pull out of that complex structure, that will pull the latitude out, and then in the next line, pull the longitude out. So we can pull the latitude and longitude out, and then we print it out. We can go into results sub-zero formatted address, and that goes into results 0 formatted address, and that pulls this little bit out. Now it takes a little while to write this stuff, and you have to put a lot of debug, and you don't necessarily figure out this complex bit here at the end, but you know, you print it, you don't get what you want, you say, oh wait a sec, that was an array, so I got to add a little sub-zero there to get the first one out of the array, but eventually you figure it out, and it's not all that difficult. It's the first few times you do it, I'm like, what am I doing? But after a while you realize, oh, I'm just sort of tearing this apart and digging deeper and deeper into this data structure, which I just retrieved over the internet from Google, and I learned something good from that. So up next we're going to talk about how sometimes these APIs protect themselves with keys or signatures, and why that happens and how to solve those problems. We are doing some code samples here. If you want to follow along, you can download the sample code all in a big zip file. I've got it. We are going to be working with the Google Maps API. In the old days, this Maps API was free and did 2,500 requests per day, but now they've made it so that parts of it are behind API keys, and you start having using OAuth and stuff. But they haven't put it all behind this one address service that we've been using. That continues to work. And the basically idea of an API is you go read the documentation, you find a URL, and this is going to Google servers, and you pass in the address. And we have to pass in the address using what's called URL encoding. So spaces are pluses, that's a comma, and then that's a space. And so we have to pass this in a certain way, but if we do it right, we hit this, we're going to get ourselves some JSON back, and that's really cool. And so deep inside here we get the real address, you know, a good address, we get a geometry, you know, we have the location, we got the latitude and longitude, and we can extract stuff out of here. And so we're talking, and this one here is still rate limited to 2,500, but it's one of the few parts of the Google Maps API that is not hidden behind an API key. In a later chapter, we'll show you how to actually talk with the API key in the Geodata code. The geoload shows you how to use an API key if you want to jump ahead and take a look at that. But for now, we're just going to take a look at GeoJSON, which is going to retrieve one page and tear it apart. So let's take a look. So we're going to grab the URL lib stuff and import JSON. So now we're going to use JSON, but we're going to actually pull the data out of the internet. And so I just take that service URL for Google Maps API. I found that somewhere in the documentation. And then I'm going to have a loop that's going to run forever. I'm going to add the location. And then if I hit enter, that's what this is saying, get out of the loop. And then what I'm going to do is I'm going to concatenate the service URL, which is this, and this URL parse URL encode gives a dictionary of address equals, and this bit right here gives me the string that leads to putting this address equals, but then coding these spaces the right way. So if you type a space, that bit of code turns it into the plus. So that's important, and I've got the question mark sitting here at the end of that. Then what we're going to do is we're just going to do a URL open to get a handle. We're going to read the whole document, and because it's UTF-8 coming from the outside world and we want it turned into Unicode inside our application, we say .decode. We can ask how many characters we got, and we put our JSON load S. Now, up till now, we've been just doing load S's from internal strings, but this is now a string that came from the outside world, and we'll put a try except in, and we'll set JS to be none, and that'll be our little trigger. Now, we can look for, they give us, if we take a look at the output, they give us this OK, and that status can be a problem, and it can complain about things. So we have to check to see if we got a good status. So at this point, if you look at the outer bit of this, the outer bit that we get is a curly brace, so it's a dictionary. Then there is within that dictionary a key results, which is a list. But then the second thing in the outer dictionary is status. And so we can ask if if we got a false, if we got nothing, that we'll quit. If we don't have a status key in that the object or that dictionary, or it's not equal to OK, any number of those things, if this or this or this are all, either of those are true, we're going to quit. Failure to retrieve and print the data out. And when you're starting to read stuff off the net, you often have to put debugging in here like this, like, oh, something quit, I got to figure out, and so debugging it. Next thing we're going to do is called JSON dump S, which is the opposite of load S, which takes this array that include dictionary that includes arrays, and we're going to pretty print it with an indent of 4, and then we're going to print that out. And so if you look at my code, we'll see that the first thing we do once we parsed it is we print it back out so we can see it, and then we're going to dig into it. So let's go ahead and run this code. Python geojson.py. One of these days I will always type Python 3 and Arbor, Michigan. Okay, so it ran, and so you see that it retrieved this URL. This URL was constructed and retrieved 1736 characters, and it's JSON pretty printed with an indent of 4, and this is that JSON dump S all the way down to here. So that's just JSON dump S, and then it starts extracting. So it's going to pull things out. Now when you write this code, it's really easy to look at this and say, oh great, it's easy. I tend to have to print this stuff out over and over and over as I kind of construct this expression. But if we look at it, the outer dictionary sub-results leads to this array. And if you go look at this array carefully, you find there is only one thing in it. And so that the results is an array. Sub-0 gets us this dictionary. I keep wanting to say object because that's what it's called. And that goes all the way down to here. So that's what we get there. And then within that, we now have an object, and we look for geometry within that object. Where is geometry? Right there. Geometry. Geometry goes from there to there. There's geometry in there. You got to get used to it. That's why it's nice to have this stuff indented. Geometry sub low. Oops, come back. And then we go to location within that. So location within geometry. And then within location we have lat and long. And so this is pulling out this 42 and 83. And then, so we print that out. Take a look. And that prints that out. Pulls that right out of the JSON. These are tricky to write, but after a while you win and you get it right and it's just fine. Okay? And so we do the same thing result sub 0 formatted address gets us this. And so that's how we print the location out. And so that's a real quick look at how we would do that with the JSON talking to the Google Maps API. Okay, hope this helps. Now we're going to talk about API rate limiting and security. The key thing is that the Google API and the Google data is super valuable. And you could build a website that did nothing but sort of like asked the person for something and then showed them that place and make it be a map searcher. And you added so little value and Google did all the hard work. And so they protect these somewhat. Sometimes they'll say you can only do 50 of these a day or 500 a day or whatever. That's called rate limiting. And sometimes they say you've got to log in, you've got to create an account and get a key with us and then present your key. So that means that your account only gets so many. And they keep track of who's using their service and how much they're using it. Google gives you even sort of a dashboard that tells you some of this stuff. It's kind of nice. And so the other thing is that sometimes an API is free and then it becomes popular and they decide they're going to put a key on it or a rate limit on it. So you got to kind of play this game with them and the rules kind of change as things progress. So that geocoding API that we're talking about has at one point in time 2,500 requests a day. You can get more requests if you get a key. Now, another API that we can talk about is the Twitter API. Now, Twitter API started out as a free public API, but then Twitter realized that people were making more money off of Twitter's data than Twitter was making off of Twitter's data. And so Twitter makes it so that you have to have an account. You can only request data from their API is if you use your account key to sign that. And so there's a whole series of getting and issuing keys and then using those keys. And I'll just give you a short summary of the kind of code that it takes to build those requests up that have to be signed. So you'll look through the Twitter documentation and it'll say, oh, this URL to get the tweets, etc., etc. And it says do a GET request to this URL and that URL and maybe substitute a little bit of things here for the screen name you're looking for or how many tweets you want. And they tell you how to carefully construct these URLs. And so here's an example bit of code that talks to the Twitter. Now, for now, I'll ignore the security bit. That's all hidden in this TW URL. So it looks a lot like the last one. We're going to use JSON and URL lib. And we have found that this is the API name, blah, 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 list.json, getting a friend list for a particular person. And so that is the base URL that we're going to do. We're going to ask a person for a Twitter account. If we hit enter, we're going to break out. And TWURL augment, we're going to say, give me the first 5 friends of this particular screen name, the one we just read in from input. And this TWURL, you'll see in a second, it adds a bunch of stuff to prove that you are who you are. It's signing that URL. So you're sending a signed URL, which is nothing more than a whole bunch of crazy characters. We'll see that in a second. We retrieve it, and this is pretty straightforward. We can just, open the URL, read it, and decode it. Decode solves the UTF-8 thing, makes it all so that data is a real string and it's in Unicode internally. Now we can actually get the headers. Remember I told you earlier that URL open bypasses the headers, but it's stored them for later. And we can say, hey, give me back those headers. And that gives us back a dictionary of headers. And the headers, if you go all the way back, are a bunch of key value pairs. Key colon value in the headers. And in Twitter, if you read the documentation, there's this x-rate limit remaining that tells you each time it returns to the API, response to the API call that you made, it says, look, you've got 12 left, you've got 11 left, you've got 10. So you can print that out. So this prints out how many you've got left. Then we parse the JSON data. We're going to print it so we can debug it. This dump to string and then printed. Indent equals 4. This is called pretty printing. And it's indenting things really nicely so that you can make more sense of it. Whereas when these things are when programs are talking to each other, they don't really make the output look particularly pretty. And then if we're going to go through, we have the outer thing of users, and we're going to print out the screen name and go grab the for each user and users, we're going to print their screen name, we're going to grab their status text and print that out. And so this is what that data looks like, kind of chopped a bit. So the thing we get is an outer layer, we get users, and then we get a list. And here's the first user. Now if you look at the actual data, it's much larger than this. Here's a second user, and then we have status text, and the screen name, right? And so those are the bits that we're extracting from that. If you look, we're going to grab the screen name, we're going to grab the status text, and away you go. So you can start with this, but you realize that once you're looking at this and you're printing this out with Pretty Printing, you can sort of work your way in, knowing that it's either a dictionary or a list. If it's a dictionary, you look up the key. If it's a list, you say which position it is, and then you get more dictionaries within dictionaries within dictionaries, and away you go. And so this code actually, when it runs, it prints out the screen name and then that status and the next person. So it's my first 5, in that case, my first 5 friends and their most recent status, the first 5 people. Now, let's talk a little bit about how this security works. And so you have to go to the website. You have to have a Twitter account. You can't talk to Twitter API without a Twitter account. And then you go to this website and then you set up a key. You say, I'm going to build an application that is going to consume the Twitter API. And then you go in, you have to work through, there's documentation on how all this stuff works. You set up an API key, you set the application. So I made a key called Python on my laptop. And it gives us some values. It gives us a consumer key, a consumer secret, a token key, and a token secret. And you get to regenerate these. And there's this file called hidden.py, and you edit them and copy and paste all the stuff from those pages, those 4 values, into these strings. Now, if you download my code, I don't have my keys in there. I got some placeholders for this stuff. So you got to get to this web page that's on Twitter, copy these things in, and then the TWRL code will start to work. It uses a technology called OAuth, which is a way to sign a URL in a way that proves that you have the key and the secret and the tokens, but and it can't be modified in the middle. So once you send this URL, they can check the key and the secret to make sure that you truly signed it without actually sending the key and the secret. It's actually kind of cool and fascinating, but we won't go into it in great detail here. And so if you look at the code in twurl.py, this is the code that does it. It actually pulls in an OAuth library. That hidden.py, that is that code that you've got. And it's got the consumer key, the consumer secrets. This is pulling that from hidden.py. This is a lot of stuff that's using this OAuth library. Don't worry too much about that. Eventually it produces a URL that looks like this. And what happens is this was the base URL you were told to use. Then you have count equals 2 and screen name equals Dr. Chuck. Those parts are your parameters to that web service call. And then all this OAuth stuff is produced by this OAuth code and the consumer key and the secret. What happens is the key gets sent, and the secret does not get sent, but they send this signature, which is based on the secret. And then what it does is it rechecks the signature on the far end. Signature is a long string. By regenerating the signature, because the secret's available to both you to generate the signature and to them to check the signature. So it's kind of like a hash, etc., etc. You don't have to worry about all this. These URLs get really long, and your values that you need are in, the name of the URL is in, and you call this routine. It's called augment. That takes a URL and then parameters and then augments it by adding all this OAuth stuff. And so that's why it's called augment, to augment the URL. And once you got this set up and hidden working, then you sort of just augment the URL and then hit it. Now, if you don't have the right keys or secrets, or you don't have an account on Twitter, then it's going to blow up. But if you get it set up, you will be able to talk to the Twitter API with this. So this whole web services section, we've done quite a bit of stuff, right? We looked at how instead of reading HTML or flat text, we are creating structured data according to contracts, whether it be XML or JSON. We can retrieve and parse that information in a deterministic way. We talked about schemas that define the contracts so that you know if the data you're getting is wrong, you can know who to blame because the schema gets violated. And we've played with APIs where you're talking to someone else who's defining what the rules are and how to read their documentation. And even if they have an API key or need signed URLs, showed a little bit about how to do that. We're doing some code, sample code, playing through with some sample code samples. And you can get this by downloading it. I've got this whole thing downloaded, and I've got all the files here. And these are the files we're going to play with today. Today what we're going to do is talk about the Twitter API. And the one thing we got to learn about the Twitter API is we have to authorize ourselves. And so we have to make sure that we have a Twitter account, and then we get some keys. And so in this particular application, if you want to duplicate what I'm doing, you have to go to apps.twitter.com, click this Create New Application button, and then get some codes. Okay, and the codes show up as soon as you hit this button and then one more button, which I'm not going to do on screen. And so what happens is there are 4 codes that you've got to put in this file hidden.py. The consumer key, the consumer secret, the token key, and token secret. These are just messed up, so I'll show you how this works and blows up if first, and then I'll put my keys in here without showing you. But basically, this is a little file you got to edit, or these Twitter ones don't work. You'll see what happens. So the first one I'm going to do is to do the simplest one of all, and that is I call this thing Twitter test, and it just is going to go ask for the user timeline, and we can take a look at this, and we're going to take the URL, and we're going to augment the URL. This is the base. We found this looking at the Twitter API documentation. We're going to pass a parameter of screen name Dr. Chuck and a count of 2, so this is just a Python dictionary. And augment comes from this little bit of code called twurl. And this uses a bit of code called OAuth, which is built into Python as well. Right? Yeah, that's built into Python as well. And it augments the URL, and it takes the key, the secret, the token key, and does a thing and signs it, and then makes this big, long, ugly URL, which you will soon see, and does this. It's a signature of the URL. So we pass this data back and forth to Twitter with a signature, and then they recheck the signature, and it's a digital signature that knows that this URL came from a program that knows the key, secret, and token secret. And so this augment basically is something that I wrote. twurl augment is something I wrote to make it easier to add all these OAuth parameters. And you feed this code by putting your data into hidden.py. Lots of people get this to work, so don't worry. It's kind of cool when you finally get it to work. So let's take a look at what it does. Just know that this makes an awesome URL that does all the security. And we'll see one of those URLs. So ignore the certificate errors. This has to do with the fact that we're using HTTPS, and Python doesn't have enough certificates put into it by default for a lot of reasons, but our quick and dirty way is to turn them off. Thank you, Python, for reducing security by teaching us so that this is the best way to do it. That's a grumpy moment on my part. So what we're going to do is we're going to do a URL open. This bit here is to shut off the security checking for the SSL certificate. And then we're going to read all the data, and then we're going to print it out. And we're also going to ask the connection, this URL. Remember I told you a long time ago that URL lib eats the headers, but you can get them back. And now we're going to ask to get a dictionary of the headers back. And so we'll print those out. Okay, so this is really kind of just testing the body and the headers and printing them out sort of in as raw a way we can do. So let's go run this. Now this is going to fail the first time we do it because we haven't put the hidden variables in there. So if I say Python 3 twtest.py, it's going to run and blow up, and it's going to give you this 401 authorization required. That's a good sign because that means that you haven't yet updated your values in hidden.py. And so this is the URL. This is that augmented URL, and you can see the consumer key and the consumer secret and the OAuth token and whatever. Okay, so these tokens are like wrong. These aren't. Oops, Control C. They aren't real. And then, but you'll notice it doesn't the key and the secret and the token key, the token secret and the secret, and that's all actually encoded in this signature. It turns out that you need to have the key and the token, I mean the secret and the token secret to generate the signature. And where is the signature? Oh, there's the signature, right? There's the signature. And so this signature combined with the nonce, that you can only do this signature has a time and it includes all kinds of things. So even if you type this in, well, you'll see these go by, and it's not really breaking my security too much when you see these afterwards. So don't get all excited when you say, oh, you revealed your token and your key. Well, I can reveal my token and key, but I'm not going to reveal the secret. Okay, so this adds all this OAuth stuff, OAuth nonce, OAuth timestamp, and these timestamps and nonces are made it so that you can't replay my URL even if you see the exact URL. Once I hit it, then you can't hit it again, and so that's what the nonce does. So I'm going to close hidden.py here, and I'm going to update hidden.py in another window. Okay, so I just, in another window, I updated hidden.py. I'm not going to show you that, but now I'm going to run Python twtest.py, so twrl is going to read hidden, and now these keys and secrets are my real ones that I haven't shown you. So this should work. Fingers crossed. Yay, it worked. Okay, so it worked. So I'm calling Twitter. Here's the URL. Now don't worry, the token and the consumer key are not enough to break into my account, and neither is the signature because you can't replay this. In about 5 minutes, you can't replay this anymore, okay? So you can't generate the signature. I've done one, the signature includes the time and date, so you can't, trust me, go read up on OAuth, don't worry. I haven't really revealed anything. But, so the first thing we see is this. So we see, and we should put like the line of dashes here. This is the JSON. It ain't very pretty, it's not very pretty. Okay, and so that's the JSON from there to there. It's just what most APIs give us back. It's really dense JSON, right? And so this is a byte array. Remember how you have to do a .decode? I didn't do a .decode here. And so this is telling, and Python is telling us this is a byte array, which it's a raw set of bytes that came from the internet, which probably are UTF-8. And if I put a decode here, then it would decode. If I say .data.decode there, then it would be fine. But we don't care. This was just a dump. Do we get anything? And so then, here, let's do this. Print. I'll just make this code different. Ooh, put some equal signs here, a lot of equal signs, so we can easily see where the thing starts and stops. So we'll run that again. If you look at those URLs, so that was all of that stuff, and then this is the headers. And so the headers again are not pretty. We get the headers. It's a dictionary. You got cache control, no cache, comma. This is the string key value. You got to find your commas key value. But the one that's really interesting here is which one is it? X rate limit remaining, right there. X rate limit remaining. So that means that for this particular API, and this header tells me that I've got 898 calls left. And this is when I will get more calls, and yeah, so let's see, yeah. So watch. I'm going to do this again, and you will see that I can only do this 897 more times now. Run it. I can only do this 897. So I am being tracked at this point. I am being tracked by Twitter. Twitter knows that it's Dr. Chuck that's doing this, and Dr. Chuck has done 900, he's done 899, 897, and if I keep running this, eventually Twitter will tell me, you got to wait for a while. And that's because Twitter doesn't want me, under my Dr. Chuck account, pulling out like lots and lots of stuff out of Twitter and making my own website. Now, I do actually have my own Twitter website using some cool software, www.drchuck.com/Twitter. And this I have to run, and it rate limits and causes all kinds of, whatever. So, okay, so rate limit. So I'll save that. So that's tweet. This is just to test it, okay? Because I want to do something interesting. So we're not parsing the JSON that comes back. We're not doing anything tricky with this. And away we go. So let's take a look at some more code. I think I don't need this anymore. So now I am going to parse this. So most of this looks the same. I've got that same user timeline JSON. I'm going to ignore the SSL certificates. I'm going to write a loop. So I'm going to ask the Twitter, I'm going to print, I'm going to get a Twitter account and quit if it's a blank line or if I hit enter. I'm going to use the Twitter URL augment the same way. That's going to do all the signing using from hidden.py. I retrieve it, and I'm going to retrieve it ignoring the SSL errors, and then I'm going to decode it. This time I'm going to decode it so that I get a real Unicode string. And I'm going to print the first 250 characters of it. I'm going to grab the headers, and I'm going to print the remaining the rate limit. So this is sort of a very simple version of this. Same thing. It really is decoding the data and only printing the first 250 characters. So let's run that. Dr. Chuck. Boom. And it's got 896. So that's just a little simpler version of that with a little less brutal debugging. Okay, so now let's do something even more fun. Let's go to twitter2.py and tear it apart. And so, so again, we're going to look at my friends list or someone else, anybody's friends list. We're going to ask for the friends and ask for the screen name, ask for the first 5 friends, and then look at their statuses. Open it, decode it, get the headers, print the rate limit remaining. All this stuff is the same as in Twitter 1, but now we're going to parse the JavaScript. I'm not even putting this in a try and accept because, hey, I'm talking to Twitter. I'm going to guess that Twitter is going to give me the right stuff. You'll probably want to put a try and accept here. Then I'm going to do a debug print. I'm going to do a JSON pretty print. Let's make that be 2 so it looks a little better. And then, well, I'm going to run it. And then you're going to see how we have to parse this. And we're going to see that it's a list. So we're done with that. And now we're running twitter2.py. So I'm going to go to Dr. Chuck. And this is going to ask the question who Dr. Chuck's friends are. Okay, let's go to the top. So it hit this API. And it has the screen name Dr. Chuck count equals 5 and all this OAuth stuff. Again, this is not a security breach by showing you all of this because the signature, the secrets aren't there. Okay, so if we look at it, it's an outer object or dictionary, and then the outer has a users, which is a list. And then each user has some stuff in it. So this one's Stephanie Teasley. It's got her screen name. It's got some descriptions. Keep on going. It's got her status, her latest status. For my friend, her status. Her source, where she's at. I don't know, man, she's got a lot of stuff here. Okay, there we go. That was the first one. Okay, and then the next one that I'm following is live edu, etc. And so you'll see that this is an array. So that outer thing is an array of users. Now, JS here is a dictionary. So I can say for you in JS subusers, well, JS subusers is a list. So the first U is going to be this Stephanie Teasley U, and the second U is going to be live edu. So that's all it took to get through all that stuff and figure that out. And then I'm going to say, get me the screen name of my person. So let's go in here. So that's going to pull Stephanie Teasley, Steph Teasley out. Then I'm going to go find her status. Let's find her somewhere in here. use sub status subtext. Come on. Okay, there's substatus. Substatus is all this stuff. More. Right there. That's status. That's use substatus is that. And then use substatus subtext is this stuff. So it's going to extract this bit right here. Okay? And so use status text, and I print out the first 50 characters of the screen name status. And I do that for the first 5 because I told it I only wanted 5. And then, of course, I get to see the rate limit. So let's go down to the bottom. So all of this is the debug print of the JSON I got back. Here is the program starting to print. Here is the screen name of my first friend. And here's the first 50 characters of her most recent status. Here is the screen name of my, and these are in reverse order who I've been following. So I've been playing with this live coding stuff. So I'm following them. What? Key error status, that didn't work. Why not? Oh, that's because live coding TV somehow doesn't have a status. So most of these work, so now you'll get to see me fix something, and when you download it, it'll be fixed. And so it says key error status, so that means that I've got to do a thing that says if status not in you, print no status found. Continue. Since sometimes there's no statuses. Who would have thought? I did not know that. Yeah, so you. Okay, so let's run this again. Oh, did I get to see my remaining? Oh, actually, let me change the order of this. Let me put this down here. It'll be wrong from the slides, but it'll be prettier now. Let's put the headers after the dump of the data. Okay, so let's run it again. Did I save it? Yeah. Dr. Chuck, blah, whole bunch of stuff. So I got 13 remaining calls on this one. So it's not the same as the other one. I don't get to call this too many more times, so hopefully I'll get the debugging to work. Sort of. I got a bad space here. I go no, not status found, no status found, and I need to put 3 spaces there. No status found. I'll make an asterisk. So let's run it again. And see, I got 13 remaining. So it's important you write code that's aware of your remaining. That's why I make so obvious about that. Go retrieve all that. I got 12 remaining, but my code starts to look, oh, dang it, I have another space here. Hang on, got to fix that. I need yet another space. Hopefully, I can make this as pretty as I want it to work. Oh, wait a sec. I didn't even do Dr. Chuck. I did that wrong. Typed my name wrong. Okay, so now it works. Oh well. So now I have my most 5 recent friends are this Steph Deasley, Live Edu Official, Life Coding TV, Nancy Gilby, and Greggy Kruger. And so there are their statuses, and I tore all this JSON apart using twitter2.py. Of course, after fixing hidden.py, which I'm not going to show you because it actually contains my real consumer key and consumer secret. You're seeing the consumer key and the token key go by on each of these URLs, but what you're not seeing is these 2 things, which are the thing I'm protecting, so that it's not a problem. Okay, so I will send that up, but there you go. Welcome. I hope you found this useful. The code will be fixed when you take a look at it and download it here from samplecode.zip. Hello and welcome to Python Objects. I'm Charles Severance, and we're well on our way to getting through all this material in the Python. So this lecture is in a weird place. I even debated where to put it in the book. I don't really want to teach you how to write a lot of object-oriented programming, but we're going to start using objects, and I want to be able to use the terminology. And so as much as anything, this lecture is about terminology and understanding the words, things like methods and method signatures and variables and inheritance. And so think of this as a terminology lecture rather than a learn how to program or learn how to use this. It's not something you're going to figure out right away. And there'll come a time when you as a programmer really want to start using object-oriented programming. It's really a powerful and wonderful technique, but I think it's too early as a beginning programmer to really say, oh, let's write a bunch of objects. So just relax and enjoy and learn this material and think of it as sort of a theoretical thing rather than, you know, a how to program thing. And so part of this is we're going to start reading data structures, and I mean data on how to use all these libraries, etc. And we're going to see the word objects, right? And then we're going to start hearing them. And I want you to be able to read the Python documentation so that you understand what's going on. And so, you know, the word objects should make sense to you, even though you're not going to write a lot of object-oriented programming. And so page upon page upon page, database stuff, which we're going to talk about soon, is uses objects all over the place. And the beautiful soup uses objects. We've kind of been using them, and I've been waving my hands, and I use the word method without defining it. But now it's really time to define it and go to it. So I want to review from the very beginning what we think of as a program. So the classic program, my favorite little minimum program, is our little elevator floor converter, which converts from European elevator floors to United States elevator floors. And the key to this is that it's input, processing, and output. And this is a good way to model any program. And in that process, we've got variables, and we've got logic, we've got algorithms, we've got loops that we write, we've got all kinds of things. And we construct a series of steps to achieve some goal. In object-oriented, and frankly, you've been using object-oriented all along, the program has lots of objects, and we're sort of putting stuff into these objects, taking stuff out of one object and putting it into another object. And you've actually been doing this all along. As soon as you're looking at dictionaries and lists, you're doing objects. And so an object is quite a little thing. It's sort of its own little space inside of a program that contains code and data. And so we're working together. All these objects are now working together. It's a bit of self-contained code and data. And it is one way to take a very complex problem and make it easier by breaking it into separate things that can be engineered and developed separately. And so you've been using string objects, or maybe you'd use beautiful soup or something. These are powerful capabilities, and if you had to look at all of them, it's just, hey, here's a thing, use this object, it'll do these things for you, and there's lots of details inside of it. Just don't look at it. Don't worry about it. And so there's boundaries, that things that you can use, things that you can look at, and things that really you don't bother looking at. You go read the documentation and use it, and away it goes. But then someone had to write that, and so they built an object. So what we're going to do is look a little bit under the covers of what it takes to build some of these objects. And so if we think of this program that originally just sort of did processing, we can think of it as having some kind of an input, right, coming into our program. And we have a string object, a dictionary object, maybe eventually some objects like a database object or an object that we eventually define. And you can think of as we're receiving data, it comes in an object, which is a string object, where we start putting the strings in dictionaries and do whatever. We pull out a list of them. And so you can think of data as moving between these objects. And like I say, even strings in the first week, first lecture, first week, first everything, we were using objects, and we've been using them all along. And so you can think of every string and every dictionary as a little program all by itself that has a bit of code and a bit of data. And so a string has the data, which includes all the characters that make up the string, but then there is a method called upper that does uppercase, or rstrip that strips off the right, a white space from the right. And so it's like they're almost little programs that have inputs and outputs themselves, and we can make lots of them. And there's lots of cooperating objects that make up an application. And one of the nice things about the object-oriented pattern is that they form boundaries, and within the boundary, if you're inside the object, you can say, look, I'm going to build you a string object or a database object or a beautiful soup object, and I'm going to build this capability and I'm going to give it to you in the form of an interface, and I'm not really going to care how you use it. And so we have this sort of visibility wall where I'm going to make an object and I'm going to let you use it, and the maker of the object doesn't necessarily have to know every single thing about the use of that object. But so just like inside the object, they don't have to worry about what you're doing with the object outside of it. When you're outside the object, you don't have to worry about what's going on inside of it. We, as the user of the object, we talk to its interface and we get things from it and give things to it and use functionality within that object, but we don't have to look inside of this. We can just say, oh, it's a nice little magical thing. We read the documentation, we read a web page, and it told us to do this, this, and this, and away you go. And so it is sort of this isolation boundary that works both for the programmer who's writing the object and the programmer who's using the object. And so it's a very nice pattern, and so you'll see how we're going to build code and we're going to group it together, and then we're going to be using it sort of as a big blob of stuff. So some definitions in this space, words that I want you to understand. When we're going to create one of these things, one of these objects, instances, that has some data in it and some code in it, we have to be able to define the shape of this object. What code will each object have in it, and what data will each object have in it? And that's called a class. The key to a class, and this little picture that I've got up here in all these slides, is a key. The class is a template. It's not the thing itself. So it's a cookie cutter. It knows a lot about how cookies are made. And if you have cookie dough and you hit the thing, then you make as many cookies as you want. And so this nice little cookie picture is a great, mental model of how it works. The class is the template, and then the object are all of the cookies that are made from that template. But the template defines the shape and the nature of the class. So the code that we write is going of each of the objects. The code we write is the class code, and then later we say, oh, let's take that template and make ourselves an object or an instance. Now, as we're defining a class, we have two basic things that we put in the class, and there's a couple of different terminologies for this. One is method, which is code. It's like a function that lives inside of a class. Not a function that lives inside your program, but one that lives inside of a class. And so this is a scoping thing. A method is really just a function, but it lives inside the class. And then fields or attributes are data items that are in the class. And so they're variables that are defined in the class. You can define variables outside the class that you use in your program, and you've been doing that all along. But if you're saying, I'm going to build this capability, and it's going to have data inside of it and code inside of it, the code is the method or message, and field or attribute. And there are just two different sets of terminology. Method is what I'll probably use. If you look in some object-oriented patterns like Smalltalk or Apple, they often will call these messages. So you can either access a method inside of a class or an object, or you can send a message to the object. The same is true for field and attribute. It's just a chunk of data that's in the object that you may or may not have the right to access. So, like I said, a class is a template. It defines the characteristics of the objects that we're going to use to make it. It is the cookie cutter. So, dog is sort of the exemplar. Lassie is a particular dog, and so dog has fur, and dog barks, and dogs do all these things, and so we know something about dogs, but it doesn't mean we have a dog, right? The class is a more abstract concept that when it's time to get a dog, we know certain things about dogs. Instances, or objects, are once we say, oh, time to make a cookie from the template, time to get a dog, we know something about dogs. That's the creation of an object, and that we call them instances, instance of a class. So the class is it doesn't exist, but we say make me a new object using this class as its template. Oh, and now make me another one. And so we can have many, many objects from one class. So just like many cookies from one cookie cutter. Method is a bit of code that lives inside of an object. It's like a function, but it's scoped to within the object or within the class. Okay, so that kind of gets us started on some of the terminology, and we'll come back and we'll take a look at how we write code that's object-oriented. Okay, so now that we've gotten through the definitions, let's work into some sample code. But hey, look at this. We've got ourselves a cookie cutter and some cookies. So remember that a class is a template. It's not the actual thing. An object is an instance of a class. So you have to take the class and do something to make the object. And actually you can see here's some other classes. There's clearly a sort of a snowflake class and a gingerbread man class. That's an object, object, object. Somewhere out here there is a snowflake class and a gingerbread class. But we got a snowman object and a snowman object and a snowman class. So class is the template. Object is the instance. So here's a bit of Python code. So let's take a look at what we got here. Class is a new reserved word, kind of like def. We have the name of the class. That is a name that we choose. That's the name by which we'll refer to this class for the rest of this program. And it has a colon at the end of it, and which means it starts an indented block, which ends when we de-indent. Inside the class, there are generally two things. There is some data, and this just looks like an assignment statement in the class, x equals 0. And then there is a def. This looks just like a function, and then it starts with a def, has a colon, indents, so that function finishes right there. The difference is this is a method because it lives inside of a class. And so there is no function called party. There's a function called party within party animal class. And we'll talk in a second about this self thing. It is the way that inside this code we refer back to that variable. So this is not actually executing any code. It's sort of remembering the template, defining the class party animal. This is what we call constructing. We're constructing using the party animal template or class. We are making a party animal, and then once we make that, we stick it in the variable an, and then we're going to call this party animal, this party method 3 times, 1, 2, 3. Now this self thing, and we'll take a look at the self. The self ends up being an alias of an, and so you can look at this syntax. It's just kind of an equivalent of this syntax. It's calling the party method within the party animal class and passing the instance in as the first parameter. And so self ends up being an alias of an each time these are called. Now if we make a different variable and a second object, which we will eventually, you will see that works a little bit differently. And so this syntax is a short version of that syntax. So if we watch how this executes, it starts up here, it just defines it, and then we construct it. And that's what basically constructing it. We know how to construct it because we look at the class and we make a variable x, we make some code party, and then we construct that. That's what the party animal does, and then we assign that into an. And so an is now pointing at that. Then when we call the party method, that basically takes this an and passes it in as the first parameter, which is used as self. And so self.x, which is what we're doing in this line right here, self.x is a variable. X starts out as 0. X starts out as 0 because when it was constructed it was set to 0. So we're in here, an is an alias of self, and now it looks up self.x, which is 0, adds 1 to it, and so this becomes 1. And then we print so far 1. And then the code returns and it goes down and does it again. And x becomes 2. Prints out so far 2, comes back down, and does the last time, calls it again. Self.x is 2, add 1 to it and stick it back in, so this becomes 3, and we print out 3. And then the program finishes. And so you can think of this as constructing the object and then associating it with this an variable. Now that we've created this object, we can play around with things we've played around before with dir and type. We use dir and type to kind of inspect variables and types and objects. So we've been using objects all along. This code here says, hey, make me an empty list. Well, it turns out that what we're saying is there is already a list class inside of Python, and we're constructing an empty list, and when we get back this empty list, we're assigning that into X. So X, in a sense, contains or points to an empty list. So then we say, hey, what is in X? What kind of thing is X? Well, it's a list. This is a thing, it's a list type. Lists have list of things in them. And, use append and all the things we've been doing before, they're just objects. And then the dir, if you remember the dir is the capabilities. And there's all these internal capabilities that do things like implement the bracket operator, etc. Those double underscore ones, we can ignore them, although you can even look them up and figure out what they mean if you feel like it. But the methods that we tend to call are in this class. And so things like x.sort, I've always told you that is the sort method within the X thing, and the dot operator is the operator that we use to look something up within an object. And so you've been using this syntax all along. X.sort, dictionary.items, all of those are methods within the corresponding class. If we take a look at this line of code that we've been doing for a very long time, which says, oh, stick hello there into Y. If I reword that as more OO or object-oriented, what this single quote does says, make me a string object and put some text in it, and then when that is done being constructed, stick that into Y, right? And so Y now points to a string object that's been pre-initialized to the string hello there. Now that's a long way of saying hello there ends up in Y, but in OO terms we can talk about that. If we do a dir of that, we see a whole bunch of internal methods which have double underscores, and then we see all kinds of methods that we've been using. We've been using methods like upper, we've been using methods like find, we've been using methods like rstrip, right? We've been using these methods, so we go to like y.rstrip, parenthesis. Again, that's a method, that's an object, not a class, it's an object, and that is the object lookup operator. Now if we do the same thing to code that we've built, or a class that we've built, so now we have a party animal class. Remember, this up to here is just definition. Now we construct it and we store it in AN. So AN is a variable that contains an object of type party animal. We ask it what type it is, and it prints out here. It says this is a class, and it's main underscore party animal, and this whole thing here is the underscore main. It's scoped underscore main. But you can see that you have made a new type. You built a type by using this class keyword. And then we use the dir. Remember, dir looks for capabilities. And again, you will see a whole bunch of underscore things. They have meaning. You can look them up. But eventually, you'll see the two things that you've put in it. One is the method party, and the other is the attribute or field X. And again, these are the things that you can say an.x or an.party, because this dot is the object operator, the object lookup operator that says look up in the object an the thing X, or look up in the object an the thing party. Okay? So up next we'll talk a little bit about how objects are created and destroyed. We also call that object lifecycle. Now we're going to talk a little bit about object lifecycle. And what we mean by object lifecycle is the act of creating and destroying these objects. And I've been using this term constructor already. And so when we declare a variable, whether it's a string or a dictionary or a party animal, there we create them and then they're discarded, and there's all this dynamic memory that comes and goes. And we, as the writers of objects, have the ability to insert ourselves at the moment of object creation and at the moment of object destruction. And we make special functions that we call the constructor, the object constructor, or the class constructor, and the destructor. And we don't actually explicitly call them. They're called automatically by Python on our behalf. And so the constructor is much more commonly used. It's used to set up any initial values of variables if necessary, et cetera, et cetera. Destructors are, we'll cover them, but they're used very rarely. So here's a bit of code that we've got. It's our party animal, and a lot of it is the same as what we've been doing so far. So we have this variable x, and the constructor has a special name, underscore, underscore, init, underscore. Again, we pass in the instance of the object, self. And in this one, all we're going to do is print out that you're constructed. And here's this code that we've had before. And now we have underscore, underscore, del, and then we pass in self. And we'll just print out that we're being destructed and what the current value of x is for that particular instance. So let's go ahead and run this. And so again, this doesn't really do any code up to here. That just defines party animal, but this is the constructing of it. And basically that says, oh, and it really kind of creates these variables, and then it also runs the constructor. And so in this case, this line right here is causing the I am constructed message to come out. Then we do and party, and that says, 1 and 2. And here's an interesting thing. We're actually going to destroy this variable by throwing away an no longer points at that object. An is going to point to 42. So we're going to sort of overwrite an and put 42 in it. And at that point, Python's like, oh, this whole little object that I just created, somewhere it's out here, it's vaporizing it and throwing it away. And so before this line completes, it actually calls our destructor on our behalf. And so that message comes out. So we are allowed, as the builder of these objects, to add these little chunks of code that says, I want to be involved at the moment this object is created, and I want to be involved at the moment that this object is destroyed. Now, in this last line, an is no longer a party animal. An is now an integer. It's got a 42 in it. It's gone. It's been created, it was used, and then it was destroyed. Okay? So you got to be careful. If you overwrite something, you can sort of throw the object away. So the constructor is a special block of code that's called when the object is created to set the object up. So we can create lots of instances. Everything we've done so far is we make a class and then we create one instance, one object. And each of these objects ends up being stored in its own variable. We have a variable an and we've been using it. But the more interesting thing begins to happen when we have multiple instances of the same class sitting in different variables. And it has its own copy of the instance variables. So let's take a look at this. So this code here, I've taken out the destructor, and it shows a little bit more information. So now we're going to put two variables in here. We're going to have a current score or whatever, and a name. And we're going to start it out as blank. And this time we're going to add a parameter onto the constructor. And so the self comes in sort of automatically as the object is being constructed. But if we put a parameter on the constructor call, which is this party animal call, then this comes in as the z variable. And so self is the object itself, and z, this first parameter, is whatever parameter we put here. Everything we've done so far has no parameter here, but now we have a parameter here. And then that means that when we call this constructor, this line of code comes, and then name is no longer blank. Name is going to be Sally in this particular thing. And then I'll say, oh, self.name, which will be Sally, has been constructed. And so then we have this, and that object is now constructed, and then we put it in the variable s. And then we call the party method on that, and we construct a different one. And so this time it calls, and z is Jim, and we basically have a, another copy of this. And so this is how it's going to look, right? As it runs down here, when this is called, it makes one instance and stores that in the variable s. And there's a variable x in there, there's a name in there, there's an init method and party, and that's all in here, right? All that stuff is in here. And now we say, let's make, and that's going to have a Sally in there. All right, Sally in there. And then we're going to do another constructor, and so it's going to make a whole new thing, and it's going to store that in J, and this one's going to have Jim in it. S party, then this turns into a 1, and then we're going to call J party. That turns that into a 1, and then S party will cause this to be a 2. Okay, and so what happens is we have now two objects, one in the variable S and one in the variable J, and they have separate copies of their instance variables. These are the instance variables or the object fields or whatever, but they're the variables. But the key is that every time we do a new construction, it duplicates this, and there's another copy of it. So there's an x within s. So s.x is this variable, and j.x is that variable. Okay? So the next thing we'll talk about is inheritance, and that's the idea of taking one class and extending it to make something new. So the last topic we'll talk about here in object orientation is the notion of inheritance. And this is a form of code reuse, and it's one of the more advanced aspects of object-oriented programming. So just kind of understand what it is at a high level, and then you know where to come back to when you need to learn a bit more about inheritance. So the idea is, instead of making a new class from scratch, we actually make a new class by starting with an existing class. We are extending it, or another word for this is subclassing. And it's sort of a situation where you're like, I've got this code and I've got this data, and I just need to add a few things to it, and then I'll have a whole new thing. And as you design objects and what we call object hierarchies, you often do this, and it's a form of sort of real clever code reuse. But again, don't necessarily think that you're supposed to know when to use this or why to use this. Right now, it's just terminology, okay? Just terminology. We have what call these as parent-child relationships. The original class is called a parent, and the new class is called the child class. So subclasses are another word for this. You have a class and then you subclass it. I think extending, inheriting, and parent-child are probably better ways of expressing it than subclassing. So here's a bit of code. Let's take a look at this. This code's unchanged. It's the party animal code that we've been saying all along. It's the one that we construct and put a name in. And now what we're going to do is extend it. And so you'll notice that this code down here is the part that's doing the extending. So we're making a new class, football fan, and by putting in parentheses before the colon, party animal, that says football fan inherits everything that is party animal, meaning the X, the name, the init, the party, all those methods and data are sitting there. And now we're going to add a new variable. So football fan has, in addition to all those other variables, it has points, and it has a touchdown method. And, you know, self points is added, you know, we add 7 of the points, and then we call the party, and that does that. So this is calling this method because football fan includes X, name, and party, and init, and everything, and all this stuff, this constructor. So this football fan is really an amalgamation of all these things together. Party animal is just this stuff, right? And so we still have 2 classes. We don't just have one. We didn't erase the party animal class. And so if we take a look at the code that we can run here, we can say, oh, okay, let's make a party animal, Sally, and so that constructs an object like this and then stores that in S, and with an X starting out at 0, and then we call S party. Oops, better change that color. Starts out at 0, and then we call the party method, and that changes it to 1. Okay, and so this bit of code, it's as if this part doesn't matter at all because it is a party animal, it's not a football fan. But now if we take a look at this code down here, take this code down here, we're going to construct a football fan and pass in Jim. But football fan has no underscore init, so that actually uses the underscore init from party animal because we extended party animal to make football fan. So we inherited all of the good that was in there. So there it's going to make a name, a variable X, which is going to start at 0, a variable name that's going to have Jim in it, and a variable points that's going to have a 0 in it. So this J variable has more things in it than the S variable has. And so we can call the J party, and if we call J party, that goes here and adds 1 to X, right? So that adds 1 to X, and then we call J touchdown. Well, that comes down in here and adds 7 to the points, right? And then calls party within us. And so self.party is the current object, i.e. self and J are the same thing, right? Self.party, and then it goes up here and passes self in, and it adds 1 to the X, in this case of this J variable. So this becomes 2. And that's where it prints out, you know, 7 and 2, and away you go. And so it's a way for you to kind of take all this stuff and stuff it into a class by making a new class and just add the extending bits, the bits that are in addition to the other stuff. So like I said, inheritance is a powerful and wonderful concept. It's a form of, excellent form of reuse, but basically the whole purpose of this lecture was so that I could in the future just use these words and you would understand them, as compared to, I just want to say method. And I've been saying method all along, and it's high time that I defined it. So let's just review one last time. Class is a template. It is not actually a thing, it is a shape of a thing. And we define it and say when we make one of these things, it's going to have these variables in it, it's going to have these methods in it. Attributes, variables within a class. Method is a function that's inside of a class. Object is once we construct a class, we get back an object. And so object here is the snowman cookies. Class is the snowman cookie cutter. And a constructor is a bit of code that sets up our object, our instance, when it first is created. And inheritance is this ability to create a new class, but take all and import and affect all the capabilities of an existing class. So, object-oriented is awesome. For the rest of this class, we're not going to write any object code, we're not going to use class at all, but we are going to use objects. And literally, you've been using objects from the beginning of this course. As soon as you said print, whoops, as soon as you said, you know, x equals high, that's an object. And as soon as you said x.upper, you were calling a method, right? You've been calling a method all along. When you're doing something like fh equals open, this thing you're getting back, that's an object. And then you do fh.read or whatever. You're calling a method in the dot operator. So you've been using objects all along. I now am just finally explaining to you when I say call the read method or call the upper method or what's this little dot and why is that there? So again, it's time for us to understand that, but it will take you a long time before you encounter a problem that's large enough where as part of your solution, you're going to make a new object. But when you do, it's really a powerful thing. I mean, it's a really bad idea for me as a teacher to say, oh, write a bunch of objects. It's like, it's premature for that. It's later is when you will actually learn how to use objects and you'll be like, oh, thank heaven that these objects are here. Okay? So, that's all for now. Thanks for listening. See you on the net. Hello, and welcome to our chapter on databases. We're going to learn a lot in this chapter, learn a whole new programming language, SQL, and learn how to use that. So you're going to need a new piece of software to run all of the exercises that I'm going to do called SQLite browser. We're using a database called SQLite. Go ahead and download this. You might have to pause and come back if you like. Go to sqlitebrowser.org and download it and install it. While you're doing that, we'll talk a little bit about the history. So in the old days, 1960s, 1970s, I started doing computing in 1975. We didn't have a lot of storage. I mean, this is, 16 gigabytes right here, and, we didn't even have megabytes. I mean, the computer I had a few megabytes of stuff. So we didn't have a lot of disk drives, and so permanent storage was often sequential. And these tape drives that we had, tapes and tape drives were the scalable part of storage because you could just make more tapes and you could rack them up, and so that was our way of greatly increasing the storage of the computer. The problem they had is they were sequential. You read it, it advances, read it, advance, read and advance. Now, interestingly, we've been writing programs that do this, that everything we've written so far pretty much reads the whole file, reads the whole web page, reads this, everything we read it either a loop or read the whole thing. And that's because we have plenty of memory, but we're still reading sequentially. And so the way you would do this when you didn't have enough spinning storage or online storage is you'd use offline storage, but the trick would be that you would sort it. So let's imagine that you're a bank and you have a bunch of accounts, only a few of which are active on any day, and you have a tape that has, in account number order from low to high, the prior balance, last night's balance of every one of your bank accounts, and then you do all the transactions and you record how much money was taken in or out for each account number, and then you sort those transactions. And then what you do is what we call a sequential master update, and that is you would write a program that would read the first transaction and hold on to it. Say, okay, this is count 45. Then it would read the first count, like 1, and it would copy 1, and then it'd read 2, and read like 7, 8, 42, 43, then it would read like 44, and then it would read 45, but it would change that and write the new 45, and read the next thing, and so this might be 60. And it would read a bunch of stuff and copy a bunch of stuff, and then it would finally get to 60, and it would merge the add or subtract, and so the old balance ended up here, and the new balance did here, and you had to only make one pass through the data, so it was super efficient. So we had all these mechanisms to sort. We used to do punch cards and have sorters and all these things, and then these things would run for hours. And if you watch old TV shows, these tapes are spinning and these things are running back and forth. These are simply reading and writing tapes, and that's how we did a lot of data processing, because we could store far more on a tape drive than we could on a disk. And with racks of tape drives, we could scale the storage that our computers had. And so that's the way we did data processing, but it meant that the only way you knew what the old balance was it was the balance as of this morning before your bank started. You don't know what the balance was for the day, and that led to things like you can never you can never withdraw more than $100 a day or something like that, because you don't know what the old balance was, or you might go withdraw $100 at a couple of different branches, and so they weren't able to look your stuff up right away. Now, it didn't take long until the disk drives got better and better and better, and you could store the entire accounts, all the accounts and their current balances on computers. And then the problem becomes is what happens if sort of in the middle of the afternoon you want to update a balance? Well, do you want to read all your data and then write a brand new one? And say that takes like 10 minutes. That means for that 10 minutes, only one person can be updating their bank balance. And so because we could randomly access this data, we didn't have to read it all sequentially. The trick is how do you spread the data out, and then how do you make it so you can change a balance? This is of course second nature today, but how do you make it so you change the balance here without changing the balance there, and you can have multiple people going simultaneously to these things, and make sure that you can't say to withdraw money at 2 different locations simultaneously and somehow have your bank balance get corrupted by that. So there's a lot of debate on how to do that, and in early days we just did sequential master update, but increasingly we wanted to make better use of the random nature of our computers and our storage, and so that's what led to databases. Databases are the science of how you make use of rotating random access data, permanent data, in a way that allows you to read, modify, and update that simultaneously from many different locations and yet keep the data completely consistent. And so this led to a study of a thing called relational databases. And relational databases are not the only databases that happened. We had many other kinds of databases, and there was a debate. And I remember in the 70s and the 80s, there was folks that says, oh, no, there you could do index sequential. That's the way to do it. And relational databases weren't all that popular the first time that I saw them. I didn't like relational databases. But relational databases had an inherent advantage because they were based on some really powerful mathematics. And the interesting thing is early on, the relational databases were slower, but eventually they figured out how to sort of bring all the cleverness to bear to make relational databases fast. And so relational databases are a pretty advanced technology, and there are companies like Oracle that are very, very wealthy, and their primary product for many, many years was nothing more than a clever database product, a clever piece of software that was really good at solving this problem. And that's how important this problem was to computing. If you read about databases, you're going to see 2 sets of terminology. One set of terminology comes from the mathematical background and has to do with the underlying math. Things like relations, tuples, and attributes. That's kind of like the fancy math version of it, and programmers kind of think of them as rows and columns inside of a table. And so if you look at sort of fancy theory, you'll see words that look like this, and they're just full of this and the connection. Now, all this is important and true, and if you really want to get good, you sort of begin to understand the nature that we modeled data at connections rather than at sort of intersection points, rather than just modeling data as a flat file the way we do. But for now, we're going to, as programmers, think of this as just like, oh, it's like a super fast spreadsheet. The super fast part is the math. For us, the rows, columns, and tables are spreadsheets. So think in a spreadsheet of sheets, sheet, and that's like a table, a named thing like tracks or albums, artists or genres. And then there is rows, and each row has a different kind of data. And then there's columns, and we sort of specialize the first column in many spreadsheets to say what's in there. This is not really the data. This is like metadata. It's like the title's in this first column. That's not really the data, and the data starts here. And we have different kinds of data like strings and numbers, etc., for each of the rows. And literally, you can get away with this as sort of about 80% of databases is just a really super cool spreadsheet. But under the covers, it is far more powerful than that. So one of the early arguments that happened was, again, what the programming model for this was. And a lot of folks wanted a programming model that reflected how the data was actually stored. The notion of structured query language came about in a way to express what you wanted to happen and allow that to be sort of a very abstract expression. Select all records that meet this criteria, not read. And so structured query language is not a procedural language. It is a imperative language where you're simply saying what you want, and then somebody writes the loop. The database actually does the loop, but it's a way for you to avoid actually writing the loop. Now that turns out to be the power of databases, because the cleverness in how to write the loop is a way that you would probably never figure out how to be most supremely optimal when it comes to writing the loop, as you'll see toward the end of joining many tables together and selecting and throwing array and getting down to a count or whatever. Someone has figured out how to do that really, really well. So the idea was you would express, we're going to create some data, we're going to retrieve some data, we're going to insert and delete it. Create, read, CRUD, C-R-U-D. Create, read, update, and delete, CRUD. And so that's what this does. It's a language that does this very simply. Now the applications that we're going to use this for are more of a data analysis application. We've been doing data analysis through the whole course. And the kinds of things that we'll see in the remaining chapters is we'll take some raw data file. These might actually come across the network, and we'll write some Python programs to play with that data, parse it, clean it up, make sense of it, and then write it into a database. And this might be a slow process, or this might be really nasty, and this might be a way to have very clean data. And then we'll write another Python program to sort of read through it, and it's all efficient and pretty. And then we can produce files, and maybe we'll visualize it or do further analysis in R, Excel, or a JavaScript visualization framework. And so in this situation, you will be the person who is both sort of writing the programs, database administrator, and you can, using SQLite browser, play and look at the database kind of in a raw way. And the first part of this, we are mostly going to be using SQLite browser just to talk straight to a database. Later, we'll write Python programs that read and write data and visualize the data. So this is what we're going to do first, and then second, we're going to do this part right here. That's the second thing we're going to do. Now, another really common use of applications, and something that if you continue learning more about programming, is that you will want to write an online application like Amazon or a company or Twitter that's got a website and it stores dynamic data in databases. And so the picture for that is similar but different than the picture we're going to start out with. And so the way this usually works is that you, the end user, uses a web browser, talks to the application, and the developer writes the application software, and that application software stores its data in a database. And inside that database, we talk to the database using SQL, and all the data is actually stored here, and the magic happens. The data server is that database software that's so precious and valuable. And then there's another person, often called the database administrator, who has direct access to the data. And these roles in medium and large projects are kept separate, mostly because the production while it's running and live, the developer leaves the data alone and works on, say, the next version of the software. And then the developer has a test version of the application that they run on their computer where they're doing all that stuff. And so this database administrator is a role in a large project where we have to run production and keep production careful, keep production in good shape. So the database administrator has this responsibility for the production aspects of the data, and you may be working in a situation where you're not actually controlling the data. The database server is on different computers, you have a little special access, and you write programs to sort of read the data. And so the database administrator is the person who is asked by the organization to administer that data. The data that we develop, and we'll do this in the second part of these lectures, conforms to a data model. That's the metadata. Is this an integer? Is this a string? You know, how many columns is this? And the data model turns out to be very, very important. And there's a lot of science to building an effective data model that leads to really good performance. And it's a collaborative activity between the application developers and the database administrator to make it so it's efficient, runs in production, etc., etc., etc. There's a lot of products out there that you may encounter. We're going to be using SQLite. SQLite's a little tiny database server, and it's built into so many things, and that's why we like it. But if you're going to work at a large organization, you could easily run into Oracle, which is the #1 commercial product. Microsoft has a thing called SQL Server, which is a commercial product, and it's also very popular and very effective. The more popular open source, there's things called Postgres, there's MySQL, and MySQL recently was sort of bought by Oracle, and there is a copy of that called MariaDB that doesn't belong to Oracle, MariaDB. And so most of the SQL that we're going to learn is common across these database systems because SQL is a standard, but then there are parts that weren't part of the original standard where each database vendor has done things a little bit different, but there is a core common subset that does the basic create, read, update, and delete operations. So SQLite is very popular. You probably have it in your cell phone 10, 12 times. Your web browser has a database engine in it. Your car has a few databases in it. And so SQLite is what's called an embedded database system. Python comes built in with it. You just import SQLite 3 and away you go. And so it's a very, very popular because it's free, it's open source, and it's such a tiny little piece of software that you just include it in other pieces of software and use it to solve the data management problems of those pieces of software. Like your browser might use SQLite to store your bookmarks. Now you think, oh, there's only how many bookmarks can you have? But what if you need it to be fast? And what if there's like people that have 10,000 bookmarks? There probably are. Do you still want it fast? Do you want to be able to search? And so you get all that by using a database like SQLite. And so again, we're going to encourage you to download the SQLite browser so you can follow along with what we're going to do coming up next. And so here is the SQLite browser. Here's what it looks like. And it's just a desktop application. And coming up next, we'll start playing with this desktop application and see how it works. So now we're going to make a database. We're going to use SQLite browser. Hopefully you've downloaded it so you can follow along. And I've got this handout, this basic database handout that saves you from having to type all these things. So bring that up in your web browser. And so that gives you all of the commands that I'm going to type now. And so you could pull them out of the either the web page, you can pull them out of the slides, or you can pull them out of that. So I'm going to bring up the database browser here. Database browser. Now the thing that's going to happen, you'll see this happen on my desktop. I'm going to make a new database, and you have to store it somewhere. And so I'm going to put it on my desktop, and I'm going to call it py4e fun. And so we should see a new file on my database right there, py4e fun. Now that's a file that you don't want to edit with a text editor or anything like that. This is a database that this is a file that's to be read by SQLite browser and nothing else. Okay, so we're going to create a table, and I'm going to make a table called users with a column called name that's a text and a column called email. So it's already asking me to make a table. I'm going to call this users, and I'm going to add a field that is called name, and I'm going to add a text, and I'm going to add another field called email, and I'm going to make that be text. Now the key thing here is we are in effect making columns and rendering an opinion as to exactly what that column is supposed to be used for, and we're not allowed to violate that. It's not like, oh, we'll do whatever you want, because the database is optimizing its storage based on a contract that we're effectively making the contract ourselves. We could make these columns anything we wanted, but we're just going to, we're going to contract with ourselves. And you can see it's kind of small here. You can see there's a create table, and that's on the slide. And that's the SQL way of doing that. This user interface is just helping us write SQL. So now I'm going to just say OK. And if you take a look, you can see that I now have a table users. And I can look at my database structure, the table users, and away we go. And so now that is creating it. And like I said, here in the slides is the create statement, or on the web page, there's the create statement that could have done it. Now, we can insert some data. Let's add a new record to this database users. And we'll call this guy name Charles C7 at umich.edu. So now we have a record. So it's kind of like a database, a spreadsheet. Now, that's not the SQL way to do it. There's SQL sort of going on in the background. But if we really want to do this using SQL, we're going to use the insert statement. And the insert statement looks like this. The SQL syntax sometimes has extra words. Insert into is actually two SQL keywords. The name of a table, the columns, and then the word values, and then one-to-one correspondence between the values and in parentheses. So it looks kind of like a tuple in Python, but we're nowhere near Python right now. Okay, and so that's what we're going to do. And so I'm going to grab this Kristen, and I'm going to go over here to my SQLite browser and say execute SQL. So now I can say paste that in, and then hit this little run button. And that's going to submit the SQL to SQLite and then update that file. And it says query executed successfully, and away we go. So if I go back now and I look at the data, I see that there's two things in here. And now I can actually insert all the rest of these. Let's go back to my little bit of stuff here. Let's put all these other rows in. It turns out that if I go into the execute SQL and I want to do more than one command at a time, I can put a semicolon at the end of each one of these things, and then I can run them all all at the same time. I mean, one after another actually is what's going on here. So boom, 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 and now I take a look at the data, and look, I've got all those things in there. Now, eventually, the thing that's going to generate that SQL is a program, not us. We're being the database administrator, so we're sort of doing things manually. Once things get going, you write programs, do that insert over and over and over again in Python or a web language like PHP or something like that. And so that is the insert. Now we can get rid of data. And so I'm going to say delete from, that's the keyword, users is the name of a table, where is a where clause. We'll have lots of where clauses in SQL, which is, it's not like an if, in effect the delete is going towards the whole table and being turned on and off by this where clause. So delete from users, if you didn't put the where clause on, will actually delete all the rows. But where ted equals, email equals ted at umich.edu, well, that one is going to make it so it only applies to the rows where that is true. So I'm going to go over here in SQL, and I'm going to say delete from users where email equals ted at umich.edu, and then I'm going to run it. Because it's only one, I don't need a semicolon at the end of it. And now if I go back and I look at the data, ted is gone. Okay? Update. So the update says updates keyword, users is the name of the table, set is a keyword, and then this is column equals new value, and then a where clause. Again, this update, if we didn't have a where clause, would change every row in the table. And so where email equals csev at umich.edu. Oh, I got to change that because I already got the name to be Charles. So you see the name is already Charles. So I'll just execute here. Make this be Chuck so we see it. And then I run it. And then you take a look at the data and it's changed. That's it. That's an update statement. You're doing great. You're doing great. And so the next thing we're going to do is we're going to take a look at how we retrieve data. Now this is the select statement. Select star. You have a list of columns, and star means all columns. From is a keyword, and then the name of a table. So this select star from users is the kind of thing you type all the time. As a matter of fact, it's what SQLite browser is doing internally to cause this to happen, but we can do it by hand by saying select star from users and then run it. And so then we get a little record set that is those 4 records that are sitting there. We can also throw a where clause on the end of it. So we say select star from users where email equals csev@umich.edu, and that, again, the select star from users goes at the whole table, and the where clause goes at the whole table and then filters out all of the things except one record. So the where clause is send it to the table, but then filter based on whatever, and so it only shows us that. Okay, we're cruising right along here. You can also put an order by clause on there. So we can say select star from users, order by email, so that's a column. Select star from users, order by email, and so that orders by email. Or we can change it to name, and we can say descending. So that's the name in descending order. Sorting and selecting are good things that databases are really good at. So this is the summary of what I've told you. I said the databases do create, read, update, and delete, CRUD. And we've done all those things, except we did create, delete, update, read. That's what we did. And that's the summary of SQL. And so you might be saying, why did I take so long to learn such a simple and elegant and beautiful language? Because it's not really exciting. It's a extremely simple language that's very predictable, and you're like, well, that's pretty easy. And it turns out that some of you may have been using SQL in situations, maybe with Microsoft Access or something, where you're actually typing this stuff and you just kind of typed it and you never realized that you were learning a programming language. That's why I like SQL, and that's a very declarative language, and it's very straightforward. It's much harder to learn. It's much easier to learn SQL than it is to learn Python, because in Python you have to figure out how loops work and how iteration variables work, and you'll notice there's none of that. And so but the key is we've only started to understand the power. That's the simple ability to move around and update data and read data randomly using these simple sets of commands. But up next, we're going to look at how you do this with data models and relationships and really multiple tables. Hello and welcome to a code walkthrough. In this bit of code we're talking about the emaildb.py. This is a beautiful little example in that it sort of reduces talking to the database to kind of its pure essence. And so we'll start out this code and we import the SQLite 3 just to get the library there. We make a connection, and in databases we sort of end up with an open that's 2 steps. There's the connection to the database, which checks access to the file, and the cursor is kind of like our handle. It's not as simple as you just open it and read it, but you open it and then you send SQL commands through the cursor, and then you get your responses through that same cursor. So CUR here is the variable that we're interested in. And the first thing that we're going to do is we're going to we've got this file. It will either create this file, and right now this file doesn't exist. It's going to be in the same directory. Oops, email. Yeah, there's no email DB. So this is actually going to create the file when it runs. And then the first thing we're going to do is drop the table if it exists. Drop table is a bit of SQL. The if exists just keeps this from blowing up if we start with a fresh database. And in this case, there is no file there, so we are starting with a fresh database. So this will accomplish absolutely nothing, which is just fine. Now we're using triple quotes here. I'm just kind of using that to make this a little bit easier to read. I probably could pull those lines up a bit. This one's actually small enough that I could Maybe I'll just do that. Let's do that. Let's bring that baby right up and turn this into a single quote. That's short enough, right? But triple quote is just, this one here is a little longer, so I use triple quote. So we're going to drop table. That's going to do nothing first time through. Then we're going to do a create table. Now sometimes your application will have like a README or something. It says go run these commands to set the database up, but we're able to just set this database up in this particular application. We'll see later ones where we're going to leave the database and not start it fresh. And in this one, we can do the same. And so, but this one, in this one, we could, but we're just going to start fresh by dropping the table. So we'll create it. We're going to have a email and an account. We're going to, basically what we're doing here is we're really going to pretend that this is a dictionary. If you recall when I said dictionary, dictionary is like an in-memory database. Well, now we're using a database to do a database, but the first thing we're going to do here is pretend it's a dictionary. So that's a little crazy. So these next lines of code hopefully are pretty familiar to you, right? Get a file name, loop through it, check to see if it's grab inbox short by default, so we can press the enter key and then loop through it, right? And so this little part right here, this is our basic loop that we're doing, and so that is pretty normal. And if we look at this line right here, that line right there is the line that is that line right there makes sure that we can only get the from lines. We've done that a bunch of times, and we're going to split it. We're not going to strip the right because the split's going to take care of that. And then we're going to grab the email address, which of course in the from line is the second part, and then we will have that. So now we're going to do some database. So the first thing we're going to do, this bit right here is kind of like the dictionary part. So the first thing that we're going to do is we're going to select count from our database, that is an integer, where email equals. And this part right here bears some explaining. This is going to be c7@umich.edu or whatever. Now, it is dangerous to put those strings, especially from user entered data, into your SQL. You technically could. I could make this be a email equals single quote c7@umich.edu. I'd have to escape the quotes and stuff. But this question mark is a placeholder. And this is a way to basically make sure that we don't allow SQL injection. Go Google SQL injection to get a sense of what that is. It's more of an issue in online applications, but in this application we're just being good. And so the way this works is this is a placeholder in this SQL that will ultimately be replaced by this. Now you could have several question marks. We only have one in here. And so you give a tuple. And if we just put email, it won't turn into a tuple. This is a one tuple basically. This little weird parenthesis email, comma, parenthesis, that is a tuple with only one thing in it, and that's just the weird Python syntax. It's rare that I apologize for Python syntax, but that's a little bit less than pretty, but it's okay, it's a tuple. And normally if there were like two of these, then there would be email, name, okay? So this cur.execute is actually not really retrieving the data. In a way, it's looking at the SQL and making sure that maybe it might verify that the table name is right, or if there's any syntax errors, etc., etc. So this actually is not really reading the data. So, but we have prepared this cursor. This is kind of like the opening of a file, but what we're opening is a record set. We're opening a set of records that are going to, be this wherever it's true. So it's like we're going to read this like a file. Now later things will loop through this, but we're only going to say, hey, grab that first one, right? We could have even put maybe a limit clause on there or something. Grab the first one and give it back in row. And so row is going to be the information that we get from the database. And so that is, if there are no records that meet this, then row is going to be none. So here's kind of, again, like the get. Here's like the get, where if the row wasn't there, because the way we're doing this is we're going to end up with this row in the database. Here's this database, and there's going to be two columns, and there's a bunch of rows. And then here's going to be CSEV 4 and Jen 3 and Stephen 6, right? So these are the counts. And so we're grabbing this variable out, if it's CSEV that we're grabbing, and that's going to come into here, right? That's going to show up in here. And that row is actually, it turns out that the row is a list, but we're only getting one thing. And what we really are doing is if we search through and we got through and there was nothing, then row is none means that there was no, and we're seeing like Chen's for the first time, and we have to insert it. So if row is none, we're going to run an insert statement, insert into counts, email count. Now we've got to set it to 1 because it's the first time we've seen it. So values, and then again the question mark. The question mark basically says, hey, I'm going to have a value in this tuple, and there's an ordering to the tuple, and so there's only one question here, one question mark placeholder here, and then 1 is the initial count. So email question mark count 1, away we go. And so then we have, again, we have a tuple that gives to this execute statement, just like in that execute statement, the corresponding sort of strings or integers that are to be replaced by each of the questions. So when this runs, there's going to be a new record, and there's going to be a 1 that's put in there into that new record. If, on the other hand, we pull back a row that exists, we're going to get this 4 number. And you might think we want to take this 4 number and add it, but in databases, it's always better to do an update because there might be multiple applications that are talking to this database at the same time. So no matter what update does is in a single atomic operation, it turns whatever this number is into 1 higher, and we don't have to worry about other pieces of code potentially modifying it. Now in this case, we don't have to worry about that because we're the only piece of code, but using update to increment something is way better than reading the value and then doing an update to adding 1 inside of Python and then updating the new value, that's 2 SQL statements, but it's also not atomic, okay? So if the row is none, if the row exists, we just know that it exists, and we just want to add 1 to the number. We do have the number sitting here in the row variable, but we don't need it. And so we're going to say update counts, set count equals count plus 1, column name, where email equals, and then another placeholder, and then another tuple for the question mark, okay? And so that's what this little bit of code does. That is kind of the read it, parse it, check to see if it's there. If it's not, insert it. If it is, update it. And so then we see this con commit. And this con commit, basically the way it works is that the database is efficiently keeping some of the information in memory, and at some point it has to write all that stuff out to disk. So you can choose at times where you put this commit. Right now we're going to commit every time through this loop, but you might commit every 10th time through the loop because the commit will take some time because it forces everything to be written to disk, and these can run really fast, and the commit is the slowest part here. So sometimes we do things like commit every 10th record or every 100th record. If it's an online system, which is not what this is, you have to commit at the end of every sort of screen paint. But for this kind of a system, because we're putting so much in, this is kind of a bulk insert, we might come up with a thing where we, every 10th time we do a commit. But ultimately what this will do when this is running is it will build up slowly but surely, adding new records, and then 1, 1, and then it'll be a 2 and a 3 and all these things, and add another one, that'll be 1. It'll do this thing, right? And then at the end of the day, that is what's going to be in the database. Now, so let's take a look what's in the database, and now we can actually read the database. And so in the database, we're going to run a select, and we're going to select the email and the count from counts, order by count, descending. So look at that, isn't that cool? We're getting in the top 10 because databases are good at sorting and they're good at all these other things. So we're going to then execute this, and then we're going to ask for the rows one at a time, and the rows are going to be a tuple, and row sub 0 will be email and row sub 1 will be count. So we run all this stuff, and then we close the connection, and away we go. Okay, so let's go ahead and run this. Let's go ahead and run all this stuff. Python 3 emaildb.py. It asks for a file name, mbox short. Well, I can hit enter, right? Mbox short, and that's it. And it looks just like that, and it counts it, and away we go. Now the difference is, at this point, we have a file, emaildb.sqlite, and we can run the SQLite browser, and we can then open this database, and we can see what's in there. So here we go. It is made an SQLite database. We have a table of counts, and then we can take a look at the data, and there we go. We've got the data and we can do this. And so let me close this. It's important at times when you don't want necessarily to have, well, let's see if we can cause it to lock up. Let me run this again, and it's going to drop this table. So I'm going to run the code again. But this time, I am going to do the full one, mbox.txt. Now, we'll see what happens here. But it ran. And now, so what we have to do then to see this date is from the previous run, but if we want the most recent one, we hit refresh, and then away we go. And so we can see this stuff. And so this is just a real simple start to see how you can connect some of the stuff that we've been doing, but store the data in a database. But the nice thing about the database is that it can store this stuff from run to run. Even though in this case, we're dropping the table every time, in later things, we will see how we can store data from run to run to give ourselves more restartable processes. Cheers. We're going to do some code walkthrough, and if you want to follow through with the code, you can download the sample code from Python for Everybody. And so the code that we're going to play with is the Twitter spider code that is both talking to the Twitter API and talking to the database. And so what we're going to be doing is we're going to run code that's going to hit the Twitter API, much like we did in a previous chapter, and we're going to retrieve the data, but we're going to remember the data so we don't have to retrieve it again. Okay, and so we're going to keep track of people's friends, and what we're doing here is sort of illicitly pulling down, slowly but surely, based subject to our rate limit, we're pulling down who our friends are. And so let's take a look. We're going to use URL-lib and URL-lib error, Twitter URL, which was code that augments my URL to do all the OAuth calculation. We're going to get JSON data back. We're going to make a database, and we have to import SQL because of the way Python doesn't trust any certificates, no matter how good they are. So this is our URL to talk to the Twitter API. We're going to make a database, and again, the way SQLite works is if this spider.sqlite doesn't exist, it creates it. And we get ourselves a cursor, and we're going to do a create table. This, if not, exists. Some SQLs, but SQLite 3 does this. Create table if it doesn't exist. We want to start this over and over. Unlike the tracks example, I want to start this over and over and not lose data. And this is a spidering process, and we'll see a lot of these where we want a restartable process where we use a database. So if we're starting with nothing and there's no file, a spider SQLite, it creates this table, and it's the name of the person, whether we retrieved it or not, and how many friends this person has that we know of in our database. Now this little bit is to deal with the SSL certificate errors. The certificates are totally fine, but Python doesn't trust any certificates by default, which is frustrating, but whatever. So here we're going to have a loop. We're going to ask for a Twitter account. We have to type quit to quit. If we hit enter in this case, we're going to actually read from the database an unretrieved Twitter person and then grab all that person's friends. Okay, and so then we're going to do a fetch one, get one, and that's going to get the name of the first person, the sub-zero. If we had more things than name here, sub-zero is the first of those. Fetch one means get one row from the database, and sub-zero means the first column of that first row. And if this fails, then we've retrieved all the Twitter accounts. And so, you know, we're going to augment this Twitter URL using this you can look at the twurl.py code. This basically requires the hidden.py file, which has your keys and secrets in it. You got to get hidden.py updated. I've got it updated, but I'm not going to show you because it has my keys and secrets in it. And so we're only going to take the first 5, which means we're probably not going to find friends of friends of friends. It's only the most 5 recent ones. We could run this with a much higher number to get so we have more than one friend. We'll show the URL while we retrieve it. We will do our URL open. We'll do a read, and then we'll do a decode to make sure that this this will give us data in UTF-8, and then decode will give us data in Unicode, which is what we need inside of Python. We will ask for the headers from the connection. We'll say, give me the headers, give me a dictionary of the headers, and the X-rate limiting header from the Twitter API tells us when we're going to be told we can't use this API anymore, because this is one of those things. And then we're going to parse and load the data that we got from Twitter and get a I think it's a list. Yeah, it's a list. And then we could dump this if you want. In yours, you can undo that. And then what we're going to do is we've just retrieved this person's screen name and their friends. And so the first thing we want to do is update the database and change the retrieve from 0 to 1. And that's because we're going to use this to know about unretrieved. So retrieved being 1 means we've already retrieved it, and we did retrieve it. So for that account, we've retrieved it. And then what we're going to do is we're going to parse that. And so this is similar to the Twitter code we did previously in the web services chapter. We're going to go through all the users. We're going to find their screen name. We're going to print the screen name out. Okay. And then what we're going to do is see if, let's see. So we're going through all the users who are the friends of this person. And we're going to say, oh, okay, let's select the friends from Twitter where the name is the friend person. And what we're going to do is we're going to do a curve fetch 1 of this Twitter, the name of the friends. This is the friend screen name, right? So we're going to say, oh, okay, if we get this, we're going to get the friend screen name, and we're going to get how many friends this particular screen name has. If we find a URL, we find it in there, we're going to do an update statement and add 1 to their friend count, how many friends they have, and then keep track. This count here is not in the database, it's just so I can print it out at the end. If there is no record for this particular friend, we're going to insert them into it new, and we're going to say, here's the new person that we just saw. Here, that's their name. We're going to set retrieve to 0, and we're going to say that they have 1 friend. Okay, and then we're going to commit the transaction, and then we're going to close this at the end. Okay, so let's go ahead and run this. The first time it's going to create an empty database. So I'm going to say Python 3 twspider. So ls star SQLite. Nothing there. Python 3, oops, that's because I removed it. Python 3 twspider.py. Okay, so I'm going to start with a Twitter account, Dr. Chuck. And so it's doing this retrieval, and don't worry, showing the token and the signature is not dangerous because you don't have the keys or the token, the secrets and the token secrets, so don't get all too worried. So I have 11 calls left, so I hope this all works. One of my friends is Stephanie Teasley, and these are in reverse order. So let's grab Stephanie and ask for Stephanie's friends. So now we just retrieve Stephanie's friends, and here are Stephanie's most recent friends. And then I can just hit enter, and it'll randomly pick. Let's see if I can in the database. Let's open this up, file open database. Hope I don't lock myself. Sometimes it's a little scary when you look at the database and you're just checking. So this is what my database looks like. We retrieve Stephanie, and she has, this is how many people. So these are the friends of Stephanie and me, and these are how many. I'm not in there. So we retrieved Stephanie, which was a friend. So let's go grab, I don't know. Let's grab Tim McKay and get that one. Remaining 10, I don't have too many of these. Tim McKay, right? So there we go. Remaining 9. And so if I do a refresh on this, then you see I've got some more folks. If I hit enter here, it will retrieve, it'll pick one randomly based on the retrieve being 0, so it won't pick Stephanie or Tim because they're 0, but we have lots of other folks to pick randomly. And we'll hit enter. So it picked, who did it pick? It picked screen name Live EDU TV, which is ironic because I'm recording this on Live EDU TV right now. And so we can keep hitting refresh and away we go. So I'm going to stop now because I only have 8 remaining. And so I'm going to type quit, and so we will see we'll see how that works. So that's how it works. Now remember that you've got to edit the hidden.py file to make this work because we are talking to the Twitter API. If you don't edit that file, it won't work for you. Okay, so I hope you find this useful. Cheers. So now we're going to take a look at how we deal with more than one table, multiple tables, because the real power of SQL and the power of database performance has to do with when you start connecting tables together. If you go back to that original mathematics, it models data at the intersections between the row and the columns. And these intersections are the magical bits. And so breaking an application to use multiple tables is an art form. It takes a while. There are some simple basic things that you can learn, and we'll teach you here. And so it's not too hard to learn the basics, but then it's much more complex to be super skilled at it. And in general, advanced databases, in my mind, it's hard to teach advanced databases because they're always so contextually grounded. Something like a Twitter or Google, the databases are so specialized. By the time you make everyone can do small to medium-sized databases using the basic techniques, but at some point, once you escape medium-sized databases, you end up in these sort of narrow things and optimize each database very separately. And so I just tell people, learn the basics really, really well, write programs, and then go do real work. But database design is the act of figuring out the data that your application is going to want to store and spreading that across multiple tables. But we don't just do it randomly, we do it very much cleverly. And if you look at a data model, this is what it looks like. And what we're showing here in this data model is we are showing 5 tables, and this is a kind of a calendar kind of a system. And we're seeing the columns that are in each of the tables, and then we're seeing the relationships between the tables. And even in these relationships, there's kind of a little bit of code. And when you have an arrow that looks like that, there's many of those to one, and this is a many-to-one relationship. Many-to-one relationship. We'll talk all about that stuff. But if you go into an organization and you have a really large and complex data application, they might have something printed out on the wall that looks about like this, which shows the database tables and connections, et cetera, et cetera. And they might say, oh, your job is to go down in this little corner and add one field there, and then do this, and then connect it with this thing over there, and then make a screen that shows all these things that pulls from this table, this table, this table, and that table, and that's your job if you're a programmer on a large software development project. These database models become sort of like the core backbone of the knowledge that applications are managing and using. So the idea is that you take your application, we're going to start really simple, we're going to take your application and you have to draw a picture. And the basic rule, and literally you could spend course upon course learning about database normalization, but I'm going to distill it into one basic rule, and that is never put the same string data in twice. So my name, Charles Severance. If I build a database well, you should go into that database and you'd say, okay, the words Charles Severance, which is the name of a person, me, in that database, only shows up once. And what we do instead is we connect things together and model my name as a connection to the record that has my actual name in it, rather than putting my name all these other places. And so the idea is to pull duplicate data out and make only one copy of it. So there is the users, and in there is the user's name, and the username shows up only here, and everything else points to the particular user entry. So that's the idea. And so here is our first application. We are working as a startup. We just quit all of our jobs, and we are going to build a music management application. I mean, what a great idea. Don't you think that'll be quite successful? And so we have mocked up and we have figured out that this is what our music management application. We want to track people's tracks, know something about what artists and albums and genre they are, and we want to have ratings and how many times we played them and how long they are. Well, that's the data that our application needs to represent. And we've done testing on this and wireframes, and everyone loves this. A great user interface. And so this is how it's got to look. But we're going to have billions and billions of tracks in these things, and so we want to come up with an efficient database to handle this. And so we're going to take a look at this and look at each of the columns, and we're going to ask ourselves, is this column part of one of our existing objects, our existing tables, or is this this object have to create a new table? And then once we've defined those different objects, we connect the tables together and model the connections. Now, a little trick to kind of make it a little easier on ourselves is we can look in these columns and look in the columns that have duplicate information vertically that's string information. So a rating is just a number like 0 through 5. So we don't worry too much about integers and numbers and that kind of stuff or whatever, but we do look for strings. And the problem here is we got like these strings occur many times. And so these are the problems. And so we have to put these things where there is replication of string data kind of in the vertical dimension. We have to put those in different tables. And so we'll start out. Now the first question that you have to ask yourself when you're going to draw this picture of how this data is in multiple tables and connected together is, what is the first one that you're going to write down? And this is an interesting debate, and often people are sitting in a conference room, and people who have experience kind of know what to do. Usually if it's a multi-user system, like a learning management system, the users might be the central concept. Perhaps the courses might be the central concept. This is a single user system, and so you can think, well, what is really this application about? It's not about people, it's one person, but it is about tracks. And so we can say, okay, here we'll take the track is probably the sort of most foundational notion of this application. And then we can take and say, okay, now that we've decided that tracks are the foundational notion, which of these columns are simply an attribute of the track? Not really, and the cheating way and the easy way in this particular one is like these numbers, all these numbers, like this number and these numbers, not that one. They just go along with track. And so we'll put that in. We got the track title, rating, length, and count, and we put that in. And then the question is, we've got the remaining things are, we've got the artist, we've got the album, and we've got the genre. And so we can say, okay, well, we've got some vertical duplication, so we're going to say, okay, this track probably belongs to an album. So let's pull out the album into its own table. Oops. Pull the album out into its own table. And so pull the album out into its own table. And so that pulls that out, and then you say, okay, what would be the next thing that we're going to pull out? So we pulled out the track, we've got this taken care of, this taken care of, that taken, now we've got the album. Well, albums belong to artists, so let's take out the artist. And then we'll pick where the genre belongs, and we'll just say that the genre belongs to the track. And so, because there might be albums with more than one different genre. So each album is not necessarily a rock album, it could have a rock track and a country track, etc., etc., etc. And so now what we've got is we've got 4 tables, right? We've got a track table, we've got an album table, an artist table, and a genre table. And if we sort of double check, all of the columns that had vertical duplication in them now have their own little table. So we can eliminate, the next thing we'll do is to show how we're going to eliminate this vertical data replication by showing how you represent these relationships that we just created inside of the database. Now we're going to represent these relationships in the database. And again, what we're trying to solve here is this notion of database normalization, third normal form. There is so much theory, right? But in this lecture, I'm just going to condense this down to don't replicate string data and use what are called keys. Use integer keys to point at those things. And we're going to use these integers then to point. So we'll assign each row an integer, and then we're going to point from one row to another using those integers. And so we're going to add these special key columns to each of the tables, and in the database will even give us help managing those. Now, and so we still need to keep track of, who is the creator of the album, which album a track belongs to. We've got to create these relationships, and we have to come up with ways to store those relationships. And so the idea is we're going to have a column in a table, which is the key column, and we're going to call this the ID column. And so this is a row. It might have many bits of data here, but in this case it's just the name of an artist. So this album is going to belong to an artist. And we're going to assign a number inside the database, and so that Led Zeppelin is 1 and AC/DC is 2. And so we have this key, this is called a primary key, and then later when we want to say that the Who Made Who album really was done by AC/DC, we put the number 2 in. And so the difference here is instead of saying AC/DC in this record, we just put the number 2 once we've established this number. So we assign keys, and then we have these pointers that point back, and so that's how we model a relationship with these small integer numbers. And so there are 3 basic kind of keys that we use. One is the primary key, and that is that little ID column that is just a number. But once we give Led Zeppelin the number 1, Led Zeppelin is the number, has got the key 1 for the rest of that database. The logical key is the text area that we use that you might look up. So the title of the band or the title of the album, that's the logical key. And then the foreign key is one of these keys that is really pointing to the primary key of another row. So that's called a foreign key. And you might think that you want to use something like an email address as the primary key for a user table or something like that. The logical key should always be separate, and there should always be a primary key, that integer number. Because things like logical keys do change. People do get new email addresses, and if you've got that email address as a foreign key pointing all over the place, it doesn't work out so well. And so that's why you use these small integer numbers that have no meaning outside. So sometimes if you're on a system and you see a URL and you see some number like 422,016, you're like, oh, that turns out to probably be my primary key in their database. So sometimes you can look in a URL and you can see these primary keys in the URL, but they don't mean anything outside of that particular system. So like I said, a foreign key is a key that is really pointing at a row in a different table. And so we have the album has a primary key for it, but the artist underscore ID points to a row in the artist table, as we will soon see. I have a naming convention, and in my naming convention on this lecture I use ID for the primary key, and then artist underscore ID I use uppercase for the table names, and then artist underscore ID says this is a key, this is just a key that points to the ID key of the artist table. And so that's what I do. So you'll see in all my stuff I'll use that. It's a convention. It's not something SQL forces you to do, but you will find when you go to organizations and work on their databases, these conventions are very important so I can do something and you can understand the rules in which I created it. Some of these, you'll find this used by some people, you'll find completely different conventions, and that'll be okay. Whatever convention your organization uses, learn that convention. So now we're going to talk about how we put these keys in and then how we actually make the connections from one row to another row. So now that we know what a primary key, logical key, and foreign key are, we're going to actually start putting these together and creating tables that have these kind of values in them. So when we were done, we drew this picture that was sort of a logical model of how our data would be spread across 4 tables and how those tables are connected. Now we have to take this and we have to map it in a way that leads to the columns and the needed columns in each of our database tables. And so here's what we do. We basically have to take, and for each of these, when we're going to build a track table, we add a primary key. So we just added an ID field to every one of these things, and that's so we have a place to store the sequence number of this particular row. We have logical keys, we've just marked those are strings, and then we have things like, rating, length, and count, they just kind of go in here. And now we have to model a relationship. So what we do is in the table that the relationship starts from, we put one more column in, and this is the one I will name album ID, and that just is an integer column that's going to record the album ID. So this might be 16, and then 16 goes in here. So there's one of these columns that's a foreign key that points to this, and that's why it's foreign. This is a key that's not in the track table. This is a key in the album table that we're pointing to, and so there's a foreign key. And that's what we have to do, and we just do that over and over and over again, and we quickly convert that picture that was a logical picture to having every table has a primary key, and every time we have a starting point, we have a foreign key, and then foreign key. And then we mark these things as logical key, logical key, logical key, and we'll see how we do that. And so that's the picture. Now we have a picture of exactly how we're going to lay these tables out and the fields that we need in these tables. So we're going to do a create table statement. And I've got this create table statement sitting there. And so this one's going to be a little bit different. We're going to say create table artist, and the ID field is integer, and we're going to add all of this stuff. This is adding to the column to tell it additional stuff. It's a primary key, which means we're going to use it to look up a lot. It's automatically incremented, which means the database is actually going to provide this number for us as we insert records. It's not allowed to be null, it's not allowed to be empty, and it's supposed to be unique. And then it's going to have, the artist is going to have a name column that's just text. So let's do that. We already have our users, and now we're going to do a create table in this SQL, and you can do that. That's okay, that's totally fine. And we have to get this right, and we say away we go. And so now if I take a look at database structure, I've got a users table as well as that users table we were playing with before, and this artist table. Let me go ahead and delete this users table just to say goodbye. Okay, so now we have the artist table, and we take a look, and it's got an ID, and it knows all about this stuff. Okay? So that created the table. We're going to keep doing this. The next thing that we're going to show here is we're going to show the foreign key, right? So artist ID is just an integer. In some database languages like MySQL and Oracle, you would put more stuff here to say this is a foreign key, blah, blah, blah. But in SQLite, we keep it simple and just say that is an integer column, that's a foreign key. The album table has a primary key and a foreign key, and then the title. So we'll go back and we'll grab that text out of my little page, this create table, go back to execute SQL, and then run that. And we'll continue. The genre table has an ID on it, and primary key order. You'll just copy and paste these. That whole thing, you do that over and over and over again. So we'll go in here and run that one. And so the last one we're going to do is the track table. And the only thing that's kind of weird about the track table is it's got two foreign keys, right? It's got an album ID and a genre ID. Once you draw the picture, you just sort of literally translate these things. It's got two foreign keys and a primary key that's pretty much just like all those other primary keys. And, you know, integer counts an integer and length's an integer, all that stuff. And now we've got it. So if we take a look at our database structure, we're going to see that our album, genre, and track are all set up. And these are no columns that we just made with those create statements. Okay? So now let's insert some data. This first insert statement is kind of important to take a look at. So insert into, by the way, the keywords can be upper or lowercase, table name, columns. Now, this table has two columns. It has ID and name, but we told the database that ID was auto increment, so it's going to actually give us the number. It's going to assign the number rather than make us assign. We could make it be 1, 2, 3, but we say, hey database, you're good at this. Why don't you make it 1, 2, 3? And so there is going to be a record that it adds Led Zeppelin. So let's take a look at that. So we'll insert Led Zeppelin. Oops. Over to SQL, insert Led Zeppelin, and run it. So now if I look at database structure and I look at let's look at browse data and look at the artist database, you will see that I put Led Zeppelin in, but this ID field here was auto incremented. And so it was put there by the database. And now when we do the next insert, which is AC/DC, and we take a look at the data, we'll see that AC/DC is 2. Now, if you're writing this in a program, if you're going to write this in a program, you can get these numbers back from the database in your program, but I'm not writing this in a program, so I have to remember that 1 is Zeppelin and 2 is AC/DC. So I'm going to keep myself a little cheat sheet here to remember that. Because everywhere else in the program that we want to say Led Zeppelin, I got to say 1 now, because the artist ID of 1 means Led Zeppelin in those rows. And so now we're going to go back and we're going to take a look at the next one. And now we're going to put the genre in. If you think about it, we're working from the leaves out, where the track will be the last table that will update, because we have to define the keys for things like rock and metal and Led Zeppelin and all those other things. And again, even though the genre table has 2 columns, ID and name, we're only going to specify the name and let the database assign the value. So I'm going to insert both of these and use the semicolon trick. Put a semicolon here and a semicolon there. And run that. And so if I take a look at my browse data and I look at the genre, it's assigned 1 to rock and 2 to metal. And I'm going to write that down. 1 rock, 2 metal. I should have done something like rock and country, because I can't even tell the difference between rock and metal, but whatever. That's my musical skill is not what's at issue in this class. So now we're going to put an album in. The album is the first thing that has a foreign key. So if you remember the thing, the album points to artist. And so that means it has a foreign key of artist ID. And so we have to explicitly say this, because the system doesn't know which artist Who Made Who is, but we know that Who Made Who is AC/DC, and that's 2. And so we know to put artist ID in, so we'll say insert into album, title, artist ID, and so we have to know what this 2 number is. And of course, because we have our handy little cheat sheet, we can go over to execute and run that. And I'll put a semicolon there and a semicolon there and run it. And so now we have in the album field, we now have this. And so this was assigned, and so Who Made Who, you still have to write down that Who Made Who is album 1, and album 2 is Led Zeppelin 4. That makes it even more complex, because the name of the album is Roman numeral 4. I'm sure I can figure that out. Okay, so the next thing that we're going to do is we're going to insert the track record. Now, if you think about the track record, the track has 2 foreign keys, and it's got a lot of stuff. It's got the title, it's got the rating, length, count, but then we got the 2 foreign keys. And so we have to know these numbers. So this 2-1, this 2-1, this 1-2 is the genre. We're specifying the genre and the album that this track is from by those numbers. Now, again, we have to use this cheat sheet, but if this was a program, the program would know that 1 was Zeppelin and or 1 was Who Made Who and 2 was Led Zeppelin 4. And so that the programs, this kind of stuff is easier for the program to understand than for us to keep track of and understand. But just so we can get through these few records, and that's why I rely so heavily on my cheat sheet. So here we are with all these numbers. The foreign keys are the tricky part here. Everything else is really quite straightforward. So now I'm going to insert 4 records into my track table. And then run that. Okay, so if I browse data and I look at my track table, this column here, this ID, that's the primary key of the track table, and then here are the 2 foreign keys. Now the interesting thing is now there is replication in these columns, but the numbers are what's being replicated, and that's okay. We went a long time just not to put Led Zeppelin 4 in twice. We could have made this a string, but by making this an integer, it saves tons of storage and makes it super fast. That turns out to be one of the key things that makes databases super fast, is using these integers. So we take a look at all this stuff. We see that in a sense, by using these little numbers, we are pointing to rows in other tables. The foreign keys are always pointing. They always point to their ID. So these foreign keys are out here. This is the primary key up here. And they always point to a row in another table. And so we have modeled all those relationships. And you will notice that in this entire database, the who made who only appears once. The word rock only appears once. The word AC/DC only appears once. What we have is we have duplication in our data, but we are duplicating the relationships, i.e. these little integer numbers, not duplicating the data itself. And in something that's this small, it seems irrelevant. But if you have billions of records or hundreds of millions of records, it's very relevant. Very, very relevant. So the next thing we're going to do is take a look at how you actually reconnect all this stuff together once we've sort of blown it out in these using these foreign keys and hand constructing all these relationships. Now how we bring it back together to show the data to the user. So now that we've carefully constructed our relationships in the tables, we need to reconstruct the data to show our users. And you can kind of see how you would go pull this stuff together, but there's a wonderful capability in relational databases called join that brings this all back together. And so we have done this for efficiency of storage, efficiency of scanning, etc. But we do need to traverse these foreign keys at times, and the database software will do this for us automatically. So the join operation basically is a way to specify in a select statement that you want to pull data out of more than one table, and then specifying using what's called the on clause exactly how you want that data pulled out. And so here we go. We already have a table, an album table to the artist table, and the foreign key, and we want to, in effect, pull data from both the album and the artist, the album title and the artist name, and we want to show that. And so we're going to say select, which is the same select statement. Here's a little different syntax. This is the list of fields. This is table.field. So it's the album title and the artist dot name, comma there, from the album. And I always start with where the little arrow starts from, album joined with. So that is going to walk down this connection from album to artist. Album joined with artist, don't say with, I just say it, on, and then this is the conditions upon which that join is going to happen. When the album's artist ID, which is this column here, album's artist ID matches, think of that as is equal to or matches the artist's ID. And so it only connects the rows here when there is a match between these two tables. And so if we look at this and we see that you know, this one matches this one and this one matches that one, and so it's the join connects conditionally, and it connects when the on clause is satisfied. And so when this whole join runs, this is what we get. So you select all this stuff. Now this is an abstraction. Are you writing a loop? Are you doing two nested loops? How are you exactly bringing all this data together? We don't care about that, because that's the beauty of SQL. That's the beauty of how we do this in a database. So now if we can just run this command. So let's grab this command. Select track title, genre name from track, join genre, that exact query. Case of keywords doesn't matter. And we go over here and we run this as SQL. And we run it. We get, oops, I got too far. Let's do this one. So let's do that one there. Select artist name. I have to add that one to my little cheat sheet. The next time you see the cheat sheet, it'll be right. So the title, so this is coming from one table and that's coming from another table. Okay? And so that's one. So here is something we can do that gives us a little more detail on that. We can say, so this is where the connection, and so you can think of the join as sort of spreading one table and connecting it to the other table. And so what we're going to show here is it's exactly the same. The only thing we're going to do is we're going to add these two columns so you can see where the match happens. And so this is one table, this is another table, and these are the kind of columns in common, even though they're not. They're the columns that match. This is where the on clause is happening, right? We have taken this table joined with this table on these two things connecting with each other. So you can almost, in some language, some variants of SQL, this would even be a where clause. So you connect these two rows, but only connect them when those two numbers match. So you can see, I mean, if we run this, I'll just run this. And again, you just see this is where it connects. Okay? Now, interestingly, we can see what happens and what the purpose of the on clause is if we omit it. So this is exactly the same as that previous query, except there's no on clause. So it's select all four of those fields from the track joined with the genre. So it's basically taken the track table and the genre with a join, but no on clause. So it's not filtering for matches. This is a match, this is a match, that's a match, that's a match. But we don't have an on clause, so the matchiness doesn't matter. And so you're going to get all possible combinations. And literally, if there were, 10 on one side and 30 on the other side, you would get 300 rows in that join. So it'd be all combinations, except the on clause reduces the combinations. And you might think, whoa, this is really inefficient. And I will say that's what my first reaction was when I first saw this, but it's not inefficient. That's the beauty of abstraction. That's the beauty of SQL. You say do it, and it just figures that out. So let me grab this, and you will see that we can run this one as well. And that kind of gives you why the on clause is important, because now we have a whole bunch of these things. And the on clause just filters that out. So if we would just add the on clause back in, then that would only show the ones we showed on the previous slide. So that's why the on clause is important. The join is like all possible combinations of all pairs of rows between these two tables. On is, oh, but only where these two things match. Now you might think that it's inefficient, but the on clause turns out to be the way it becomes efficient. Okay. So now we're going to do the same thing where we're just going to take the track title and the genre and going to connect that together. So we select this. We need to join from one table, join to the genre table with an on clause. And so we're going to make those connections. And the only thing we're going to look at is the title and the genre name. Oh, oops. And then run that. And so we got the title and genre name. Now the thing you'll notice is for the first time, we now have replication of string data in a vertical dimension. That's okay, because the data is not replicated in the database. The data is now replicated as a result of the join. And so we are going to reconstruct what the user wants to see, which the user originally, all the way back to the beginning, wanted to see the duplicate information in the vertical axis. But now we're reconstructing it. We didn't waste the space or performance in our database, but we still have to show them. And so now the next thing we're going to do is a monster. We are going to reconstruct across all four tables. And you might think this is really hard, and sure, it's going to be a little tricky, but as long as you follow the naming convention and the naming convention makes sense, we're going to do a select from the track's title, the artist's name, the album's title, and the genre name. From the track, join genre, join the album, joined artist. And so the joins follow the little arrows, right? And then the on clause qualifies each of those arrows, when to follow the arrow. And then this becomes pretty easy. It's a foreign key. The track's genre ID, that's a foreign key, equals genre.id. That's primary key, that's a foreign key because I name it that way. And I know that this goes to that genre table because I name it that way. And track's album ID is equal to the album's ID, foreign key, primary key, and album's artist ID is equal to artist's ID. After a while, you can type these pretty fast as long as you follow a naming convention and you know the naming convention. So this looks like it's really hard to do, but after a while, it's really just a pattern. So let's go ahead and run that one. And it will, assuming we've done everything right, replicate all the data. So there's all kinds of vertical data now being replicated. Every column has vertical data. Again, it's not in the database. The select and the join are reconstructing vertical data as it needs to be shown to the user. And so, if you've been following along, probably a couple hours later now, we started with a picture that was our mock-up of what we wanted our user interface to look like, and it had vertical stuff, and we're like, oh, we can't put that in a database model. And then we carefully built a database model that didn't have the data, and then we were like, we got to reconstruct it. So we used join to reconstruct it. And so after all that, we went here with a clean little model with 4 tables all beautifully connected together, and then we had to join it all back together. So join reconstructs it. And again, the key is the storage is efficient, the scanning is efficient, and we still use the join to produce the output that we ultimately want with all the sort of vertical vertical replication that our users really want to see. So there's one more kind of relationship. That was called a one-to-many relationship. That was actually 3 one-to-many relationships. And the other major relationship is what's called a many-to-many relationship. We're going to do some code walkthroughs, actually running some code. If you want to follow along with the code, the sample code is here in the materials of my Python for Everybody website, so you can take a look at that. So the code we're going to look at is from the database chapter, and we're going to look at tracks.py. So a lot of the lectures that I give in this database chapter are just about SQL. And this is really about SQL and Python. So I'll go through this in some detail. So the code that I'm going through is in tracks. There's also tracks.zip that you can grab that has these 2 things. It's got this library.xml file which you can export from your, if you have iTunes, you can export this, or you can just play with My iTunes. And so this is also going to review how to read XML. So we're going to actually pull all this data. And this XML is that Apple produces out of iTunes is a little weird in that it's kind of key values, and so you see key value pairs, and it even uses the word dictionary. And so it's like, I'm going to make a dictionary that has this, then a dictionary within a dictionary. This to me would be so nice if it was JSON, because it's really a list of dictionaries. This is a dictionary, then another dictionary, then another dictionary, and then the key for that dictionary. And it's a weird format, but we'll write some Python to be able to read it. And so you export that from iTunes, and you can use my file or you can use your file. It might be more fun to use your file. So here's tracks.py. We're going to do some XML, and so we import that. We're going to import SQLite 3 because we want to talk to the database. And then we're going to make a database connection, and in this, once we run this, you'll see that that file will exist. And so right now, if I'm in my tracks data, that file doesn't exist. But what we'll see is this is going to actually create it. Now remember that we have a cursor, which is sort of like a file handle. It's really a database handle, as it were. And in order to sort of bootstrap this nicely, we are going, because this code is going to run all the time, it's going to run and read all of library.xml. In later things, we won't wipe out the database every time. And so I'm executing a script which is a series of SQL commands separated by semicolons. So I'm going to throw away the artist table, album table, and track table. Very similar to the stuff we covered in lecture. And then I'm going to do the create table, and I'm doing this all automatically. And you'll notice this is a triple quoted string, so this is just one big long string here, and it happens to know that it's SQL. I'll thank you, Adam, for that. And so it creates all these things. Now, it's not quite as rich as the data model we built because there's no genres in here. And so it's artist, album, track, and then there's a foreign key for album ID and a foreign key for artist ID, which it's sort of a subset of what we're doing. And so when that's done, that actually creates all the tables. And we'll see those in a moment once we run the code. Then it asks for a file name for the XML, right? And so that's what that is. And we're going to, I wrote a function that does a lookup that it's really weird, because if you look at these files, the like in this dictionary there is a key, right? And so the key of this dictionary, this really should have been a key value pair, but so I had it. There's this weird thing where the key for an object is inside of the object, and so we're going to grab we're going to loop through all the children in this outer dictionary and find a child tag that has a particular key. And so you'll see how this works. And this was something I was going to use over and over again. And so the first thing we're going to do is we're going to just parse the string, and this is the string. And then this, of course, is an XML ET object. And then we're going to say we're going to do a find all. And so this shows how the find all, we're going to go the third level dictionaries. We want to see all of the tracks. And so we have a dictionary and a dictionary and a dictionary. And so what we want is all of these guys, right? All those guys right there, right? Track ID. So we're going to get a list of all those. That'll be the first one. This will be the second one, because the find all says go to the find the dictionary key, then a dictionary key, a dictionary tag within that, and a dictionary tag. So it's, and then we'll tell how many things we got, and then we're going to loop through. An entry is going to iterate through each of these, and see, we'll get our name and our artist. Another one bites the dust, a queen, and away we go. And then the next time through the loop, we'll hit this one. Okay, so then what we're going to do is we're going to go through all those entries, and if there's no track ID, and if that's this track ID field, where are you hiding? Track ID. If we don't have that, we're going to continue. And then we're going to look up the name, artist, album, play count, rating, and total time. Okay? And so here they are, play count. A lot of those things that we had in the sample lecture that I did. And we're going to look those things up, and we're going to do some sanity checking. If we didn't get a name or an artist or an album, we're going to continue. We're going to print them out, and then we are going to ask for remember how you have to get the primary key of a row so you can use it? So the way we're going to do this is we're going to do an insert or ignore. And so this or ignore basically says, because I said that the artist name, go up here, I said the artist name is unique, which means if I try to attempt to insert the same artist twice, it will blow up, okay, because I put this constraint on that, except when I say insert or ignore, that basically says, hey, if it's already there, don't insert it again. So what I'm doing here is insert or ignore into artist. So this is putting a new row into the artist table, unless there's already a row in that artist table. And this syntax right here, you know, the question mark is sort of the where this artist variable goes, and this is a tuple, but I have to sort of put this comma in to force it to be a tuple. So this is a way you have a one tuple. And then what I need to know is I need to know the primary key of this particular artist row. Now this line may or may not have actually done the insert, and so I need to know what the ID for that particular artist is. So I do a select ID from artist where name equals. Now it either was already there or I'm getting it fresh and brand new. So I do an artist ID equals, I fetch one row, and it's going to be the first thing, given that I only selected ID. And so this artist ID is going to be the ID. Now I have the foreign key for the album title, right? And so now I'm going to insert into the title artist ID. This is the foreign key to the artist table. And I got this value that I just moments ago retrieved. And I got the album title. But this also is insert or ignore, because now if you look, I have unique on the album title. Yep, unique's on the album title. So that'll do nothing. It doesn't blow up. Or ignore says don't blow up, just do nothing, because this next line is going to select it. And I grab the album's foreign key for either the existing row or the new row, and then I'm going to insert or replace. And so what this basically says is if the unique constraint would be violated, this turns into an update. Now, not all SQLs have this, but SQLite has this that basically says insert or replace. Some SQLs are totally standard. Some things we do, like this select statement is a totally standard part of SQL. Then insert is totally standard, but insert or replace and insert or ignore is not totally standard. But that's okay. It works for SQLite, which is what we're doing. And so we have the title, album ID, length, rating, and count. And then we have a tuple that does all that stuff. And of course, the title is unique, right? The title is unique in the track table as well. And so we've inserted that. So the clever bit here is both dealing with new or existing names in these 3 lines. And we see that pattern twice here where we're doing that, okay? So there's not much left to do except run this code. Hopefully it runs. Python 3 tracks.py and library.xml. Whoosh! Okay, so that is my, so we found 404 of those dictionaries, 3D dictionaries, and now it's starting to insert them, insert them, insert them, insert them. And we can take a look at, so we can do an ls-l or dir on Windows, we'll see that we made a track database. We extracted the data from this library and we made a track database, and we have all these foreign keys. So let's go and take a look at the SQLite browser. File, open database, TrackDB SQLite, and come on up. Where'd you hide? I got it minimized, so there you go. Let's look at the database structure. We have an album, this is the structure, artist and track, we have no genre, and this is all like we did it by hand, except Python did all this work for us. If we take a look at the data and we start from the outside in, we have the artist names and their primary keys. Right, there's the artist names and primary keys. And then we have the albums, and we have the artist IDs. See the artist IDs, how nice those are. So we have the primary key here and the foreign key there, and then we have the title. And if we get to the track, we have the album ID, and away we go. So if I was clever, I could be able to type some SQL. Oh, great. If I was smart, I'd have had this in a paste buffer. So select track dot title, album dot title, artist dot name. I think artist has names and albums have titles. Yes. Okay, so I can do that from track join album. Oops. Album join. Let me make that a little bigger. Bring that over here. Album track join album join artist. Now I need an on clause, and I can say track dot album ID equals album. Notice how I know the name that I named these things, and album dot artist. This is so great when you use a naming convention. Artist ID. Golly, I think that might work. So let's just see what we get when we type that into the SQL box here. Execute SQL. Run. Yay! I got it right the first time. Right, so that's basically my nice little joined up track list. Oh, I'm so happy that I got that right the first time. Okay, well, you can play with this yourself. Play with this tracks, maybe make an export of your own iTunes library and run it with that. And so I hope that you found this particular bit of code useful. Okay? Cheers. So our last major topic is called many-to-many relationships. And up till now, everything that we've done is what's called a one-to-many relationship. And that is, there are many tracks associated with one album. There are many albums associated with one artist. There are many tracks associated with one genre. And you can think of labeling, and as you look at data models, they put little labels on each arrow that tell you which end of the arrow is the many and which end of the arrow is the one. And so in this case, the foreign key is pointing to, there are many of these rows over here, many rows that point to one row over here. So it's a many-to-one relationship. There are various ways. Sometimes I'll put two arrows at this end and one arrow at that end. But whatever it is, this kind of thing we've been showing is a many-to-one relationship. And that's probably the most common thing. But there are times when you just can't model things with a one-to-many relationship. So like if you have a mother and children, well, that's a many-to-one relationship, and it's just fine, and that works fine. But sometimes you have a many-to-many relationship in that there might be many books. One book has many authors, and each author has many books. And so you don't have like the one side. There's no one. And so you have to end up building a table that what we call it, I call it a connector table. They call it a junction table on Wikipedia. But we need a little table that allows us to break a many-to-many relationship into, in effect, two many-to-one relationships in a connector table. And so this is a connector table. So you could think of this as, you know, there are many links here, but we don't have a way to model the many over here to here. And so what you do is you basically say, oh, there's a lot of these things. There's many that go to the one, the many that go to the one, and then in here you sort of create that manyness that you want to create. So it's probably just as easy to look at a sample of this. So let's imagine a learning management system where you're taking a class, and there are some people that are teachers and some people that are students, and many students are members of many classes. A student can be part of many classes, and a class has many students in it. So you can't really find the one end. And so what we do is we make a table called membership. And in that table of membership, we actually often don't put a primary key in at all. We simply put in two foreign keys. And if we're going to put a uniqueness constraint, we put a combination of the two foreign keys as the uniqueness constraint. So we say there can be duplicate user IDs and duplicate course IDs, but there can only be, you know, user ID, course ID combinations. That has to be unique. So you can make unique be more than one column. And so if you imagine a course table and a user table, there's a user ID, the name and email, and the course has a title and an ID. And then we have this little table that just is the connector table that shows the points out. And so we can expand this membership. So let's take a look at how that works. So we're going to create some tables, and these are very classic tables because these are the one end of it. So these are the one end of it. So it has a primary key, a title, a logical key, email. There's a primary key for course, and then there's text. So we add this unique to kind of indicate that it's a logical key. We're not going to allow ourselves to put any duplicates in here. Now the connector database here is a table member, and it has two foreign keys, user ID and artist course ID. And you can even model some data here. So I'm going to model role, which is going to be 0 equals student and 1 equals instructor. And then I'm going to indicate that the primary key or uniqueness constraint is the combination of the user ID and a course ID. Now when we say the primary key, it both limits our ability to insert duplicates, but it also allows the database to optimize its scanning because it knows that that combination is always unique, and so it can organize its disk structure and storage structure to understand how to look things up more efficiently, knowing that once it's found a user ID, course ID combination, it doesn't have to look any farther because they're unique. And so all of these contracts that we add speed things up, save storage, and makes things more efficient, but in ways we don't always know exactly how they happened. And so let's go ahead and make these. Let's go ahead and make these guys. I think I will start with a new database. I'm going to call it LMS for Learning Management System. No, I don't really want to do that one. And so I'm going to not create the table. I'm going to do everything in SQL. And so let me see if it's in my cheat sheet. Nope, that's not in my cheat sheet. So I'll have to fix the cheat sheet again for you. By the time you see the cheat sheet, all these things will be in there. So I'm going to go in here and I'm going to grab create table user. Actually, I'm going to grab them all. Watch this. Grab them all. Highlight all these. Go over to SQLite browser. Blast them all in. And then I'll put a semicolon at the end of each one of the statements. And I want to run them. So does it look good? Yep. So I got a course, I got membership, 2 foreign keys, and I got user. So that all looks good. Okay, so now we're going to have to insert some data in. And we're going to insert from the outside in. And so we're going to just put the name and email. The ID will be automatically assigned for the users. And we're going to do the same thing, and the ID and the courses will be automatically assigned. So let me just grab all this stuff. Go into SQL. That has the semicolons at the end already for me. Thank you very much. Now I'm going to run it. And if I take a look at my data, now I've got primary keys for the courses, and I've got primary keys for the users, and I've got nothing in the membership table. And I of course have to remember what these values are, because Jane is 1 and Ed is 2 and Sue is 3, right? And Python is 1, SQL is 2, is 3. And so when I go into membership, I've got 2 foreign keys here and a role, and they just have to be for the course person combination. And so it's a little tricky to figure all this stuff out. But again, these are just numbers, and if you look at these numbers, user ID, course ID, role, well, user ID 1 is in course 1, user ID is in course as the teacher, user ID 2 is in course 1 as the student, etc., etc., etc. So I'm making these connections by just putting these little numbers in, and once again, conveniently, I have all my semicolons perfectly in place. So I go to SQL, and then I run that, and then I take and I look at my membership data, and there it is. So 2 foreign keys and a bit of data modeled at the connection. That's the way we say that. The role is modeled at the connection. So now we build all this stuff up, we can write some queries that take a look at this. And so what we're going to do is we're going to look at who's in what course and what role are they, and we're going to sort this in a nice way. So let's just take a quick look at the code we're writing. We're going to do a select from 3 tables: the username, the member role, the course title. So in effect, we're not showing any of the foreign keys or the primary keys. We're going to go from the user table, join to the member table, join to the course table. This is pretty easy to write. You know there are 3 tables you want to go across. The on clause is also very easy to write, right? The on clause models each of these connections, where the member's user ID is equal to the user's ID, and where the member's course ID is equal to the course ID. So we're going to concatenate all 3 of these tables together, but we're going to only keep rows where it matters. Now that this role doesn't participate, but we're going to print that out. And we're going to order it by the course title first, and then the member role second, and the name third. And so let's run that. So we've reconnected it. So Ed's the teacher of the PHP class, Sue is the student in the PHP class, Jane is the teacher in the Python class, Ed's a student, and Sue are students in the Python class. Ed's the teacher in the SQL class, and Jane is the student in the SQL class. And so we have many people there are many students in many classes there, and so we have modeled that, but we model that with this sort of table. And if you look at a piece of software that I've written called Sugi, which is a standalone learning management system that's built with learning tools, you will see in anything where membership, where we have a user table, we have a context, which is also the course table, and then we have a membership table. And you look, here's these foreign keys. It's kind of like that's the many side, that's the one side, many to one, and so this, this is now in effect a many to many between these two, but then it's modeled as a series of many-to-one relationships. And you see this all the time in all kinds of things where membership or other kinds of things are necessary, many-to-one, or many-to-many. So, with all that, there's so much to learn. It's both easy and complex at the same time. It's easy when someone shows you how to do it, but at some point you will learn how to build database models and you realize, oh, it wasn't so bad. It takes a while to get used to them. This really just is a quick walk. But the bottom line is what we just did seems like it was, wow, that's nice. Do you really have to do that? And the answer is, if you're going to scale at all, you absolutely have to, because you simply can't read and write data sequentially. You can't read through, update one little piece of data in a file by reading all the way through and then writing a new copy of the file. That could take seconds. And in a system like an online system, you get 1/100th of a second to do something like that. And the databases make it so that happens in 1,000th of a second. So ultimately, you simply have to take advantage of this. You just can't, if you're going to modify data, you can read data from flat files, but even if you're going to read a lot of data, if it's big, it slows down terribly. So it might seem like there's a trade-off that you could debate whether this is worth it, but if you're going to deal with a lot of data, you've got no choice. It's really not as much a trade-off as you think. So this has been a quick romp through databases. We talked a little bit about indexes. There are constraints. We talked a little bit the not null stuff. We've talked about that. Uniqueness, that's a constraint. Another whole area is what's called transactions, and that's the locking of little areas, so you can read an area, then lock it, and then update it to make sure no one else reads it. And so they make sure they either get the version before you looked at it, or before you change it, or after you change it. And so that's how you make sure that you can't do things having to do with bank account balances and get yourself in trouble. So these are a lot of SQL. It's really fascinating. SQL is a fascinating thing to use and learn and performance tune and enjoy. So relational databases are cool. This gets us started. The big thing is don't allow replication vertically of string data. Pull that out into a separate table, establish a primary key, and then have foreign keys that point to that primary key. It is not just how much data you store. It's sort of a compression way, as a way of compressing data. You might think strings take no data, but they do. Numbers take a lot less data, and it's both how much data that's stored, but also how much data has to be scanned. And that way joins work. That's part of the magic of why Oracle is such a successful company. It's a bit of art form, and it's something that you can work your whole life and always get better at.
Hello and welcome to our code walkthrough on the roster code. So the learning objective of this is to do a many-to-many table. And so the idea is that we're going to, just like we talked about in lecture, we're going to have a set of users, we're going to have a set of courses, and then we're going to have a connector table or a many-to-many table that basically has two foreign keys. So we are going to use the integer not null primary key auto increment unique as the way to get auto assignment of the primary keys in the user table and the course table. And then we're going to say that the name, which is like a logical key, and then the course title, we're going to mark those as unique. And we're going to take advantage of that in a moment. And so you'll see how we take advantage of that. So what unique means is if you try to insert the same string into this column, like Chuck twice, then it's going to fail the second time because it's going to refuse to create a new record. And so if we just kind of like take a look, we're going to get our roster data from this sample JSON, which is just an array of arrays. And this is the person's name, the class that they're in, and whether they are a teacher or a student. And so we're going to read that. So we need the JSON library and the SQLite library. We make a database connection and we get a cursor. The cursor is kind of more like the file handle. You send SQL commands to the cursor and then you read the cursor to get the data back. The connection can create more than one cursor so you can have more than one set of commands. But the cursor is generally like the file handle to the database server. And we are going to execute a big script, and you'll notice this is a triple quoted string that goes all the way down to here. And so some people would just give this to you in a text file and have you cut and paste this and then go run that in your SQLite browser to create them, but that's okay, because what we're going to do is we're going to set this up. It will either reconnect to existing file name rosterdb.sqlite, and if I look where I'm at, I do an ls, we find that that file is not there. So the first time I run it, it's going to create it. But I want this to start fresh every time, so I'm going to wipe out the tables if they exist. That way you can run it over and over and over again in case you make a mistake here. Now I don't have a mistake, or hopefully I don't have a mistake on this. So we're going to drop 3 tables, and we're going to create 3 tables. And here we're going to create the table that has 2 foreign keys, user ID, course ID, that are sort of going outwards from the member table. And then we're going to model a little bit of the data at the role. And I guess this, and again, this is straight from the lecture. And the primary key is actually a composite primary key, because we're going to look up, and it's going to force this to be the combination of user ID and course ID to be unique. But there can be many user IDs and many course IDs, but only one particular combination of a value for user ID and course ID. And so that's what we're basically saying. You can be a member of a course, but you can only do that once. You can't be like a member of the course a bunch of times. So we're gonna, oh, that should be roster data sample. That's okay to, oops, fix a bug. Save that, roster data sample. And so that's just this file, and it's really just an array, and then each row is an array, and it's a way for us to get this roster data in. And so once we do load S on JSON, we're parsing it, and then this is going to be an array of arrays. And so for entry in JSON data, so entry is going to be one of these things. So entry itself is a row. So an entry sub 0 is the name, and entry sub 1 is the title. Name, that's the sub 0, and that's the sub 1 of the particular entry that we're looking at. And we're going to print it out just for yucks as a tuple. So we make, that's what the 2 parentheses are. This inner thing is a 2 tuple. And we're then going to take the person, and we're going to do an insert, and this is new, or ignore. So what the or ignore means is if this insert would cause an error, please don't blow up. Don't just ignore that I tried to insert it. And so this is our trick, and it's a beautiful trick. It's like a gorgeously beautiful trick here. If we insert the name Chuck twice, or ignore will just mean that nothing happens, meaning it's already there. Okay, so if it's already there. If it's not there, it'll put it in. And the unique will guarantee that it only goes in once. So we just, in effect, always attempt to insert it. And if it's been there once, then it's all set. And so this insert or ignore is a super powerful mechanism. I use it all the time. And we have a placeholder in the form of a question mark. And then we have, so one of these days we'll have 2 things that we're asking for. As a matter of fact, here it is. There's a tuple down here. But this is kind of a tuple with 1 item in it, name. And that name is then going to substitute in for there without, while avoiding SQL injection. So this runs. It may or may not insert a new record, but if this Chuck or whomever the name is not there, it will give us a new record. And then we are going to get back the ID. And so this is the logical key, and this is the primary key. And that primary key is going to be auto constructed for us, and so we need to know what it is. So we say select ID from user where name equals, and then that same name. So that's Chuck, and so that gives us one. And then what we do is we're going to fetch 1 record from the cursor, because that's a select and it gives us back a cursor. There's only hopefully 1 record there because it's unique. I could put a limit 1 in there, but that'd be kind of redundant because it is the name is a unique key. And then the sub 0 just means if there were more than 1 thing that I was selecting, which we'll see in a bit, the sub 0 is just the first thing. And so this is going to give us the integer user ID that was assigned, or if we're coming through later for Chuck, Chuck later, Charlie later, that will be the old one. So this is inserted if it doesn't exist, and this is get the newly created ID field or the original ID field. And so part of this works by having both a logical key and a primary key. The primary key is auto-generated, but the name is a logical key and it's unique, and so that's our trick to get that assigned thing. Before we just looked at it in the user interface of SQLite browser and wrote it down. But this is how we do it in code. So we need to know what that key is, whether it was new or not. And then we do the exact same pattern for the course, except we're inserting the course title. So that's no big deal. And so we're going to get the user ID, course ID. And then what we're going to do is we are going to insert or replace. So this is it. Basically, remember that this user ID course ID combination is the primary key for this member table. If there is a duplicate, if this combination is already there, this becomes effectively an update statement. And we have these two number values. Now what's missing here is the role is not there. And so user ID, course ID, this is the SQL bit. And now we have a tuple with two items in it. And that's because we have two question marks. And then we commit it. And as I mentioned before, sometimes you want to commit every time through. The commit it turns out that these things are less costly, but that's because it's not always writing all the way to disk. Whereas when you enter the commit, it's going to go and write everything to disk, pause until it's complete, and then your program doesn't continue. So sometimes we don't run this every single time through. Okay, so let's just go ahead and run this. The only thing we're going to see is the output of the name and the title as it's running. So if I do Python 3 roster.py, hopefully I can hit enter. So you'll notice, by the way, that this SQLite now exists, right? And it has no data in it. So let me see if I can open this database and see it. So you see that there's no data. So we're the code, we've run this code in effect up to this point. So we've done all the create tables and all that stuff. And so the create tables are there. So all this data is here. It did it. We haven't started putting any data into it yet, because if we look at browse data, we're not finding anything in here. Okay? There's no data to browse. Now, hopefully we won't have locked ourselves, because we are sitting right here, and when I hit enter over here, then it's going to go, it's just going to run really fast. So I'll hit enter, it'll read it, and so it inserted all of those things, and now it's been changed. And if I hit refresh over here, we will see in the user it just sort of assigned user IDs, right? The columns auto-assigned. We will find in the course that those courses are all auto-assigned. There's the courses. And there's no duplicates because this is unique, right? And so these are the newly created things. But then membership is user ID, course ID. And so again, the primary key, as it were, the unique constraint / primary key is the combination of these things. And I haven't put anything in role. And so if you scroll through these, you see all of the users who are members of the courses that they're part of. Okay? So there you go. And I'll leave it up to you to come up with a join. I'll leave it up to you to figure out how to put the role in, but I just wanted to kind of give you a bit of a walkthrough of this code base, and in particular, the tricks of the uniqueness keys, the auto increment keys, the logical key uniqueness, and then this kind of composite primary key, and then the trick of insert or ignore, and then the quick select that comes right afterwards to get the newly generated ID or to get the old ID. You can insert or sort, and then insert or replace, which is a combination of a insert and an update. So I hope you found this this example useful and can apply it and basically create many-to-many tables. We are doing some code walkthroughs. If you want to follow along with the code, you can download the source code from Python for Everybody the Python for Everybody website. Okay. So the code we're playing with today is twfriends.py, and this is a step beyond the simple TW spider. It is a restartable spider, but we're going to data model things a little bit differently. We're going to have two tables, and we're going to have a many-to-many relationship, except that it's sort of a many-to-many relationship between the same table, which is okay. Friends is Twitter friends are a directional relationship, and so we start out here in twfriends.py. Remember that the file hidden.py, I'll show it to you, but I'm not going to open it because I've got my keys and secrets in it.
So this hidden.py file, you got to edit that, and you got to go to apps.twitter.com and get your keys and put them in there. Otherwise, these things won't work. But if you have Twitter and you set your API keys up and you put them in hidden.py, then all these things will work. It's kind of fun, actually, and impressive. Not hard to do, actually. So the Twitter URL, that's my library that reads hidden.py and augments the URL and does all the OAuth stuff. JSON and SSL because because Python doesn't accept any certificates, even if they're good certificates, so we kind of crush that. Here's our friends list that we're going to hit. We're going to make a database, friends.sqlite. Now here we're doing create table if not exists. So what this really is saying is I want this to be a restartable process and I don't want to lose the data. We're starting out, we do not have SQLite, any SQLite files, and so this is going to create the database and create these tables, but the second time we run it, we're not going to recreate the tables. We're going to be able to restart this because we're going to run out of rate limit before we finish this, but so we just have to wait however long the rate limit takes to reset, and we'll watch the rate limit go down. And so we're going to have a people table, and we're going to have a primary key and the name. The name is going to be unique, and whether or not we've retrieved it. And that's kind of from a previous one. But then there's the who follows who, the from ID to to ID. And so this is a direction, and we're going to put a uniqueness constraint in, just like we do in many-to-manys, that basically says the combination of from ID and to ID has got to be unique. We don't allow ourselves to put duplicates of the combination. So from ID can be 1 in many records, and to ID can be 1 in many records, but 1 is only allowed once. And this is the CRUD we have to do to convince Python to accept the Twitter certificate. And so this is similar to some of the other stuff that we've done. We're going to enter a Twitter account or quit. And if we hit enter by itself, then we will actually go and retrieve a record that was not yet retrieved. And now we're actually pulling out two values, ID and name. And so we will grab fetch1 is going to give us a two-tuple basically, and we're going to store that in ID and account. Of course, that's like this is coming back with a two-tuple, first of which is the ID from the database. Limit 1 means we're only going to get one of these, or 0 of these. If there are 0 of these, that means there are no unretrieved Twitter accounts. Retrieved equals 0. Well, you'll see in a second that all the new accounts we put in are the ones for which we haven't retrieved. And again, given that our rate limit, we want to know which ones we've retrieved. Okay, and so what we're going to do next is we're going to check to see if the person that we just checked, which means the length of the account is greater, that we just were entered, we're going to check to see if they're already there. Okay, and we're going to select ID from people where name equals, so that's the one we just entered. And we're going to fetch 1 and grab the first thing because we only got one thing in the select statement here. And if this person that we just asked to see is not in the table, that means this is going to fail. We're going to do an insert or ignore. This or ignore is kind of redundant because we just checked to see if it was there, but we'll put that in just to be safe. And we're going to put the name in as the new account that we're looking at, and we're indicating that retrieved is 0, so that we will know that we haven't retrieved it yet. You'll see that we'll update that in a second. We commit it so that later selects will see this. So you got to do the commit. This later select wouldn't see the one we just inserted, and we're going to ask how many rows were affected, and if it's not equal to 1. Then we're going to complain about we inserted it, and we are going to do this thing. We're going to ask, hey, remember there was an ID up there? Right here, ID integer primary key, and we did not insert this here, but we want to know what that ID is. And every time I was showing you that in lectures, I was saying it's really easy in Python to do this, and that's what we're saying. Is this cursor did the insert, but one of the things happens is after the insert, we're going to grab the last row ID, which is the primary key that was assigned by SQL. Okay, and so that means that one way or another, coming through this code here in line 45, one way or another, we're either going to know the ID of the user that was there before, or
we just inserted one, and so we're going to know the primary key of the current user, and you'll see why we need that. So ID is the primary key of the current user that we entered right here. Okay? And now what we're going to do is do the Twitter URL augment with the OAuth and all the keys and the secrets and hidden.py. Instead, we're going to go through, let's count 1,000. Let's go count, what the heck, let's go 200, up to 200 friends. Save. No, let's do 100. We'll keep it that way. And then we're going to retrieve it, and we're retrieving the account. We're not going to print the nasty URL out. We could. Then we're going to open the URL with a connection, and then we're going to read that, and we're going to get the UTF-8 data from this, and then we're going to decode that, and we're going to have the Unicode data. So the data string is a internal Python string with all that data representing all the wonderful characters. And of course, we're going to ask URL open to give us back the headers as a dictionary using this call, and we can see what how many we have left for the remaining, right? What's the remaining rate limit that we have, okay? And so then what we're going to do is parse the data with JSON load S. If, oh wait, I need a continue in here. Continue, okay, save. If we are going to parse this data, we'll print it out, right? So that means that this died, which means it's not syntactically correct JSON, basically. And who knows if we're ever going to see that, but at least when it blows up, it'll print this data out. We'll have to catch it, and then it'll continue. Actually, I'll make this a break, because if that's blowing up that bad, we should quit. Now, I don't yet know what happens when this rate limit says you can't have it. And so, but I do know that I expect when it's successful that there will be a key of users in this outer dictionary that we're going to get. And if this outer dictionary that if users is not in the parsed dictionary, then I'm going to dump out this data so that at least I can debug what happens when I've got some broken JSON. So the difference between this code is going to fail when the JSON is syntactically bad, meaning a curly brace isn't right or whatever. This code will trigger when I get good JSON, but I don't have a user's key in it, okay? So then, once we've retrieved it, we're pretty happy with it. We're going to update for our account that we're retrieving. We're going to set this as one of our retrieved accounts, okay? And then what we're going to do is write a loop that goes through all the friends of this particular user that we're asking and gets their screen name, prints it out, and then we're going to check to see if this one is already in our people database, because this is a spider. We're grabbing accounts, and so we'll do a friend ID and do a fetch one, grab the sub-zero thing, and if that works, if this person's not in there, this fetch one is going to blow up, which means we're going to drop down to the accept code. But if it does work, we have friend ID is the, you know, that they're there and they're already in our database, right? They just weren't retrieved, okay? And so now if the friend ID wasn't there, we're going to do an insert into setting retrieve to 0, and then we're going to commit, right? Now, remember, row count is how many rows were affected by this last transaction, cur.row count, and we're going to die if that insert doesn't work. This is unlikely, unless somehow we've ran out of disk drive or something. And we're going to grab the friend ID as the key, the last row that was inserted. We're only going to insert one row, so it's basically the primary key of the row that we just inserted. So if you look at this code right here, it comes out the bottom one way or another with friend ID successful, right? Friend ID is either they're already in our database or they're not. And if we insert them, then we have it. And so now, this count new and count old is just so I can print out a nice printout. Now we are going to insert into the friend table, which is called the follows table in this case, from ID and to ID. Those are the two outward pointing foreign keys. And we have the ID of the account that we are retrieving the friends of, and then this particular friend. And so we're inserting the connection from this person to that person. And then we commit it. We want to commit these again so that later selects, when the loop goes back up, later selects get all of that data that's going on. Okay, so we do want to commit from time to time, and then we close the cursor at the very end.
Okay, so let's run this and see what happens. Okay, so Python twfriends.py. Oh, of course, I am a refugee from Python 2, so I always forget to type Python 3. Okay, so we're going to start. If we take a look right now, I'm going to start another tab over here, and ls-l star SQLite. Now that SQLite file is there, right? And it's actually made the tables. If you go up here, it ran all this stuff. Create the tables, yada yada, and we're sitting right here at this line. As a matter of fact, I think without causing too much trouble, I can open that database and get into this database right here, and there is no data in the follows table, and there is no data in the people table. It's completely empty, okay? So we're waiting for the first one, and I'll go with mine, Dr. Chuck. So it's retrieving the 100 friends, and they all were brand new. They're all inserted, right? And so now if I hit refresh, we will see that Dr. Chuck is retrieved. Who follows? So these are all the people I follow. So one follows two. So if we look at here, we see that Dr. Chuck follows Stephanie Teasley. Because we grabbed the followers of Dr. Chuck, you know, we're going to have a record in all of the follows for all the ones that I did, right? So these are all the people I followed, and we put them in. Okay? So we can go back, and we can, let's see, grab somebody. Let's go grab Stephanie Teasley. And let's pull out her friends. So we grabbed 100 of her folks. I got 14 left. That's my X rate limit. So I did Stephanie Teasley. So let's go back here. So you'll notice there's 101. There's probably going to be, 182. That's interesting. So we've retrieved Dr. Chuck and Stephanie Teasley. And let's go take a look in the friends table, the follows table. Okay. So we have all of the people I follow, now all the people Stephanie follows. Okay, so there we go. So let's go ahead and do somebody else. Let's see, I think we both follow Tim McKay. Where's Tim McKay? Yeah, let's follow Tim McKay. Let's see who Tim follows. See if we can get like an overlap. Oh, we revisited some. Let's see if we can see this in the follows. Let's see people. So we've got Dr. Chuck retrieved and Tim McKay's somewhere down here. You know, it might take us a while before we get any really good overlaps. Let's see. Let's do a database call. Let's see, let's do a database SQL. Select, count, Okay, so let's just run this some more. It's clearly working. Now, one thing I can do here is I can hit enter, and it will just pick one randomly. So it grabbed live edu TV, and now I can, and let's see how many I got left. We got 12 left, and now I can hit enter again, and it picks another one. That was the next one. I was kind of picking them in order. Is it picking them in order? Let's go to people. Yeah, it's picking these. So it's gonna, we can see that it's gonna just do the first unretrieved person, who's Nancy. Let's let it retrieve Nancy. So it grabbed Nancy, new. So we're finding some, and this table's getting really big. And so if we look at the people table, we now have 455 people, and we have 467 following records. And so there we go. Oops. Hit enter, it does another one. And away we go. So you get the idea. I can type quit to finish. And just to give you a little interesting bit of code to show you how to do selects, I'm going to do this twjoin. Now you'll notice that we're not talking. Oh, let's show you one thing. ls-l friends star SQLite.
So this database has it so I can restart this process and run it again, and the database is still there. And so we just grab, swear trek, and so we can keep doing this. And so this data, it keeps extending. And so this is a restartable process. I can run it and then tell it to grab the next unretrieved one. And so away we go, right? And so that's part of it. So I can, if I run out of my, I've got 8 left. Oh, how many do I have left really? Let's keep going. How many do I got left? I got 5 left. Okay, wait. Oh, I guess we'll just run it out. So I got 4 left. You know what I should do is I can't change the code. Yes, I can't change the code. I can stop the code and I can quit the code. So what I'm going to do is I'm going to change this code a little bit really quick. And I'm going to print the headers of rate limiting at the beginning and at the end. So now I can run it again. I changed the code. Hopefully I didn't make a Python error. Tell it to go get another one and a Navarro. And so I got 3 left. Oops. We'll see what happens when I run out of rate limit. Run out of rate limit. So we have 1 left. Hit enter. Hit Control K. Opensource.org. So we have 0 left. That worked. Now let's see what happens. I don't know what happens next. Oh, we blew up. Too many requests. Oh, we got an HTTP error 429. So that means that, going for Mark Cuban, that was in line 48. So the right thing to do would be in line 48. We should really put this in a try except block. Try except block, because it gives us an error. Print, oh fiddlesticks. How do I print the exception message? I always am forgetting. Print failed to retrieve. Okay, so we'll put that in. Now if I run it, oh, and then I have to put a break here because that's not good. Break. Failed to retrieve. Now I got to figure out. Oh, I never know how to print out the error message. Yeah. So I have to. I never see. That's the weird thing about stuff, is that I don't ever remember enough. I don't remember the syntax, what I say here, to print the error message out. So I'm going to go to Google, and I'm going to say print out the exception message in Python. Print out the exception message in Python. Oh, Python 3, hello. Okay, so let's go find it here in the documentation. Except. Is this it? Is this what I say? I just want to print out the message. Ah, that's it. Except. Let's try this. So this is part of Python programming, is like, for me at least, because I'm just not like a genius expert at this stuff. This is one thing I like about Python, is you can guess stuff, and sometimes you guess right. So there we go. We got the error, we got the nice little error message, and we see error 429, too many requests. So that cleans that up nicely. So we have run out of requests, and on that, it is a good time to say thanks for listening, and I hope that you found this valuable.
Hello, and welcome to our final chapter, Retrieving and Visualizing Data. In this chapter, we are going to basically bring this all together. Databases, web services, code, loops, logic, and we're going to solve a problem that is a multi-step data analysis. We're going to find some data on the internet, might be HTML, might be an API or whatever, and we're going to write a relatively slow process that's going to pull data slowly, because these are all rate limited. This is a slow and restartable process. So you can start this, and what we're going to do is we're going to have a database that's going to hold the data that we're pulling, and so this might take several days actually, if you really have to do it, and then you'll build up your data in your database, and then what you tend to do is you tend to produce two databases. One is kind of a raw database that, it's all of its data columns are aimed at helping you figure out what you've got to retrieve yet and what you haven't retrieved yet. So that's kind of a crawling, spidering process. And then you find that the data is kind of nasty and ugly, and you find that before you're going to do any analysis, you probably want to clean and process it. So in a lot of these, you're going to go from a raw database to a clean one. And this is going to be really large, and this is going to be really small. And you're going to do this sort of once but slowly, and you'll do this as many times as you need, changing this program, cleaning the data up over and over and over again. And then you'll end up with really clean data, and it's relatively small. And you might run programs that'll loop through this to do visualizations or analysis or some things or whatever. And so you'll actually sort of use this database as a source of information. Okay? So that's the basic pattern of what we're going to work with. Now, this is what I call personal data mining. And if you're going to do this seriously, Python is used in lots of data mining activities, but if you're going to do data mining seriously with really, really large data sets, we're doing small to medium-sized data sets, as you might do sort of for individual personal research versus like an organizational research where you're processing the logs of a web server or something like that. And there's lots and lots of wonderful technology. And what's really cool is this technology just keeps getting better and better, because the whole data mining, data analysis, natural language processing field is just so hot right now. It's so awesome. We're going to keep it simple and do stuff for ourselves for now. And I gave you a bunch of sample code that's going to make it so that you can adapt this sample code to solve the problems that you need to solve. So like I said, this is more of a programming exercise. Data mining might be a lot more complex. If you're doing simple research, this might actually model what you do pretty well. So the first thing that we're going to do is what's called use the Google's JSON API for geocoding. And there are two versions of this. One version requires a key, and one version doesn't require a key. Google used to make all this data available for free, but with just a rate limit, but now they're increasingly requiring a key. So I give you code in this zip file that kind of does both. If you really want to do something in production of taking user entered places and names and getting precise latitude, longitude coordinates, so you can produce a nice little Google map like this. Since Google has made a rate limited API, I've actually pre-spidered a copy of the Google data, and I have my own sort of fake Google API, and so you can do your assignments and test all your code using my fake API, which has no rate limits and has no problems, but it's only a limited set of the data. And so this is the basic process, and it's one of those things that it follows that basic personal data modeling, personal data mining pattern. And so here's this API, which is either Google or me. I've got my own Dr. Chuck version of this, drchuck.net version of this, and there is an input queue of the location. So this is the user data where they just put in the name of where they think they live, University of Tübingen or something. And so this is the queue of the things that are to be retrieved. And in my case, when I built this map for the first time, there was like 15,000. And it took me days to get this. And so it would stop. And so what I would do is I would, read the first one into this geoload.py, check to see if I already had it in my database. If I didn't already have a database, I would go into the API, I'd pull the data down, and I would put it in the database. And then I would go to the next one, the next one, the next one. And so, I might get 1,000 in my database, and then it blows up, or I'm told I can't go any further. So I wait 24 hours, I start it up, and it reads the first 1,000 and says, oh, they're all in the database already. And then it starts at 1,001. And then it adds that, and adds that, and then until it stops. And so it took me several days of processing to get this data right. Now, I didn't have a separate cleaning process because this data is pretty simple. I was pulling out the JSON, the latitude and longitude, etc. And so I didn't have to do two separate processes to clean this data up. It was clean enough right as I pulled it. Because I was talking to an API. If you're talking to the HTML, sometimes it gets nasty and ugly. And so then I wrote this program that just reads through it. It just does a select and reads through the stuff, and it prints out some summary information and tells you what to do. It also prints out, and you'll see this pattern, because I'm visualizing using browsers, HTML, and this happens to be using the Google Maps API. And putting all the data in a little JavaScript file. So these end up being assignment statements in JavaScript. You can take a look at that file. And all the data shows up as assignment statements in the JavaScript. And then when this HTML loads, it reads this file and puts up all those pins, as long as you have access to the in-browser JavaScript API. So the next thing we're going to talk about is Pagerank, which is spidering now HTML. We talked a lot about this. Spider HTML, get some links. And so up next, we're going to actually build a real database, full-featured search engine using Pagerank.
This is another worked code example. You can download the sample code zip file if you want to follow along. And the code that we're working on today is what I call the Geodata code. And that is code that is going to pull some locations from this file. We're simulating or using the Google Places API to look places up, and so we can visualize them on a map. And so this is the basic picture. If we take a look at this where.data file, it's just a flat file that has a list of organizations, and this actually was pulled from one of my MOOC surveys. We just let people type in where they went to school, and this is just a sample of them. So this data is read in by this program geoload.py, and if you recall, this Google Geodata has rate limits. It also has API keys, which we'll talk about in a bit too. And so the idea is this is a restartable spider-like process. And so we want to be able to run this and have it blow up and run it and start it and not lose what we've got, right? And so this is unlike some of those. So we're not now using a database as well as an API, but in order to work around the rate limits of this API, we're going to use the database with a restartable process. And then we'll make some sense of this, and then we'll visualize this. But in the short term, let's start with geoload.py code. Geoload.py, take a look here. So a lot of this hopefully by now is somewhat familiar to you. URL lib, JSON, SQLite. And so I mentioned that the Google APIs, these used to be free and did not require an API key, but increasingly they're making you do API keys for especially new ones. And so what happens, you can go to your Google Places, go to Google APIs and get an API key, and you can put it in here. It'll be this big long thing that looks like that. And then if you have an API key, you can use the Places API. And I've got a copy of a subset, not all of it, a subset of it here at this URL. As a matter of fact, you can just go to this URL in a browser, and it will tell you a list of the data that it knows about. Okay. And I made it so that does the same basic protocol with the address address equals as the Google Places API. So this will just change how we retrieve the data. Either retrieve it from my server. Nice thing about my server, it's got no rate limit. It's really fast, and you're not fighting with Google all the time. And it means that perhaps if you're in a country that Google is not well supported, you can use my API. I mean, that's really strange that somehow my API is more reliable and available than the Google one, but it's true.
So we're going to make a database. We're going to do a create table if not exists, and we'll have some address, and we're really just caching the geographical data. We're going to cache the JSON. One of the things we do when we build these processes is we tend to simplify these things and not do all the calculation and parsing of the JSON. Just load it and get it in, and load it and get it in, and fill the data up in this database. And so that's what we're going to do. Because Python doesn't ship with any legitimate certificates, we have to sort of ignore certificate errors. We're going to open the file, and we're going to loop through it and pull out the address from the file, and we are going to select from the geodata where that address is the address. Let's move this in a bit. And so we're going to do a select and pull out that address. And the idea is if it's already in the database, we don't want to do it. So we do a fetch one and pull out that first thing, which is that will be the JSON right there. If we get that, we'll continue up. Otherwise, we'll keep going. Pass just means don't blow up. So we accept and we just do a pass. That's like a no op. And we're going to make a dictionary because that's what we do for the key value pairs. Everything you've seen so far, I've used constants here, but because we may or may not have an API key, query equals, and then that's the address, and then the key equals, and then the API key. If you recall, URL encode adds the pluses and question marks and all that nice stuff. We're going to retrieve it. We're going to read it and decode it, print out how much data we've got, and add a count. And then we're going to try to parse that JSON data and print it if something goes wrong. And as we've seen, at this top level of this JSON data from this geocoding API is an object, which we'll see a little bit of it in a bit. And it has a status field in it. And the status is okay if things went well. So if the status is not there, that means our JavaScript is not well formed or not how we expect it. If the status is not okay, or not equal to 0 results, then print out failure to retrieve and then quit. And then we're simply going to insert this new data that we just put in, and then we're going to commit it. And every 10th one, this is count mod 10, we're going to pause for 5 seconds, and we can hit Control-C here, and then we're going to do the geodump. Okay, so let's just run this. Geodata, Python. So let's do an ls. So we don't have, oh, we do have, let's get rid of from a previous test, geodata.SQLite. So we'll start with a fresh set of data and run python geoload.py. Of course, I'm always forever making the mistake of forgetting Python 3. So you can see that it's running and it's adding the query, and in this case I don't have the API key. And it's putting the pluses in, and that's this part here with all the pluses. That's the URL encode. And you notice it's pausing a bit. Now, it depends on how fast your net connection. This may or may not go so fast, but this is not that much data, so it's like only 2,000, 3,000 characters. And so it's working and talking to my, my server. And the interesting thing here is I can blow this up. I'm going to hit Control-C. In Windows, you'd hit Control. In Linux, you'd hit Control-C, and in Windows, I think you'd hit Control-Z, depending on what shell you're working in. But I'm going to hit Control-C, and you see I sort of blew it up, right? And that's causes a traceback, a keyboard interrupt traceback. If I do an ls-l, you can see that now this geodata is there. Now, in the name of restarting, I will restart this, and you will see that it checks and skips, and so it runs this code here, where it's right here. It grabs it and finds it in the database. So you'll see it say found in the database really quick, chop, 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 and go really fast, and then it'll go back to catching up where it left off. And so all those up there, they did not actually retrieve it because it knew about those things. And so now it's catching up and doing some more and doing some more and doing some more. And then I'll hit Control-C. It has a little counter in here that basically, if it hits 200, it stops and you have to restart it. You could obviously change this code. You could make it so it didn't sleep. It doesn't hurt to sleep for like a second after every 100 or so if you want. You could change that code. And now let's just hit Control-C.
and blow it up, ls-l. And there is another bit of code, and this code, it's always good to write these really simple things. And so we're going to import SQLite and JSON. We're going to connect ourselves up. We're going to open, except this is a UTF-8 because it's a UTF. We're going to open this with UTF-8, and we're going to read through. And in this case, we are going to decode. We did select star from locations, and if you recall, locations has a location and a geodata. And so the sub 0 will be the location, and the sub 1 will be the geodata. And we're going to parse it, convert it to a string, and then parse it. If something goes wrong with the JSON, we'll just keep skipping it. We'll check to see if we have the status in our JSON. Let me run the SQLite browser here. File open database. Let's take a look at what's in this database. Oh, where are we? Code 3, Geodata SQLite. So this is the data we've got. So if you make this a little bigger, if I can I make that bigger? Yeah, it's not going to show us much. So you can see that these are the addresses in the geodata. That's just the JSON. So that's the JSON that we got, and it retrieves it. And so this is a really simple database. That's just a sort of spidering process, run. But now we're going to run the geodump code, which is going to read this and dump this stuff out and print where.js. So it's going to actually parse this stuff. And that's code we've seen before. And so we're actually reading it. And this line goes into the results. Results is an array. So if we go into results is an array. We're going to go grab the 0th item in that array. And then we're going to go find geometry, and then location, and then lat and long for the latitude and longitude. And then we're also going to take the actual address out of the formatted address right here. So in this bit of code, we're actually parsing the JSON, and we're going to clean things up, get rid of some single quotes. This kind of data cleaning is just stuff after you play with it for a while, you realize, oh, my data is ugly or does this. I'm going to print it out, and then I'm going to write this out, and I'm going to write it into a JavaScript file. And so the JavaScript file is this where.js, and this, I'll show you what it looks like. It's going to be overwritten. This is the one that came out of the zip file. It'll have the latitude, the longitude, and we're going to use JavaScript to read this in this where.html file. It's going to actually read this right there and pull that data in, and that's how we're going to visualize. I'm not going to go into great detail on how the visualization happens, but that's what's happening, and so we're going to write that. So we're going to actually write this to a file. So let's go ahead and run this code and say Python 3 geodump. Okay, so it wrote 120 records to where.js. So if we look at where.js, this is now the new data that I just downloaded moments ago. And it says open where.html in a browser. Now this you'll need the Google Maps API, and you might not be able to see this depending on where you're at, but here you go with Google Maps locations, and I think if you hover over this, you can see, and you see the UTF, why we there in that particular thing, why we had to use the UTF-8 when we wrote the file, so that we didn't end up with trouble writing the file out. And so there you go. And so that is a simple visualization, and just a simple visualization. It wrote this where.js. If you are smart with HTML and JavaScript, you can look at this where.html file. It's really just reading through a bunch of data and putting the points. That's all there is, but I'm not going to go through that. So, at least not in this. And so I hope that this was useful to you, and thanks for watching.
So now we're going to write a search engine. Do some of the things. We're going to do Pagerank, and we're going to visualize it in a web browser and show the weights. We're really only going to do Pagerank on one page because you want to have links that more than one page that points to a page so that you can figure out which pages are more or less important. And then we'll visualize it. We'll run the PageRank algorithm and we'll separately do all this. So at this point we're going to do pretty much the web crawling, the index building, and the searching. We're not going to really search it. We're going to visualize the index. But you could write a simple program to do searches for keywords and figure out which page was the most likely page for a keyword. And that would be a fun additional thing to do. So the web crawler is this program that hits a page, pulls down the HTML, parses the page, looks for links, makes a queue of incoming links that are as yet unretrieved. And I'm going to do this in a simple SQLite database. And starts out with, the database basically starts with one link as the starting point, and then it retrieves that page, and then you see the database end up with lots of unretrieved pages, and then it goes back in and picks a random page and retrieves that one, and then it just expands and expands. This code that I've built that you're going to play with only stays on one website, otherwise it would go crazy. But of course Google doesn't use an SQLite database running on your hard drive. But you'll get the idea. You'll see this thing exponentially gain links, and you'll run it for a while, pull down 1,000 web pages or whatever. But of course, make sure that you don't violate any terms and conditions. And again, I've got some data sources that you can use, and they're not rate limited, but you can also use things like Wikipedia, which I think they sort of discourage you, or drchuck.com, which has no rate limit, or who knows what, right? So just be careful. Don't do this on Facebook, and don't do it on Google. Don't get yourself in trouble. And if you're using, you know, a internet connection where you're paying for bandwidth, be careful. So this is the idea of the web crawler, and this isn't my picture. This is the classic picture of a web crawler. Read a page, parse it, take all the URLs and stick them in a queue, grab again and again. So for us, this scheduler is going to do it as long as you'd say, oh, do 100 pages, or it runs until it blows up. I mean, and again, these processes that have the network in the loop, it's really important that they behave well when they blow up. And that's why databases are so useful, because you can be writing along to the database and some random thing happens and blows your data up and you start over. So you're reading these things, you're storing each page, building up your storage, etc., etc. So you just keep on doing that. And with this program, you'll be able to retrieve some stuff, then run the PageRank, then you can retrieve some more, and then you can run some more PageRank, and you can kind of see how Google sort of evolves its index over time. Of course, we're so much simpler. And like I said, be careful when you crawl. You're going to run a crawler that just goes as fast as it can, but Google doesn't do that. It's careful not to overwhelm any websites. It's trying to be smart about the use of your bandwidth on your website. There is a file. Our code won't bother looking at this. But there's a file called robots.txt that real web crawlers look at, and it gives a list of the things you are allowed to look at and not allowed to look at. And so if you go to Google and you see a search that says, we are not allowed to show you the summary text of this page because of the robots.txt, it's there, and you can go and you can actually see a robots.txt. Like on, just go to any website, it's at the top root, blah, 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 / robots.txt. It's not a path. It's not / this, / that, / something else robots. It's at the very, very top of a website. The index building uses the PageRank algorithm. And the whole goal of the PageRank algorithm is to figure out which pages have the best links. So having the most links is really easy. You can just say how many links go to this. But the problem is you got to figure out the value of those links. And then you have to, how do you figure the value of those links? By looking at how many good links come to it. So it turns out that it's an infinite problem. It's an infinitely difficult problem to use PageRank. But you can approximate it, and what happens is after a while it converges to a reasonable value. And so we're going to run the search index, and each time it runs, you're going to see that it says, you know, how much did these numbers change? And what happens is, in the beginning, they change very wildly, but quickly they flatten out. And it has the best way to think about the PageRank is think about how water runs, where you have a small little stream going by a house, and sometimes it rains, sometimes it's dry, and sometimes, you know, and there's like a little lake, And the stream is always running, and it doesn't go up and it doesn't go down. It might go up a little bit if it rains a lot, but in general, there's sort of a steady state, meaning that whatever water's coming in is about the same as the water going out. So we think about this in terms of web pages. The value of the links coming in is roughly the same as the value of links going out. So when that starts to balance the in and the out value from each of the nodes, then you've got pretty stable. And so what Google does is they have a really relatively stable assessment of goodness and value of pages, and they use that to compute PageRank, and then they throw a few more pages in, and it kind of has to adjust for a while, but it reconverges. And so this is a calculation that generally converges, and it doesn't vary wildly. And that's why Google's pretty good at kind of arriving at the true value of something. So let's take a look at what we're going to do in this application. Again, we have a file that is going to spider the web, and we only have one database. Again, in this one, we'll have two databases in the next one. And so this is spider is the restartable part. And what we actually do is we put one URL in, the starting URL, and then spider walks in and asks, are there any unretrieved pages? And it does that randomly. It sort of picks among the unretrieved pages and says, okay, great, I'll go retrieve that page. And then I'll parse that page, and then I'll put in a bunch of new unretrieved pages, okay, as well as the text of that page, and then a bunch of unretrieved pages. And then it'll go back up and it'll say, oh, give me one of the randomly non-retrieved pages, and it'll grab a next page and pull that page down and then add to it. And so this is like there's a page and then a to-do list. And then this one becomes a page and then adds a few more things to the to-do list. And so the to-do list, or the unretrieved URLs, grows very rapidly. And the retrieved ones grow sort of as you retrieve them one at a time. But you've always got this long list. If you have a really short site that only has like 2 links, if you start at drchuck.com/page1.htm, it'll go to page 2 and then go back to page 1 and it'll be out of things. It'll have retrieved all of the pages. And so if you have a website that has no external links or has very few pages and they point to each other, this will run out of things to do. But if you go to a page like my blog or the code that the sample stuff that I have up for you to spider for testing on drchuck.net, it'll run for a very long time, and you'll have far more pages to retrieve than pages that you retrieve. But that's okay. At some point, you can stop this. Maybe it stops because you ran out of bandwidth, or maybe your computer went down, or who knows what, right? But it's okay. This is a restartable process because it always has some pages that are retrieved and some unretrieved pages. You start it back up, it picks randomly from the unretrieved pages. Your database is the sort of persistent state of your spider rather than a bunch of dictionaries or lists inside the Python, which go away when the program dies. And so at some point you have, let's just say, a few hundred pages in here and a few thousand unretrieved pages. You can run the PageRank algorithm. And what the PageRank algorithm does is it loops through all the pages and figure out which pages are linked to which pages, and then reads the numbers and then updates the numbers, and then does that some number of times. And so this is where the numbers, all the pages sort of start out with goodness of 1. I think this printout is showing that goodness of 1, and then it changes, and then the goodness goes to some of the goodness goes up to 2, some of the goes to 7, and whatever. But then it does this over and over, and then it uses these numbers, and then they change again. And so there's a number of time steps that this PageRank runs, and you will see as the PageRank runs, when I show you the code, you will see the average sort of change in these numbers across all these things, and you'll see that the average goes down very rapidly as you get through. And so usually with a few hundred or even thousand pages, like 100 plus times running this algorithm, and these numbers have converged. And that's when you sort of can begin to trust the numbers. Now there's this one program called SP Reset, which sets all the pages back to 1, so you can start this over. So if you were to spider for a while, run SP Rank for a while, play around, and then you wanted to spider some more and start it over, you could say, oh, let's start the PageRank completely over. Or you could simply take the new pages and watch it adapt. Either way, this is just a way to reset all the pages to have sort of their initial value of a goodness of 1.0. So at some point you run this. This part here runs really slow. This part runs super fast, like in the blink of an eye. This one is pretty fast. And then at some point you've got these pages that have, numbers on them. They have values on the pages, and there's a couple of programs that allow us to visualize that. One is the dump, which just reads it and checks to see. It shows the new page rank, the old page rank, and various other things, and shows just a way to dump it. And then there's this thing that reads the whole thing. You say, I'd like to do 25 of the best. It sorts it by page rank, and then produces a JavaScript file that has just the numbers in it. And then there is some HTML and a visualization library called d3.js, which you can read about, that when the HTML starts, it reads this and has this nice force-directed layout of the page rank. And you can hover over things and you can see what page rank you've got. And so that is the PageRank algorithm that we're going to do. And up next, we'll do the largest and most complex of these things, and that is the email. We're going to spider some email, which is about 1 gigabyte of data. Okay? We're doing a bit of code walkthrough, and if you want to, you can get to the sample code and download it all so that you can walk through the code yourself. What we're walking through today is the PageRank code. And so the PageRank code, let me get the picture of the PageRank code up here. Here's the picture of the PageRank code. And so the PageRank code has 4 chunks of code that are going to, 5 chunks of code that are going to run. The first one we're going to look at is the spidering code, and then we'll do a separate look at these other guys later. So the first one we'll look at is spidering. And again, it's sort of the same pattern of we've got some stuff on the web, in this case web pages. We're going to have a database that sort of just captures the stuff. It's not really trying to be particularly intelligent, but it is going to parse these with beautiful soup and add things to the database, okay? And so then we'll talk about how we run the PageRank algorithm and then how we visualize the PageRank algorithm in a bit. Now, the first thing to notice is that I've got to put, I put the beautiful soup code in right here, okay? So this is, you can get this from the bs4.zip file. There might be a README, no, but there's a README somewhere. But you got to use Beautiful Soup, you got to put this bs4 zip, or you have to install Beautiful Soup for your stuff. So I provide this bs4.zip as a quick and dirty way if you can't install something for all of the Python users on your system. So that's what it's supposed to look like. You're supposed to have it unzipped right here in these files, and I don't know what dammit.py means. That came from Beautiful Soup. If you look, it's in their source code. So I'm not swearing. It's Beautiful Soup. People are swearing. I'm sorry. I apologize. Okay, so the code we're going to play with the most is, in this first one, is called spider.py. And, you know, we're going to do databases, we're going to read URLs, and we're going to parse them with Beautiful Soup. Okay? And so what we're going to do is we're going to make a file. Again, this will make spider.sqlite, and here we are in PageRank, and else minus L. Spider.sqlite is not there, so it's going to create the database. We do create table if not exists. We're going to have an integer primary key because we're going to do foreign keys here. We're going to have a URL, and the URL which is unique, the HTML which is unique, whether we got an error. And then for the second half, when we start doing PageRank, we're going to have old rank and new rank, because the way PageRank works is it takes the old rank, computes the new rank, and then replaces the new rank with the old rank, and then does it over and over again. And then we're going to have a many-to-many table, which points really back. So I call this from ID and to ID. We did this with some of the Twitter stuff. And then this webs is just in case I have more than one web, but that really doesn't make much difference. Okay, so what we're going to do is we're going to select ID URL from pages where HTML is null. This is our indicator that a page has not yet been retrieved. And error is null, ordered by random. And so this is our way, this long bit of stuff. And not all this SQL is completely standard, but this order by random is really quite nice in SQLite. Limit once is just randomly pick a record in this database where this true is true, and then pick it randomly. And then we're going to fetch a row. And if that row is none, right, we're going to ask for a new web, a starting URL, and this is going to fire things up, and we're going to insert this new URL. Otherwise, we're going to restart. We have a row to start with, and otherwise, we're going to sort of prime this by inserting the URL we start with, insert into it. If you enter it, just goes to drchuck.com, which is a fine place to start. And then what we do is what this does is its PageRank is it uses this webs table to limit the links. It only does links to the sites that you tell it to do links. And probably the best for your PageRank is to stick with one site. Otherwise, you will just never find the same site again if you let this wander the web aimlessly. And so I generally run with one web, this should be probably called websites. And I pull in all the data and I read this in and I just make myself a list of the URL, the legit URLs, and you'll see how we use that. And the webs is what are the legit places we're going to go? Because we're going to go through a loop, ask for how many pages, and we're going to look for a null page. Again, we're using that random, order by random, limit 1. And then we're going to have we're going to grab one. We're going to get the from ID, which is the page we're linking from, and then the URL. Otherwise, there's no one retrieved. And so the from ID is when we start adding links to our page links, we got to know the page we started with. And that's the primary key. We'll see how that primary key is set in a second. So otherwise, we have none. And we're going to print this from ID, the from ID and the URL that we're working with. Just to make sure, we're going to wipe out all of the links because it's unretrieved. We're going to wipe out from the links. The links is the connection table that connects from pages back to pages, and so we're going to wipe out. So we're going to go grab this URL. We're going to read it. We're not decoding it because we're using Beautiful Soup, which compensates for the UTF-8, and so we can ask. This is the HTML error code, and we checked that 200 is a good error. And if we get a bad error, we're going to say this error on page. We're going to set that error. We're going to update pages. That way we don't retrieve it ever again. We basically check to see if the content type is text HTML. Remember, in HTTP, you get the content type. We only want to look for the links on HTML pages. And so we wipe that guy out. If we get a JPEG or something like that, we're not going to retrieve JPEG. And then we commit and continue. And so these are kind of like, oh, those were pages we didn't want to mess with. And then we print out how many characters we got and parse it. And we do this whole thing in a try except block because a lot of things can go wrong here. It's a bit of a long try except block. Keyboard interrupt, that's what happens if I hit Control-C at my keyboard or Control-Z on Windows. Some other exception probably means Beautiful Soup blew up or something else blew up, and so we indicate with the error equals -1 for that URL so we don't retrieve it again. At this point, at line 103, we have got the HTML for that URL, and so we're going to insert it in, and we're going to set the page rank to 1. So the way PageRank works is it gives all the pages some normal value, and then it alters that. We'll see that in a bit. So it sets it in with 1. We're going to insert or ignore. That's just in case this pages is already the pages is not there, but and then we're going to do an update, and that's kind of doing the same thing twice, just sort of doubly making sure if it's already there, this or ignore will cause this to do nothing, and the update will cause us to retain it, and then we commit it so that if we do selects later, we get that information. Now this code is similar. Remember, we use Beautiful Soup to pull out all the anchor tags. We have a for loop. We pull out the href, and you'll see this code's a little more complex than some of the earlier stuff because it has to deal with the real nastiness or imperfection of the web. And so we're going to use URL parse, which is actually part of the URL lib code. And that's going to break the URL into pieces. Come back. We use URL parse. We have the scheme, which is HTTP or HTTPS. If it's this solves relative references. This solves relative references by taking the current URL and hooking it up. URL join knows about slashes and all those other things. We check to see if there's an anchor, the # at the end of a URL, and we throw everything past, including the anchor, away. If we have a JPEG or a PNG or a GIF, we're going to skip it. We don't want to bother with that. We're looking through links now. We're looking at all the links. And if we have a slash at the end, we're going to chop off the slash by saying -1. And so this is just kind of nasty choppage and throwing away the URLs. But we're going through a page and we have a bunch that we don't like, or we have to clean them up or whatever. And we've made them absolute by doing this. It's an absolute URL. This is just, you write this slowly but surely when your code blows up and you start it over and start it over and start over. Then what we do is we check to see through all the webs. Remember, those were the URLs that we're willing to stay with, and usually it's just one. If this would link off the sites of the sites we're interested in, we're going to skip it. We are not interested in links that leave the site. So this is like link that left the site, skip it. But now we finally, here at line 132, we are ready to put this into Pages, the URL and the HTML, and it's all good, right? And that one's going to be null right there because we haven't retrieved the HTML. This is null because this is a page we're going to retrieve. We're giving it a page rank of 1. And we're giving it no HTML, and that way it'll be retrieved, and then we commit that, okay? And then we want to get the ID, so we could have done this with one way or another, but we're going to do a select to say, hey, what was the ID that either was already there or was just created, and we grab that with a fetch 1 and say retrieve to ID, and now we're going to put a link in, insert or into links, from ID to ID, which is the ID, the primary key of the page that we're going through and looking for links. To ID is the link that we just created, and away we run. So it's going to go and go and go and go. Let's go look at the create statement up here, from ID and to ID right there. Okay, so let's run it. Python 3 spider Python. So it's fresh, and so it wants a URL with which to start. And I'll just start with my favorite website, www.drchuck.com. Now this first one you put in, it's going to stay on this website for a while, okay? So I'll hit enter, and let's just grab let's grab one page just for yucks. Okay, so it grabbed that, and it printed out that it got 45 characters, and it printed out that it got 6 links. So if I go to this and open database, and I go to code 3 and I go to Pagerank and I look at this, let me get out so it closes. So notice this SQLite journal. That means it's not done closing, so I'm going to get out of this by pressing enter, and so you'll notice now that that journal file went away. Otherwise we would not be getting the final data. There we go. Okay, so webs, let's take a look at the data. Webs has just one URL. That's the URLs that we're allowing ourselves to look at. You can put more than one in here if you want, but most people will just leave this at one. Pages, so we got this first one and we retrieved this, and this is the HTML of it, and we found 6 other URLs in there that are drchuck.com URLs, right? There was lots of other URLs in there, but there were only 5 other ones that we found, okay? And so, and what we'll find is if we go to links, we'll see that page 1 links to 2, links to 3, links to 4, links to 5, links to 6, because the links is just a many-to-many table. So page 1 points to page 2, page 1 points to page 2, page 1 to 3, page 1 to 5, okay? So that's what happens when we have the first page. So let's retrieve one more page. Now we could have started a new crawl, but it's going to stay on drchuck.com, and I'll just ask for one more page. And so now it went and grabbed. It randomly picked among these null guys, and I'm going to hit enter to close it, and then I'll refresh this. And oh, so it looks like we retrieved OBI sample and we didn't get any new links. And so the links page, no, we didn't get any new links. So that page, whatever that was, OBI sample, had no external links. So let's do another one. Oh, one more page. So that one had 15 links. So let's take a look now. So now we have 15 pages. It picked this one to do, right? And now it added 15 more pages. And then if you look at links, you will see that page 4, which is one it just retrieved, links back to page 1. So now we're seeing this is where the PageRank is going to be cool. 4 links to 1, 4 links to is whatever, away we go, right? 1 goes to 4, 4 goes to 1. I should have probably put a uniqueness constraint on that. It's not supposed to that duplicated that. Okay, so let's run this a bunch of times now. So let's just run it 100 times for 100 pages. It'll take a minute. So you'll see it's like freaking out on certain pages and not parsing them. You know, it's found its way into my blog. It's finding like 27 links. This table is growing wildly at this point. It's going to take us a while before we get to 100. It's kind of slow. Now the interesting thing is I can hit Control-C at any point in time. Right? And so that blew up. But it's okay because the data is still there. And so if we go back to pages, for example, and we refresh our data, we see we got a ton of stuff. And this will restart and all the things. So if we search this, that I sorted that by HTML, you see that there's lots of files that we've got, and it's never going to retrieve those again because those have HTML. So then I can run this thing again and start it up. And when I say Control-C, your computer might go down, your network might go down. There's all kinds of things that might happen, and you just pick up where it leaves off. It just picks up where it leaves off, and that's what's nice about this. Okay, so that's pretty much how this works. We've got this part running. We're seeing it flow into Spider.SQLite. We're seeing that we can start this and replace this. And so what I'll do is I will come back in the next video and show you how all these things work together and then how we actually do the PageRank. So thanks again for listening, and see you in the next video. We're picking up in the middle here where we are running a simple spider that's retrieving data and putting it into running this spider.py file, and it's cruising around and doing things. And the beauty of any of these spider processes is I can stop anytime and just hit Control-C. And so we take a look at the spider.SQLite file and retrieve it, and it looks like we got 302 pages. I don't know how many we got retrieved. 70. Okay, there we go. We got about 100. Oh wait, I'm looking for the wrong thing. No. Yeah, we got about 107 pages. So what we're going to do now with 107 pages is we are going to run the PageRank algorithm. Okay, so let's take a look at that code. So the idea of PageRank, we're going to run this PageRank algorithm. The SP reset just resets the PageRank, and SP rank runs as many iterations of PageRank. So the basic idea is that if you were to look at the links here, you know, we think of page 1 pointing to page 2 gives some of page 1's love to page 2. Page 4 has some value that it gives to page 1. You go on, and page 2 gives love to page 46, over and over and over again. And so, but the problem is that how good is page 1, and how much positive karma does it give to page 2? And so what happens is we start by giving every page a rank of 1. We say, look, everybody starts out equal. But then what we do is we divide up in one iteration of the PageRank algorithm, we divide up the goodness of a page across its outbound links, and then accumulate that, and that becomes the next rank. Okay, and so let's take a look at the code for the PageRank algorithm. So this is pretty simple. It only imports SQLite 3 because it's really doing everything in the database, right? It's going to be updating these columns right here in the database. And so so we're going to do some things here to speed this up. This rank runs, if you're thinking of Google, this rank runs slowly and is going to run continuously to keep updating these things. So the first thing I do is I read in all of the from IDs from the links, select distinct, throws out any duplicates. And so I have all the from IDs, which are all the pages that have links to other pages, because all the pages are in pages, but in links to have a from ID, you have to also have a to ID. Okay, and so we're also going to look at the pages that receive PageRank, and we're kind of pre-caching this stuff. Okay, and so we're going to do a select distinct of from ID and to ID, and loop through that group of things. And we're making a links list here, and so we're saying if the from ID is the same as the to ID, we're not interested. If the from ID is not already in my from IDs that I've got, I'm going to skip it. If the to ID is not in the from ID, meaning that this is a to ID that's not also, we don't want links that point off to nowhere or point to pages that we haven't retrieved yet, and that's what this is saying. So this is really going to give us, it's a filter on the from IDs and the to IDs from the links table so that it only are the links that point to another page we've already retrieved. And then we're going to keep track of the entire superset of the to IDs, the destination IDs. And I'm just putting these all in lists so that I don't have to hit the database so hard. Okay, so this is getting what's called the strongly connected component, meaning that any of these IDs, there is a path from every ID to every other ID eventually. So that's called the strongly connected component in graph theory. Then what we're going to do is we're going to select new rank from pages where for all the from IDs, right? And so we're going to have a dictionary that's based on the ID, the primary key, that's what node is, equals the rank. And so if we look at our database, that means that for the part of the strongly connected component in links, we're going to grab this number and stick it into a dictionary based on the primary key of this, this number right here. So we're going to have a dictionary that's this mapped to that. Again, we want to do this as fast as possible. Now we're only doing one iteration at the beginning, so it asks how many times you want to run it. Okay, so we just make an integer of that. We check to see if there's any values in there. If there are no values, we are bad. And now we're going to go I equals 1 to range many. This is going to be 1 to 1, so it might run however many times. And then what it's going to do is it's going to compute the new page ranks, and so what it's really going to do is it's going to take the page rank, the previous ranks, and loop through them, and this is the previous ranks is the mapping of primary key to old page rank. Okay, and for each node, we're going to have total equals total plus old rank, and then we're going to set the next ranks to be 0. Okay. And then what we're going to do is figure out the number of outbound links for each page rank item. So node and old rank in the list of the previous ranks. These are the IDs we're going to give it to. And so for this particular node, we're going to have the outbound links, and we're going to go through the links and not link to itself, although we made sure that doesn't happen. We make sure that this, but then we're going to make a list called give IDs, which are the IDs that node is going to share its goodness. And now what we're going to do is we're going to say how much goodness are we going to flow outbound based on our previous rank of this particular node and the number of outbound links we have. So that's how many that's how much we're going to give in our outbound links. And then what we're doing is all the IDs we're giving it to, we started with the next ranks being 0 for these folks. These are the receiving end, and we're going to add the amount of PageRank to each one. So whatever this is, so we'll go through all of the links, give out fractional bits of our current goodness, and it's accumulated in each one. And so eventually, all the incoming links will have granted each new link value. Okay. Now I'm just going to run through and calculate the new total, and this evaporation. The idea is that you can't. It has to do with the PageRank algorithm that there are dysfunctional shapes in which PageRank can be trapped, and this evaporation is taking a fraction away from everyone and giving it back to everybody else. And so we add this evaporative factor, and then we're going to do some computations just to show some stuff, and that is we're calculating the difference, the average difference between the page ranks, and you'll see this when I start running it, and that is telling us, this is going to tell us the stability of the page rank. So from one iteration to the next, the more it changes, the least stable it is, and you'll see in a sec that these things stabilize. And then we'd say, what's the average difference in the page ranks per node, which is what this is, and that's what we're going to print. And now we're going to take the new ranks and make them the old ranks, and then run the loop again. So I'm not actually updating the database each time through the PageRank iteration, but then at the very end, I am going to do the update for all of these things and update all of the rankings with a new rank. So I'm doing an in-memory calculation so that this loop here runs screamingly fast. Even if I want to do like this loop 100 times or 1,000 times, it's really all just in-memory data structures. Okay, so it's probably easier just for me to show you this. It'll be very, the code runs quite simply. Python 3 sprank rank.py. And so I'm only going to run it for one iteration, and that means that this loop here is just going to run one time. And so it's going to start with the page ranks of the new rank of 1, and it's going to just run one iteration and put the rank there, okay? And then update this as well. So let's go ahead and run that once for one iteration. Okay, and so it ran one iteration, and the average change between the previous rank and the new rank is 1. So it's actually quite crazy. So I'm going to refresh here, and you'll see that the old rank was 1, and the new rank went way down, way down, way down, way down, down a little bit, down, down some, up a whole bunch, down, down, up. So you see that they went down and up. Now the sum of all of these numbers is going to be the same, right? Because all it did was like floated out and recalculated it. And so that's what happens with PageRank. And so what will happen is if I run one more PageRank iteration, these numbers will be used to compute the new rank, and then these will be calculated to the old rank. And so you'll see that these will change again. So I'll just run it one more time. So I'm going to run one iteration, and then we'll hit refresh. So you see all these numbers got copied over, but now there's a new rank that's computed based on these guys. And so they're getting, this one went up. This was 0.13. That's gone up a little bit. This one's gone up some more. This one's gone up. This one went down, right? So this one went down from 6 to 8. And you can see that the difference is now the average difference between this number and this number across all of them went from 1 point something to 0.41. And you'll see that with these very few pages, this PageRank converges really quickly, okay? So let's run it again. And I'll just run 10, and you will watch how this converges. Okay, so there you go, it converges. So, and you're seeing now after like 12 iterations that the difference between the old rank and the new rank, well, that's because it's that old rank. I'll run one more iteration so that you can see. So this old rank is less than, 0.005, so now you can see that these numbers are sort of stabilizing. This is the average. That 005 number is the average difference between these two things. Now, if we're going to pretend to be Google for a moment, we can say Python 3 spider.py. So let's just do 10 more pages. Now what's going to happen here is these new pages are going to have page ranks of 1. Okay? So let's get out. So if I do a refresh now and I look at new rank, so there's these guys that have high rank. What you'll see, I hope, yeah, okay. So you see new pages, right? These are the new ones that we just retrieved. I don't know if they're linked or not, and they all got 1. So some old pages are way up, 14. Some pages, if we go downwards, are way down, right? So these are like useless pages. They point to somewhere, but nobody points to them. That's what happens with these page ranks, okay? So what happens is the new records get this 0.1, and so if I run the ranking code again, and I run, let's just run 5 iterations, you'll see that the average delta goes up just briefly as it sort of assimilates these new pages, and then it goes right back down again. And so that's what's happening with Google. It's sort of running the spider to get more pages, then running the page rank, which gets disturbed a little bit, but then it reconverges very rapidly. And of course, they've got billions of pages, and we've got hundreds of pages, but you get the idea. Okay, and so I can run page rank like 100 times, and after a while, it just sort of hardly is changing. So that's 2.7 to the negative 10th power. So now, let me run it one more time to update the stuff. And if I refresh this, you're going to see, look at how stable these numbers are. 14, 9, 4, 3, 5, 9, 1, 5, 6, 7. The difference is there in the 7th one. So that's why this whole PageRank is really cool. It seems like it's really chaotic when it first starts out, and away you go. Okay? So that was just this, SP rank, right? SP rank, and SP reset, we can look at that code. I won't bother running it. It just sets the old rank to 1. That's it. That's as much code as you've got. It just restarts it and lets it rerun. So I'm going to stop now, and I'm going to start a new video where I talk about this phase here where we're actually going to visualize the page ranked data. And what we are in the middle of is we're in the middle of the PageRank code, and we just got done running the PageRank, and so we have spidered the code, we've run PageRank a bunch of times. SP reset allows us to restart the PageRank algorithm if we want, but we're not going to play with that. We're just going to play with SP dump and SP JSON and do the visualization, which is the fun part. So I'll go into SP dump. So this is simple code because it's really just running a SQL query and then printing stuff out, right? So we connect to our database, create a cursor, and then just do a select count, and we're going to just show the number of links. We're going to order by the number of inbound links descending, so we see the most linked things, and we'll see the top 50 of that. So this is just a sample. You'll tend to write little helpers like this that make your life easier just to show you the kinds of things that you want. spdump.py, and like you just kind of test to make sure that's like, oh, this looks right to me, and so here is the number of inbound links. So that's my blog that has the most inbound links, followed by my uncategorized, whatever that is. And these are the number of inbound links within my own blog somehow. I don't know, because this is not looking at the whole internet at all. So there we go. So that's SP dump, pretty straightforward. And now we're going to go through the visualization process. And so this is going to look at all that data and produce some file, a JavaScript file. It's going to write a JavaScript file that will then be fed into my visualization using D3. And SP JSON
is going to do a big long join. It joins the links with the thing, and where HTML is not null and error is not null. Ordered by the number of inbound links. So we're looking at the things that have the highest number of inbound links. We're going to read all this stuff. We're going to read through all those rows and pull out the page rank for each one. We are looking for the highest and lowest rank because these numbers can vary quite widely. They go all the way from 0.000 to 20 or 30. And so it asks how many do you want to do, so it only does the top, like 20 or something, and you'll see why we need that in the visualization. And so this is just checking. And so we're going to write out a file. We'll see what the format of this is. It's just a JavaScript file, and we're going to write out. We're basically normalizing the rank. We're subtracting the minimum rank, and because we're going to turn this into line weight, the thickness of the line, and so we're dividing by, we're normalizing the rank to be the thickness of the line and the size of the ball. You'll see all this, and so this is really just writing some JavaScript with the little strings and stuff like that, and then we're going to finish the JavaScript, and then we're going to write all the links out. So these are the balls that you'll see. And this is showing this is drawing all the lines, and this is again normalizing things for thickness and printing these things out. Now I don't want to go through this in tremendous detail, but so I'll do Python spjson.py. Let's do the top 20 nodes, and if I take a look at this file spider.js, you can see that it's some objects that basically put the page rank in, which ID it is, and that's a way for me to be able to link back and forth. Weight is how big the little circle is, and then I have the links. And I only asked for the top 20, right? And then this is the thickness of the line, where the line starts, where the line ends, okay? So this is read by this HTML file, and it's going to read somewhere this force.js file, and my own spider.js code. This is some JavaScript. The force.js is the visualization code, and this is D3, the visualization library. So I'm using this d3.js, which is a really great visualization library, and this is just drawing the circles and making the circles colors and making the circles bigger and smaller, and then connecting all the lines in between it. So this is just there. This data feeds that thing. And so when we're all done, you simply say open. You don't have to do anything. Open force.html. And so all this beautiful JavaScript stuff is like, oh, wow, that's really cool because you can move these things around. Whoa. You can see the circles are bigger. If you hover over it for a while, it shows you the big ones. You can see these things, and it's kind of cool. So I gave you all this force.js and force.html, and so that kind of visualizes the page rank, and you could use this to visualize quite a bit of stuff. It'll take you a while to pull down enough data from a real website, but after you pull down 400 or 500 pages, if you have some time, and then the visualization is quite interesting. But you can see why we had to pull down several hundred pages just to get this much page rank information. Okay, so that gives you a sense of how to run the page rank code in Python for everybody. So thanks for listening.
The last visualization application that we're going to take a look at is mailing lists, and that's kind of ironic. We started with the mailing lists, and we're going to end with the mailing lists. The mailing lists, of course, are from my open source Sakai project, which I love and very proud of. And so what we're going to do is we're going to crawl the archive of a mailing list, and then we're going to do two visualizations. One is a activity visualization, and another is a word cloud. So it's probably the more important thing is when I do the demonstration of how the software works. So this is a large data set, so you got to be careful. This could spider gmane.org, which is a very free and friendly archive. This data originally came from gmane.org, but I've got a copy of it. And so gmane.org is not rate limited, but if everyone who is watching this starts spidering gmane.org at the same time, you will crash it. It just doesn't have the horsepower to give you this data as fast. And so I've got something that can give you the data super fast and has no rate limit on a really good server, and it's cached all around the world using a technology called Cloudflare. So please, please, please don't point this at gmane.org. Point this at the URL here, mbox.drchuck.net, etc., and then you can run this as fast as you like. Now, another thing to worry about is if you have a metered connection. So don't do this on a cell phone connection because you'll pay thousands of dollars perhaps. Make sure you run a no-cost connection before you start running this, because this is going to pull a lot of data down. If you just start this from scratch and you let it run, it on a super fast connection, downloading the whole thing is probably about 4 hours. On my home connection, when I had like about a 10 megabit connection, it took several days. And so just understand that in this one, it's both fun to deal with a ton of data and it's scary to deal with a ton of data. So this one is big. This one is, you'll see the process in action because it'll run for a while. The things will take a long time. So here's basically the flow of the data in this particular one. You are going to have the restartable spider that talks to the API, mbox.drchuck.net, which has a scalable copy of all this information. And again, it's going to do kind of a raw database, not a very clean database. It's sort of a mess. It's just enough columns to keep track of whether or not we've got this page or not. And so this has, the ones we've retrieved so far. And so what Gmane does is it sort of scans down to see where to retrieve next, gets that, and then starts scanning and then adding things here. So it just adds it, and then it blows up, and then it comes in again and says, okay, I'll start here, and then it starts retrieving stuff and fills this in, fills this in, fills this in. And sometimes you put like a delay in this so you don't overwhelm networks or don't overwhelm servers. But basically this is pretty much a raw retrieval of the email messages. And this file can get rather large. This is the one that's greater than a gigabyte. Now this data is actually really nasty. It's email data. The date format's changed. This is data that lasted from 2004 to like 2012 or 13. And so this data has got a lot of things wrong with it. It even has things where people's email addresses changed. And so it has this mapping file. This comes along with it. This mapping file that says, here's this one person, and here are the 6 email addresses that they used throughout the life of the project. And so there is a relatively complex, and so this part here is super slow, very slow. This part here is slow, but it'll take, like, depending on how fast your computer is, somewhere between 2 minutes and 10 minutes. This first part will take days, perhaps, depending on the speed of your network connection. And so what Gmodel does is it reads through this, it actually recreates, it wipes this out and recreates index.SQLite every time it runs, so that you can change any number of things, you can respider things, you can do whatever. And often the cleanup, this is one of those cleanup processes, and you have to tweak the cleanup process. You like look at your data like, oh, the cleanup missed something, so I got to run it again. So this produces index.SQLite every time it runs. So this is like 2 to 10 minutes. Gmodel is 2 to 10 minutes. And it like maps names, and when it's all said and done, this is a very small, highly normalized, it's a nice data model. This one here had the Content SQLite has an ugly data model. Index.SQLite has a pretty data model. It's got foreign keys, it's got all this stuff, and all those things we talked about in the database where it's efficient. And so in your mind, keep track of how fast it is to scan all the data in a database with a bad model, and then watch when you run like gbasic, which is a scanner, or gline, which produces line data, or gword, and watch how fast they run. They run in like a couple of seconds at the most, and this runs in 2 to 10 minutes. And the difference is that's because the data is efficiently modeled in index.SQLite. So you can take a look at that using SQLite browser and take a look at the data model, and you'll see it looks just like the stuff we talked about in the database chapter. It's got foreign keys and all those things. And so that runs, and you got this, and then we do our visualizations and our analysis from this clean version of all the data. And so GBasic just loops through and prints some stuff out. It's a great way to test things. It's a pretty easy to understand program, and you could take a look at it. Gline does some bucketing and makes some histograms to produce a line graph. And then GWord does a different histogram. It does a histogram of word frequency and then produces that as the word frequency ends up in gword.js. And then we have two HTML files that use the d3.js visualization to produce a line and a word chart. And so, you know, in another video I will show you how this code works, which is probably more useful than this picture. But this is a whole bunch of good stuff in this particular application, and if you really understand everything in here, you can build a pretty sophisticated data retrieval and analysis pipeline. And so that's it. I thank you for watching all these lectures, and look forward to seeing you on the net.
We're doing some code walkthroughs. If you want to get the source code, you can take a look at the sample code and download it and work through it. And so what we're working on now is doing some retrieval and visualization of email data. It's kind of ironic. We are going to now look at the email data that we started with. It's the same Sakai developer list email data. And so there's this service called Gmane. And Gmane archives developer lists and various email lists. And I've made a copy of their data because all the students in my class hitting their server with their API would crush it. So in order to be a nice guy, I put up a much more powerful server with just the data from this one list. And it's about a gigabyte of data. So be real careful if you're paying for network. So the basic process we're going to go through is we're going to have a spidering process that's a simple, restartable, focused on the network problems, data pulling to pull content.SQLite, and there's going to be a database there. And then we're going to have a cleanup process. This database is going to get large, about a gigabyte. And then we're going to have a process that kind of grinds through this data. It takes a while. And so then it's going to read this mapping, and I'll show you that when it comes, because things like people's names have changed over all these years. And it does a cleanup and makes a really nice, highly relational version of this data. And then we visualize from here. And so this could take you several days to finish this. This will take like a few minutes to run, and then this will just take seconds to run. And so this is a multi-step process where if you were doing something like running something for 2 days to produce a visualization and it blew up 3/4 of the way through, it would do you no good. And so that's why we break this into simple parts. But right now we're just going to focus on this part right here and take a look at the mail bit, the mail bit, and retrieve the mail, and then we'll have another video to talk about the rest of this stuff. Okay, so let's take a look at the code. So here is Gmane.py. That is the basic code, and it's hopefully this stuff is starting to look familiar. The thing that's weird here is we got to do some date time parsing, and there is code that's out there, but you may have to install it. And I had to write my code in a way that didn't assume that you could install the date time parser. And so it has it, even if that's not there, it uses my own date time parser, and that's what this code is. Don't worry too much about that. And of course we have to deal with the lack of certificates inside of Python. And so we start things out. And this is really a simple table. We've got a messages table that's got a primary key, the email itself, when it was sent, what the subject, and the headers and the body. Okay? And so what we're going to do is, because we have to pick up where we left off, we're going to select the largest primary key from the messages table and retrieve that, and then we're going to go to the one after that. Okay, and so we know what the ID is, and we're going to pick up where we left off. And so we have a starting point. It starts either 0 or 1,
and we're going to ask how many messages to retrieve. We've got some counters, and so we're going to say, okay, see if select ID for messages where ID equals whatever that starting is. It's the highest number we've seen so far, and if row is not none, that means we've already retrieved this particular email message. Otherwise, we're going to keep on going, and we're in good shape. And this is one that we want to retrieve, and we're subtracting that so we don't. And so this is the base URL. This is the URL of our API, the one that I have a nice copy of all this data on a server that's accessible worldwide and won't crash. So the format of this is you can say I would like the email address for from 1 to 2 or from 100. Oops. From 102, 101, message 101 to 102, and we can just kind of walk through these things. So that's the message ID. And so if we're going to make the URL, we're going to take the base URL, add the starting address, and then add +1. So we got the slash at the end of the starting address, and so that's how we form those. And we're going to retrieve that, and we're going to decode it. We've seen this in some other ones. We're going to check to see if we got legit data. If not, if I got a 404 not found or something else, we're going to quit. If someone hits Control-C, or Control-Z, we'll get the program interrupt, and we'll stop. If there's some other problem, right, we're going to complain and keep going. And if we have 5 failures in a row, we're going to quit, but it will just keep on going because these things do have glitchy bits here. And so at this point, if we've made it this far, we've retrieved the URL and we've got the number of characters we've retrieved. And if we get bad data, if it doesn't start with from, because this is a mail message, right? And they all start with from space. If it's right, it starts with from space. Then what we're going to tolerate up to 5 failures there for bad data because it could be bad. And then we're going to find a blank line because that's the new line at the end of one line and then a blank line. And then we're going to take and break this into the headers, the mail headers, which is this stuff right here up to but not including the blank line. And then the body is everything after that. Okay. And so we'll just break that into pieces. Otherwise we'll complain and tolerate up to 5 characters. And then we're going to use a regular expression, kind of from the regular expressions chapter, to pull out an email address from the from colon line somewhere in these headers, from colon right there. It's going to go find a less than and then pull this stuff out up to it. So you got the less than, you got the parenthesis, you got 1 or more non-blank characters followed by an @ followed by 1 or more non-blank characters, and we'll get back a list of those. We should only get 1. If we find 1, we're going to grab the email, we're going to strip the lowercase, and if we got some little nasty less than sign in there, we'll tolerate that as well. So this is kind of cleanup, and you get used to this where you're like, oh, how come all those email addresses have this other stuff in them? And then we also look for it if there are no less than signs, and we do this way. And that's different. Some mail messages have it this way, and others, again, you write this code after you watch it for a while. You're like, oh, it's crapped out and giving me bad stuff. And I make them all lowercase so they match better and get rid of bad characters. Well, now I got an email address. Then what I do is I look for the date of this. So I'm going to graph these by date. So I look for this line and use a regular expression to pull that out, right? So I'm looking for a date, followed by a blank, followed by any number of characters, followed by a comma. So I'm not interested in this Wednesday bit, so I'm skipping that bit right there and going and grabbing everything after that comma space. And so it's really here to the end of the line. So that's the new line. And so it's going all the way. It's going to pull this bit right here. That's the text. And this is where we're going to say, oh, that's kind of a funky looking date and we want to standardize that date. So we're going to, let's see, Yeah, we're gonna chop it off at the 26th character. Apparently, I don't know what the 26th, why we care about the 26th character, but we chop that off at the 26th character. And then we're gonna parse it, and that's gonna give us back a nice clean date, sent at date. Otherwise, we're gonna complete, we're gonna quit. And if we can't parse it, then we're gonna tolerate 5 bad email addresses in a row. Then we're looking for the subject line using another regular expression. Subject line, regular expression, that's pretty easy. Up to but not including, right? There's a blank there. It's the subject. And we pull that out, we get the subject. Now at this point, we parsed it and we got good stuff, so we reset the fail counter because I kept saying if you fail 5 straight times, you quit. And we're going to print it out, and then we're just going to insert that stuff. We've got the ID of the message, which we've got the email address that it came from, the time it was sent, the subject, and then basically the headers and the body, and we're just inserting it. And now we're going to say every 50th we're going to commit it, so that speeds things up, and every 100th we're going to wait a second. So that's, you know, count is going up, 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 and every 50th you'll see it pause. And then it will, every 100th, it'll pause for a second. Mostly that's to let me hit Control-C or to not overload any server. Okay, so that's the simple one. The problem is this data just gets ugly, and so you'll find yourself wanting to reset this and start it over. This one's going to work, of course, but these are hard to build, and that's why it's a good idea. Oops. Python 3 Gmane.py. How many messages? Well, let's just do 1. Okay, so it went and grabbed, oh, do I have this already running? 51 through 52. Let me start over. +-l star SQLite. Okay, rm content. I must have run it to test it. So let's run it again, Python Gmane.py, and ask for 1 message. Okay, so there we went and got message 1 from 1 to 2. We got 226 characters, and we printed out the email address, the time we got it after all that hacking, and the subject line, and that's what we got. So if we take a look at the database and we go into the Gmane, every time you see the content SQLite journal, that means it needed to run a commit, and it hasn't run a commit, but I'll hit enter and that will do the commit, and you see that vanish. So now I can open it and I take a look at, how come there's no messages? Did that one not get stored in there for some reason? Just refresh. Huh, well, let's run it again. Maybe it didn't commit. Maybe I got a bug in it. Let's make a change to the code. I'm going to see this connection.commit. See that? Connection.commit. I'm going to commit there. And the other thing I'm going to do is every time I stop to read, I'm going to commit right before I read it. So I think we should, I hope that doesn't blow up. We'll see. So the idea is that if I want to stop, I want it committed. So let's do this. Let's do 1 message. And now I should hit, is it committed? Now that I put the commits in, I think that it will look better. And I can't refresh. And so there it is because I committed it. And I don't have the journal file, so that's good. So that's a good idea to put those commits there. So I'll just leave those commits in. When you download it, it'll have those commits in there. So again, I put a commit here and a commit at the very, very end to make sure. And then I missed that. But now we get 1, right? And so let's just run it again, and you'll see how by selecting the max of the ID, it's going to select the max of this and then add 1 to it, so it doesn't do the next one. So if I run it again, I say give me 1 message, so it goes 2 to 3, and give me 2 messages, right? So I hit enter,
And I can do refresh, and now you see we've got 4 messages. Okay, and so let's just fire this baby up. Tell it to get 100. Run, 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 run. Right? It just goes and goes, and it pauses once in a while to do a commit. And if I made a commit every time, oop, it just paused there. Now it finished. So this will run, and we will get a bunch of data. The problem is if I just run this, it'll take about 5 hours, okay, to run this and get this all. And I've got a really fast connection. So I have got a file that you can download. Let's go find it. Let's see if I can, let's see how long it'll take me to download this. I've got a file that you can download and save. Now I'm going to use the command line curl, or wget is another command that we Linux and Mac people can use. I don't know, you might have to use your browser to do it. Let's see how long this is going to take. It's retrieving. Minute 30. Okay, well I'll just wait when this comes back. Okay, so now that's done. I was averaging 10 megabits a second. I downloaded about 600 megabytes, 10 megabits a second. That will probably be slower for you. But so now if I take a look, you're going to find that that content.SQLite is 624 megabytes. Now what happens is I've pre-spidered this, and so now if you run Gmane.py and ask for 5 more messages, it will pick up where I left that one off. So it's up to message 59,000. And I think that, oh, you saw an error. See, you saw a bug in that one. I don't know what's wrong with that one. So let's see if, so at this point we're going to have most of the data. It might find its way to the very end. Once you get this, it should be not too much more. I don't know, maybe it's like 63,000 or something. So what we'll do is we will let that run, and we will come back when that one's finished, and run the next phase after it's got all of its data. Okay? So thanks for listening. The work that we're doing right now is we are in the process of building a spider and visualization tool for email data that came originally from this website Gmane, but I've got my own copy of it. And so what we've done before is we ran gmane.py, and I grabbed a URL. I have a URL that has all this data, and I downloaded that, and then I ran Gmane again to catch up. So it took quite a bit of catching up, but by the time I get to, remember how I said it tries to fail 5 times? Well, it ran out of data at 60,421, and then it started failing, and then it quit. And so we pretty much have all of our data now. We have finished this process in content SQLite. Okay, and if I take a look in the database browser, we can see we got 59,823 email messages. And so if I look at any of these things, you see the headers, you see the subject line, you see the email address, you see the body of it. So remember, I split the body in half, and headers, and so I made this as raw as I possibly could, because as you saw, I had to spend so much time in the Gmane just getting the data successfully retrieved, and so I don't like cleaning the data up too much. And so what we're going to look at next is the data cleaning process. Okay, and so this is gmodel.py is code we're going to take a look at now. So let's get rid of those guys and look at gmodel.py. I don't think I need URL lib in this code. Do I have any URL lib? No. So I don't need that. Sorry. Fix that. Okay. So
it's going to read from the database. It's got to call. It's going to use regular expressions, and zlib is a way to do some compression. And so I'm going to do in this one. I'm going to compress some of the data to make it so that I have less data. To some of the text fields are going to be compressed. I wanted to keep these fields uncompressed inside of messages, so we have some just cleanup messages and cleans things up. And it turns out that the way email addresses in this particular mail corpus, they changed over time, and there's certain kinds of things. Sometimes the gmane.org is the email address when people want to hide their address, and I made all kinds of stuff, and I split it and checked to see if it ended with this, and I cleaned up things, this, that, and the other thing. And so I have all kinds of cleanup stuff going on in here. And I have this mapping and DNS mapping that I'll talk about in a bit, where organizations sometimes sent email with different addresses over time, and people sent email from different time. And we're going to do the parsing of the date, and that is the code for that. We're going to pull out the header information. This is sort of borrowed from the other code. We'll clean up the email addresses and the domain names. And we'll pull the date out, pull the subject out, pull out the message ID, various things. So here's the main body of the code. We're going to go from content.SQLite to index.SQLite. And what I'm going to do every time is I'm going to wipe out index.SQLite and drop the messages, senders, subjects, and replies. So this is a normalized database in that it has foreign keys. So there's a messages table here with an integer primary key, the GUID for it. The GUID stands for Global Unique ID, sent time, sender ID, and it's going to have a blob. These are blobs, binary large objects for the headers and the body, because I'm going to compress them in this database to make them. And then the senders, each sender has a key, and then subjects, each subject line is going to have a key, and then replies are a connection from one message to another, and so this is like a many-to-many. Now, I also have this file called mapping.sqlite, and so we can take a look at that one, mapping.sqlite. And so what happened is this has two tables that I hand deal with, and so sometimes this was a email address that mapped to that. So indiana.edu, that's a way to take that's the email address, and then these were a bunch of people that had email addresses changing throughout the project, and I sort of kind of mapped them in a way. And so this is just sort of like I pull this in really quick, and I read all this stuff from the DNS mapping, and other than stripping and making this lowercase, etc., I just am going to make a dictionary. DNS mapping, which is the old name to the new name, and the email address mapping from the old name to the new name, and I'm using fixed sender. Fixed sender is because the email addresses even within Gmane were kind of funky. So don't worry so much about this. Okay, and so now what I'm going to do is I opened up a connection just to read all that stuff in, and now I'm going to actually open the main content. And I'm asking it to open this a little trickier. I open that read only. That was so that I could potentially be running the spider and running this at the same time. I get a cursor, and so I'm going to read through. So in the content file, this is the big one. I'm going to read through and go through every one and write all of these things in. And I'm going to take all the email addresses and I'm going to put those in a list. So I loaded that. I've got the mappings loaded. And so now I'm going to go through every single message. I got all the senders, all the subjects, and all the global unique IDs. So I read in each message. So now I'm going through content one at a time. I parse the headers. I check to see if the sender's name, email address, after it's been cleaned up, is in my mapping.get sender, and the default is I get back sender. That's what that's saying. Look up sender. If it's in there, give me the entry of that key. Otherwise, give me sender back. We're going to print every 250 things we do. We'll complain if this is true. We're going to go get the mapping between the senders, which is a way to look up the primary key. I could have done this with a database thing, but I wanted it to be fast. So that's part of the reason I read all these things in, so I could have those mappings to be really fast. You'll see this takes a little while, even though it, even though it's I got all this stuff cached. And so then if I don't have a sender ID, meaning that I haven't seen it yet, then I'm going to do an insert or ignore into senders. And then I'm going to do a select, and then you've seen this where I grab the row back and I'm really just trying to look at the recently assigned ID, and then I'm going to not only set the sender ID for this iteration of the loop, but I'm also going to store it in the dictionary, and so that builds this dictionary up. And you'll see the same thing is true for subject ID. I'm going to insert it into the subjects table and get a primary key if I don't know what it is. And then I'm going to put it into, not only am I going to put it into the database, but I'm also going to put it into my dictionary. And the same thing, I guess I didn't do it for the GUID. Okay. So now what I have is the sender ID and the subject ID, which are foreign keys, into the sender table and the subject table. And I'm going to insert the message with the sender ID, subject ID, the sent at, headers, and body. And the values here are the GUID, sender ID, subject ID, sent at. Now this here is zlib compress. So what I'm taking is the message, the header, and the body, and this little bit ends up with a compressed version of this stuff, and you'll see it in a second. And this keeps the size of these text things down at the cost of the computation of, at the cost of the computation to compress and decompress when we want to read it, okay? And then I pull the GUIDs out, the ID, which is the GUID, and I pull out the primary key for this thing based on the GUID, and I update this dictionary, okay? So let me run that code. It is doing a lot of cleanup, and I'll tell you, it took me a long time to make this work. So this code that I'm running now, oh, don't forget to take a Python 3, Chuck. So this is going to run every 250. So it did all this pre-caching, so that's how long it takes to do 250. Now there's 60,000 in here. And so this is really busy. The reason it's bouncing back and forth is that every time it makes this journal file, and then does a commit. So you can kind of see that it's busy making journal files and committing, and there's a lot of activity going on here. Just so happens that Adam shows me these files. Okay, so it finished. It took about 3 minutes to finish that, right? And so if we take a look at the size of the files, we will see that the index is much smaller. It's fully normalized. It's still 263 megabytes. It's all compressed. So let's take a look at that in the browser. So it's 200 megabytes, but it loads up a lot faster. There we go. So we have a senders table, right, which is just kind of a many-to-one table. We have a subjects to table, which is a many-to-one table. And we have messages, which has foreign keys. It takes a little bit to load that up. Okay, and so we see the foreign keys for sender and subject, and that saves us. All those foreign keys save us. And so we have, you can kind of see that I can't see the headers in the body because now they're compressed. That saves me a whole bunch of stuff, right? It saved me a whole bunch of stuff. You know, and so that's what's in that file, and that we've finished this process, okay, and we've finished modeling the data and making it really clean, and we'll pick back up, and the rest of the stuff we will do is actually visualizing pulling data out of index.SQLite. The idea is this can be restarted, this can be run over and over and over, even though it takes like 3 minutes to run this. That's way better than 5 hours to run this. So 3 minutes, 5 hours,
And then we'll see now reading this is in seconds because we got it all nice and normalized in a quite pretty way. So I hope this has been useful. In the next one, we'll actually do the visualization. We are in the process of retrieving data from this Gmane server, one that I've made a copy of. And we have so far spidered it all. Ended up with 600 megabytes of spidered information. We have ran a rather complex cleanup process that you probably don't need to fully understand. You can look at it for patterns, but in general, the cleanup process will be very sensitive to the data. And then we have this index.SQLite, which is 260 megabytes right now. And we're going to now do the fun, easy bits here, where we're going to run little queries that just pull data out. And so these are much simpler. So part of what I wrote when I was doing this is I wanted to do some simple, basic calculations on the data to make sure. I really was sort of looking for anomalies, right? What was working, what wasn't working. So I wrote a series of really simple things like this gbasic. The gbasic code just give me some basic data, right? So I wrote things down and I counted things. And so do I need URL lib request in this one? I don't think so. Let's fix that bug. It's not there. No reason to put any of that stuff in there. So it reads that index.SQLite, which is our cleaned up data. It reads through and makes a dictionary. This pattern you're going to see a lot, where I'm going to make a dictionary of ID to senders, save myself repeatedly looking at things. I'm going to grab the subjects. I've cached them all. I could have done this all with SQL, but I just wanted to do things faster. And now I'm going to go through each of these messages and make a dictionary of them. I'm going to put a lot of stuff in memory. And then I'm going to do some counts. I'm going to see who is sent the most, right? The organizations. And so now I've got to go through the all the messages. I am not actually, so you'll notice that I'm not selecting the body or the headers here. I am just getting sender ID, subject ID. I probably could have done this with a join. It would have been cleaner. You can do that. You can make that change. Do that with a join so it's cleaner. So I'm going through all the messages except not the body, so this is going to be really quick. And I'm pulling out the sender's ID. I'm breaking the sender into pieces. See, my data's clean now. I cleaned it all up in the previous processes. And if I don't have two pieces, I continue and I get the domain name. So I have the person. I'm doing a basic dictionary histogram for the people and the domains. And then I'm going to sort them, right? With a sorted, and we're going to grab the key. We're going to sort it by the how many there are, reverse, and then print out the top few of the organizations and the top few of the people. Okay, so we'll just run that code. Python gbasic.py. Let's dump out the top 10. So we loaded 59,000 messages, 29,000 subjects, and 1,800 senders, and figured out the top 10 people and the top 10 organizations. And you can write various things like that just sort of scream through your data, and it's good to get sanity checking on your data. Okay, so that's gbasic. Now I want to do gword.py, because that's kind of fun. gword.py. I don't need URL lib. Why do I keep putting URL lib in all these things? So we'll get rid of that. So this is really simple because I'm just going to go for the words in the subject line. And so I go through index.SQLite. I read in all of the subjects. And I make a dictionary of those. And then I go and find all the subjects. And then I'm doing this code right here. I'm pulling out the subject based on the message, and I'm doing this so that when the subjects are used more than once, I count the words more than once. This stir make trans, I talked about that in an earlier chapter. This basically throws away a punctuation in numbers, so that when I make my words, I don't end up with words that are like dashes, it compresses them down. Then I strip it, I convert everything to lowercase. This is basically just to keep too many words from showing up. Then I do a split, and then I got a counts, a dictionary. So this is a no punctuation, no numbers dictionary count. And then I just take the and do a dictionary, and then I sort them in reverse order. And then I figure out what the highest and lowest is by running through I could have probably done this with a max and a min if I felt like it. And so now I have the highest and the lowest. Yeah, I should have done a max and a min on that one. Why did I do that? But oh well. And now I've got to spread out the size, and so I'm going to produce this file gword.js, which is needed by the visualization because it's going to use d3.js, a word visualizer, and gword.js. I have to tell it how big the text is, and so I'm doing some text normalization. Took me a little experimentation. So if I run this now, and I say Python gword.js, and I say Python 3 gword.js, which is a lot better. Oh, not Python. Okay, so now I can go look at the gword.js, wherever that is, gword.js, yep. And so this is basically, it normalized all the frequencies and made it font size. These are font sizes now, okay? And so this is just the data that's needed by this gword.jm, which uses this D3 visualization word cloud code. So this pulls in all my data, and then this is just some JavaScript that draws the picture in on the page, okay? And so the easy part now is to just open gword.htm in a browser. It just so happens on a Mac I can do this. And so that gives me a word cloud based on that data. It kind of randomizes it and shows different stuff, but it's using this data to generate how big those things are, and then using a bit of randomness and simulated annealing to lay it out. That's not stuff that we actually have to worry about, okay? So that's how we get to the point where we're seeing a word cloud from this. Now we're going to do another visualization, and this time we're going to do a line visualization, and we're going to create a thing called gline.js and produce with another HTML file. We're going to use D3 and produce that output. So let's say goodbye here, goodbye, 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 goodbye. So gline.py, get rid of that file. So again, I'm going to preload all of the senders in this case. And again, I could have done this with a join, probably should have done this with a join. I'm going to preload all the messages, the sender ID, subject ID, etc. I'll load those up. And now I'm going to read through. I'm going to have the sending organizations and the senders. And I'm going to split the senders, and I'm going to have the sending organizations, and then I'm going to do a simple dictionary as I accumulate the sending organizations by splitting the person's name into @ signs, and then based on the organization I accumulate it, and then I sort them, and I pull out the top 10 organizations, print those out, and now I'm going to break this down into months. And I'll show you what this looks like in a second. Let's go to the gline.js. So the month looks like this. Okay, so the month looks like that. So that's the first 7 characters of the date. So if we look at the date looks like that, and the month is the first 7 characters. And this is the data that I've got to give it. We'll clean that up in a second. That data will look better in a moment. Go back to gline.py, and so this is we're doing a the key is a tuple, which is the month, and which organization that did it. And it's only in the top 10 organizations. And then we're going to do a we're going to basically do a dictionary where the key is a tuple. And then we're going to sort it. Sort by key in this case, not by value. That's in the months is going to sort that. And then we're going to write all this data out into gline.js. So let's go ahead and run this. And again, this is just the data that has to be written in a way that the JavaScript can understand it. Python, gline, Python 3, gline.py. Okay, so top 10 organizations. So now let's take a look at that JavaScript. So this is what it looks like. So it just so happens that you got to tell it these are the data points. These are the lines. So this is the year, the line for University of Michigan, gmail.com, swinsburg.com. So this first column is that line points, and the next line points. So all this code was to get the data in such a way that I could produce this JavaScript file, because if I look at gline.htm, I need that data in that particular format, and I've got all this stuff. I make a line chart and I draw it with this data. That data, I had to go read all the documentation on how to figure this stuff out, right? And that's the data that I'm going to use, and I had to figure this out, and I had to transform it and make it pretty. It took me quite a while to get this to work, and this is not a JavaScript class nor a how to visualize in D3, but basically we pulled all that stuff in, and here's the G line that came from the JavaScript, and then it makes an array data table, and then that data table is what G line draws. So with no further ado, let's open gline.htm to show that data. So there you go. That's the Sky developer participation from 2015 through 2005 through 2015, based on which organizations did the most commits in Sakai. And so I know that I haven't done this all this code full justice. There's a lot of code here. The fun is just to kind of run it and see it, and then when the time comes to come back and see the techniques that are used when you're trying to build your own visualization pipeline. So I hope that you found this useful. This is a lot of code, hard to explain in 15-20 minutes, but I hope you take some time and look it over, and I hope you found all these videos. This is kind of the last walkthrough video for chapter 16 of the book, and so I hope that I will see you on the net.